Good morning, everybody. Take your seats. We are ready for day 2. It's going to be a wild ride, I'm sure, especially if you all feel like I do this morning. Thank you, Danny, for giving us all headaches. Love it. Some people were sensible and went home. No, it was a really good night. Thanks to South 32 for hosting us down at the quarter deck last night. It was really good, very generous. And we all appreciate that support. Okay, we've started online. We've got the nods and the thumbs up. Evan has tested out the bell this morning to get your attention. That's going to get a lot more use today. And before we start, I would like to acknowledge the Woolgoorukaba and the Bindal people, who are the traditional owners of this land. And I would like to pay my respects to elders, past, present, and emerging. And I extend that respect to other Indigenous people who are also present. Okay, the agenda is up on the screen. The writing is a little bit small, sorry if you can't see it. We're going to start off with some mineral systems talks up until morning tea. And then we're going to have a pretty cool mine waste session with a variety of speakers from UQ and also SCIAPS, and Kobie Johnson from the Department of Resources is also going to be joining us. Then we're going to have a couple of sessions this afternoon playing with some data and looking at some of the new compilations and new data packs that are out there, and new opportunities for a digital twin of Queensland's geology with Steve Micklethwaite and Steve Amar, and then the Northeast Queensland Deposit Atlas to bring us all home. And then we will also, if anyone feels like they need it, we will also have some drinks out in the foyer there this evening, but not as many as last night. Okay, so first up, we've got our own Vlad Lisitsin, who's the manager of our mineral systems team and one of the smartest guys that I know. So he's going to talk to us about mineral systems of North Queensland. Have you got your mic on?
Yep.
Cool. Take it away.
Okay, thank you, Helen. Let's see if I'm smart enough to fire up my presentation. Okay, good. Good, I failed, sorry. Okay, lasers. Okay, good. Okay, good, thank you. That's the good page. Okay, good morning, everybody. Well, first of all, thank you all for coming. Thank you all for making it here today. I see lots of survivors of the night before, so I appreciate it. I have deep respect, borderline admiration, so I have to be here. You don't have the excuse, so thank you. And thank you, Danny. So the water of life kept flowing, lubricating, facilitating lots of very fruitful conversations. So it was really good. Okay, thank you. And first of all, just let me tell you that this title is a bit of a false advertising. So all advertising is, it's a very immense topic, and really I can't do it justice in 15 minutes. So I'm not even going to try. So I'm not going to try and wear you out by multiple names of deposit types, deposit styles, and lists of chemical elements and other properties. It's just not the point. So the main point of this exercise today, it's a forward-looking presentation. I'm going to focus a little bit on the definition of the problem, what it is we're trying to address, why we're doing these types of work. Give you very few illustrations of recent past and current work, the types of activities which we're trying to do to address this problem. And the most important thing is a call out for help, because there is no way we can resolve this problem on ourselves. Within our mighty internal team of several people. So that's forward-looking and call out for help. That's the main purpose of this conversation. So if you miss out everything else, just remember that. So just talk to me or a few other people from the survey about how you can work with us in the future. So first of all, a definition of the problem, what we're trying to do. Just imagine a very practical greenfield exploration situation. You are in the right place, you are in the right district. Some smart people from project generation told you that that's the place to do the drilling. You drilled a few boreholes, you found something which is not really a sexy body. So it's something, yes, some nice looking altered rocks, a whole 1 centimeter of mineralization. in 200 meters of drill core. So what do you do next? So do you have any idea whether you are within a footprint of a deposit? Obviously not an obvious one. So if it's a footprint of some kind of a mineral system, well, which one? Which style of mineralization you might be looking at, and even more important and more difficult, so what do you do with this all? So you've just spent $2 million of your company money and a whole field season. So do you have enough confidence to say where we need to go next? And so is there any way with all the smart tools, with all the smart equipment and all the smarts you can have access at your disposal, can you see that you are this close to something this major? And this is a real situation. So this not much, this very boring signals, which are very, very easy to miss, happen to be just a couple of kilometers away from your center. And that's pretty much the problem which we're trying to resolve. How can we acquire the template data and do analysis and extract the value out of this data to help you making these decisions? So first, to give you some appreciation of the scale of the problem, this is about half of our project area. So just the eastern half, I'm starting from that because we happen to be in the east. And that's half of the project area is about 800 kilometers north to south, about 200 kilometers east to west. There is a great variety of distinct mineral systems of different ages. And here I'm just listing up the hydrothermal ones. So it's lots of styles of gold mineralization, tin tungsten, epithermal gold, orogenic gold, intrusion-related gold. Each of them have their distinct signatures. Each of them have their distinct footprints and ways of navigating them. And the scale of our work, where we're trying to characterize footprints, is something like within this circle over here. And Courtney spent most of the day yesterday discussing what happens with that small circle. And it's just one small circle of many. So the second part of the second half of our project area is northwest. That's where we spent most of the past 4 years. And we have completed a few project activities there. So there are a few products which are released. And the most important things there are not the beautiful PDFs, but the data associated with those PDFs. So we are trying to build up the baseline information, which can be used by others, not by us, in making decisions about exploration within a district. And each dot on the map represents a deposit on which we have done some work, not trivial enough to show on the map. So it's busy slide. And it's a lot of work. So the first and most fundamental activity in this whole sequence of smart projects is acquisition of samples. Actually, everything starts from samples, and until we get access to a large enough collection of samples from the right area in the context, we don't have anything to work on. So we could spend a wonderful time exercising our intellectual prowess, trying to interpret existing, not sufficient data, but quite often, like frankly, no data means no data. And yes, we've tried some magic with smart machines and machine learning, but in many cases, if your fundamental data is missing, it's missing. That's it. And spare some thought for that anonymous person in a reflective shot. That anonymous person with Courtney here. So that's where the real serious activity begins. First, we need to identify the drill core which we need and make sure that it's of the quality which allows for the work. And then we need to make it into pellets and make it in the core store. And then the actual smart work only begins. So once we get information from a company or company reports to suggest that we have the right materials to work with, we're trying to characterize what happens within those samples at the drill core scale. So what happens at the scale of tens to hundreds of meters. And we normally do it by continuous scanning. So we have our very own Haloga machine, and you saw a presentation from Dan yesterday. Illustrating just one of many applications of that machine. We're doing other bits of scanning like continuous XRF to characterize variability of chemistry downhole. And that's pretty much to still build up understanding of the framework and get some understanding of what happens at the scale of tens to hundreds of meters. But then we need to go to the scale of samples, because that's where the properties can be measured, which can allow us to answer the question whether it's mineralization, whether it's alteration, and of what kind. And we have to be very sparing, because I showed you the scale of our project areas. We could easily blow our annual budget on 2 boreholes. So we cannot do continuous sampling, continuous doing everything. It's just simply not feasible. So sample selection is very critical, and the most basic thing we do is multi-element geochemistry, measuring every property we can realistically do in a commercial lab, including everything which has been classified by anyone as a critical mineral, realistically measurable. And from that point onwards, we are going further into further details like microanalytics, like a beautiful illustration here of micron scale resolution distribution of chemical elements and minerals at the bottom. This is a beautiful illustration explaining why SEDEXs are not SEDEXs. So it's just showing that sphalerite replaces carbonates, and it's a carbonate replacement process. And that's what we see everywhere. So just to give you a quick summary of the outputs for the Northwest Queensland. So we did a fair bit of work on ICGs, and we know enough to say what typifies their common signature. Yep, they're typified by not only copper, gold, but by tellurium, selenium, and that's quite typical and common signature of them. And yes, we know that they can contain sufficient amount of cobalt to be worthy of potential extraction. Some of them, very few of them, have substantial rhenium, including some affiliates of ICGs, which are essentially rhenium deposits. Rare earths are present in some, but not in most. So-called sediment-hosted copper, we see the disappearance of the prominent signature of tellurium. The common signature there is bismuth, arsenic, antimony, which is typical for this whole group, and potential byproduct. It has been extracted in some places. It will be extracted in the future, is cobalt. So-called SEDEXs, leaving aside the question that they're not SEDEXs, they have also quite distinct and common signature with a particularly strong thallium, for example, and potential byproducts include germanium, and that's why we spent a fair bit of a wonderful time trying to figure out how to analyze for it, because standard techniques lose about 95% in the analysis. So just warning for you. And we did a fair bit of work on phosphorites, which are generally known to be enriched in rare earth elements. And we found some places which are so enriched in rare earth elements that it's pretty much getting towards the potential ore grades. So I'll just give you a bit more detail about what happens in the world of ICGs, because they're particularly diverse, because the group is particularly poorly understood. So we collected, and the statistics keep getting out of date. So this 1,000 samples by now is probably 1,200. So the number of drill holes increasing. So that's a moving beast. So we went with the help of our CSRO people and ourselves to more than 20 deposits. We collected multiple samples from as far away as we could get through the middle of the ore bodies. And I'll just give you some teaser results from very diverse end members of this family, from Ernest Henry, Eloise, quite often called ISCG, Swan. Now, incidentally, you can see red rock alteration in Swan, which sometimes look very much like red rock alteration in Ernest Henry, except it's L-bite, not K-spar, and Osborne at the bottom. So geochemically, it's a very intuitive way to display geochemical signature. You can clearly see that there is a broad similarity. Tellurium is the most relatively enriched element of them all, but within that similarity, they are very, very different. And whatever people normally call typical ICG or Cloncurry ICG signature, it's only the signature of Ernest Henry, and pretty much that's it. And everything else is sufficiently different, and everything else is different from each other as well. So that's a matter of complication. So another way to illustrate that diversity. So for people who like principal component analysis of geochemistry, I can assure it was done properly. So it's just simply a way to visualize that different deposits have very distinct signatures and they don't overlap. And so what is considered typical ICG signature for Ernest Henry, it is the signature of Ernest Henry, E1, and a little bit of something else. And color coding here is just a way to highlight natural groupings, natural clusterings of deposit properties, just to reduce that variability to some sensible number. For enthusiasts of machine learning, well, this is machine learning. I'm not going to tell you how this magic was done. I can tell you after the fact, and Kate can tell you more about the nature of this work. This is just another way to highlight natural clustering of geochemical properties, identifying several distinct groups, and the most distinct and the most standout group is signature of Ernest Henry, which don't overlap with anything else but E1 and a little bit of Monaco. That's it. The group in blue contains so-called ISCGs and so-called shear or ironstone hosted, so they're quite distinct deposit styles in ICG group, but in this particular view of the data, they look close enough together. And the green group is the most diverse. This is, if you want to say, Cloncurry style ICG. That's the group in green, which doesn't have just about any of the characteristics of Ernest Henry. And quite often they're missing some of the letters in IOCGs. They start missing sometimes even I's, and they don't have, any of them have a distinct potassic alteration. It's just an illustration of the great diversity of this group. And this is the job of identifying signatures in just geochemistry. Geochemistry, well, some wise people and enthusiasts of geochemistry say that you can infer everything from geochemistry. I admire this view, and I'm more geochemist than anything else, but it's not quite true. So there is also mineralogy, there is also petrophysics. That was addressed by CSIRO in a series of their projects. They went ahead and collected a couple of thousands of samples of the same kind, the same size, done to the same specifications, measuring 9 distinct properties on top of our geochemistry. And this is a beautiful data set, the most machine-ready data set, which can allow comparison of properties of multiple deposits known to humanity. And this is an illustration of what we are trying to do with it. So we played with geochemistry a great deal, and you can get really, really good impression out of just geochemistry. But combining it with mineralogy and petrophysics, your conclusions can become much more robust. And so we had this exercise which lasted more than a year with CSIRO to try and bring it all together and see how we can identify joint, very, very, very multi-property signatures of different deposits. And Kate will tell you a bit more in more detail in the next presentation. So now going from the problem of identifying signatures, answering the question which deposit type, and into footprints. How to navigate within very obscure deposit or beyond deposit halos. We had a very nice exercise with good people in codes. So it was a brave decision. They've done a very good work in green rock alteration on porphyry epithermals. It took them only about 10 years and $10 million to develop the tools. So we brought them in for 3 years to solve everything for ICGs. Well, it was a bit optimistic, but we did make a good first impression. So we did get some good information about the signatures in mineral chemistry of a series of specific minerals typical for ICGs. And we got a good framework to start talking about distal footprints, what signals you can see in minerals which are distal to mineralization at a distance of 1 to 3 kilometers away. It's a very good start, but it's pretty much something which we're going to continue over the next couple of years, that's for sure. And now we're going to illustrate by example where we spent most of the time, and that's the most intensely sampled deposit of them all we have done so far, Ernest Henry. Just to illustrate to you the scale of our attempt to identify footprints. So the scale here is about 4 or 5 kilometers. So we start from the mine site over here, that's the open cut, and go 4 kilometers to the north and 1 kilometer to the south. And so far we haven't covered in sufficient detail east or west. And the attempt is to try and see what changes at this scale. So that's the scale way beyond usual university research, way beyond your usual PhD projects, way beyond what normal company people are doing in near mine exploration, because mostly it's where is the next ore shoot, and that's where the biggest problems lie. So some teaser of results to date. So we can clearly identify what is the signature of mineralization, the ore body, that's the group in red. We can see on the other extreme, the group in blue, that's pretty much as regional as it gets. So that's sodic alteration without any usual polymetallic chalcophile signature that you're anywhere near. So that's good. It's distal, and you can see it all the way out here. So it's the sea of blue. But the word of caution, you see that the sea of blue starts just above the ore body. And just looking at geochemistry mineralogy, there is no way we could see that we're just 30 meters away. So we could see that we are proximal to something all the way here. That's a kilometer away in the right direction. But we're going across, we're going in the wrong direction, and using just normal available data and our usual ways of dealing with this, we cannot see the signal. And that's an indication of the nature and the scale of the problem. So we should go beyond just looking at normal geochemistry mineralogy. And a bit of illustration of what we think we need to do going forward. So we looked at something at a scale of up to 4 kilometers in the right direction. We need to take it even further. So that's pretty much the scale of that box in the regional scale. So we think we have some good handle what happens within a kilometer. Probably we can see something in the right direction going 2-3 kilometers, but we need to go and map out from there just to make that big box bigger. And at some point, we're going to see that we're losing the signal. Probably we'll have to go back, but the general approach is still the same. Start from the known, where we have most of the data, and keep mapping out using all the smarts, all the intelligence, all the expertise from anyone, and make that box as large as possible to provide some vectoring within it. So that's pretty much the definition of the task for the future. And if you have any suggestions how we can make it, I'm all ears. We're trying to figure it out for the last 2 years. So that's our indication of our way forward. So we have done a fair bit of work with our esteemed collaborators, the only way we can do it. We can't do it by ourselves. I think we're just getting started. We're just laid framework to allow us to move forward. We are building templates and reference data sets, which would allow other people to work with. So we can give you all the data and all the information about it. So that, okay, good. I'm finishing. Okay. Honest, just one slide to go. So we're providing templates and reference data sets, which would allow anyone who wants to compile their data and try and navigate within these templates. And we are intending to go seriously into the problem of mapping out mineral system from known into the unknown as far as the time and money can allow us. And I want to acknowledge in the end my esteemed team in GSQ. So there are a whole 8 of us, including the administrator who spends most of the time ticking off timesheets and approving everything. I'm not complaining, it's all good, it's all good. Collaborators who are doing lots of work, which is highly specialized, that's greatly appreciated, but we need much more. So it's a call out for whoever wants to play in this place. And a particular thank you, and again, forward-looking thank you to the companies. We need access to lots of well-characterized samples within your properties. So if you hear from somebody like Courtney, or just spare the thought for somebody like Courtney or anybody else of us, if you're thinking about throwing away some of those 50 drill cores which are not used to you, just give us a call so that we can salvage something and at least to keep it for posterity. Okay, I shall leave it at that. Thank you.
Thanks, Vlad. Do we have any questions in the room? Oh, you've scared them. Johan has a question. I'm coming. Meet me halfway.
Thanks, Vlad. I think that's an extraordinary compilation, very useful. But I think you pointed to you had a very good point there when you said that it's important the direction you are looking in, because fluid flow usually follows even foliation planes or some kind of pre-existing structure. So if you look across structures, you're not going to see the signal. But if you look along the same structure, this is probably a question that's been asked many times. Why is the deposit where it is if the fluid that carried the goods travel all along that structure? So why we don't have a series of deposits like Ernest Henry? If you look along the same structure, you have Ernest Henry sitting there, and the next one, E1, it's kind of folding. So it almost looks like the fluid may have taken a turn there. Or is it different fluids or different processes that operate?
I think a conceptual answer is very simple. Practical is extremely difficult. Conceptual answer is very simple. Fluids are just fluids. They just flow by the law of physics. And they don't care about their origin. They don't care about the nature of sources, pathways, and any mineral system components. They're just behaving just like normal fluids, following by the laws of physics. And you're forming deposits in the places where you have the largest fluxes of mineralizing fluids and the largest reasons for the fluids to destabilize and drop out the metal. So that's a very simple answer. The very complex part of it is to explain why exactly there. You need much more information, which is almost never available before the fact. So PhD students can, and explorers, if they care, I don't think they mostly do, but a PhD student can figure out everything exactly why there, but you only have this information after the fact. So before the fact, frankly, honestly, with all due respect to people who admire machine learning, deep learning, and other cool things, in many respects, the specific location of a specific deposit of a few hundred meters in size, you can consider it to be totally random because you don't have enough information to predict it.
Okay, how are we going
Good.
for time? More questions? No.
Good.
Evan says no more questions.
Good. Cheers. I'm free.
Thanks,
I'm off the hook.
Vlad. Now we're going to hand over to Kate Wathen-Dunn, who is one of the senior data scientists within the GSQ, and she's going to talk to us about some signatures of mineral systems in the eastern Mount Isa province.
Thank you. Man, short people, right? Can you hear me? Is that all right? So I'm going to talk about the same project that Vlad just spoke about, but I'm going to come at it from a different perspective. So we've taken a machine learning approach to this, and there's some things we've learned along the way, and I just want to share that with you in case you guys want to take on those kind of learnings for yourself in your own work. Okay, so the outlines is what I'm going to talk about. So as Vlad did, I'm going to go over some of the project goals, where we started in the beginning, why machine learning is not a magic solution, and what you can do. Louder? Is that what you're saying, Joe? I'm too short. There we go. What you can do to make machine learning successful. The work that went into that Vlad had just explained on how to create a suitable data set for machine learning kind of work. Some of the testing that we did, well, Morgan and Cyro did, some of the methods that they used, and then the pipeline that we've made and we're going to make available for you. So project timeline. So this started, it's kind of built over the years. So it started in 2016 with a Cloncurry Uncover project. It's gone onto the middle database that Vlad just explained. Publications on that. This latest project with the data analytics, and then there's some present and some future work. So some of the work that we've done is making this into a pipeline that people can access, and then some future work for us to do on this as well. So some of the goals, develop a pipeline, try some of these techniques, make sure that machine learning actually works in these kind of contexts. As Vlad explained, see if we can identify the signature of these mineral systems and find the key features in these data sets that drive these models. So, you know, what can we learn from this? And then, of course, to make these pipelines available for people to use in their own work. Bit of tongue in cheek with the push the button analytics, but that's kind of what we're going for here. That's what we're trying to do. Make it easy. All right, so the starting point. Historically, all kinds of surveys for all kinds of reasons, all over the place, different kinds of data collection, data formats, data types, resolution and precisions, all over the place, unrelated data. So people have tried to collect all this stuff together and feed it through machine learning. And it's kind of given the whole thing a bad rap because it doesn't work when you do it like that. Also, the importance of interpretation in geology. You know, if you have the same results and you give it to a handful of geologists, you get a handful of results. That's important. That's the way the work is done. So if you're comparing apples with oranges, it doesn't really work. If it's only apples and oranges, you can probably kind of fudge it and make it work. But the kind of data sets that we had to begin with was more like a basket of fruit, all kinds of things. And then if I torture that fruit metaphor a little bit more, if you give a machine learning algorithm the kind of variability that's in that fruit basket, it's really difficult. So it can't figure out, if you ask it what a fruit is, and it's got a fruit basket like that, it can't go on shape, it can't go on texture or seeds even, because some of them will be seedless. It might decide maybe that the amount of water in all of those things, if it's over a certain amount, that makes it a fruit, but then that would also classify a jellyfish as a fruit. So these kind of approaches don't work with data sets like that. So algorithms are very clever, but they're also very, very dumb. And I've grabbed some blog articles and things off the internet to support that. So computers will always do literally exactly what you tell them, good or bad. Google itself is smart but dumb. And this is my favorite. Skynet isn't coming for you, but Excel might be. All right, so I've just told you machine learning is not a magic solution. So what can you do about it? What does it need? So it really does work best on really large data sets. You need to give it lots of information to try and sift through and find those patterns. It requires a lot of expertise. So you need to have someone who knows about how to choose the right methods, how to transform and scale the data, how to normalize it. Algorithms are really lazy. If it finds a path through and finds a pattern, it'll just go with it. It doesn't care whether it's right or wrong. Like I said, with the water example and the fruit basket, that's an answer. It's not the right answer, but the machine will just run with it. So you need to be careful to prevent these kind of shortcuts. And of course, interpreting the outcome of these machine learning results is a little bit tricky as well. And there are some mixed results when you try to apply these models that you've trained to new data sets. So there's some expertise involved in that too. So what can you do to make your machine learning projects a success? The biggest tip, and I'm going to follow on from Vance here yesterday, is standardized data. It really is. Same. So same data types and formats, same features collected, same analyses done, same batches, methods, all those things. If you feed it a big bunch of the same things, it gives it a lot more information to work with and a lot more context. You need to have good controls and well-designed experiments. You can't just give it a whole heap of crap and expect it to find the answer. It doesn't work. You need to have a large number of samples, like I said, for it to sort through. And you need to have people who know how to run these things that make it work as well. So this is for Michael. After yesterday, I couldn't resist. I've just told you how dumb they are, so now I've got to build them back up again, right? So now they look a bit smart. So the data set that Vlad was telling you about, it's built on the Cloncurry Uncover project and now the metal database. And it's a really great data set for machine learning because it has thousands of samples. They're from set deposits. And each sample, this is the crucial part, each sample is analyzed by the exact same 9 methods in the same way. And that gives machine learning algorithms a lot to work with. So this is the best, like Vlad said, the best machine learning data set that we have. So again, these are all the methods that it was done with, 9 different methods on the side there, the ways that it was done, all the kinds of data that we have. and we've made it into a pipeline. So these are all the greatest hits. It's done supervised and unsupervised. It's done clustering, regression, classification, dimension reduction. There's all the k-means and the dB scans and the random forests and all those things. These are all options in the pipeline, right? So I'll explain a bit later, but we've made that pipeline into an app that we can access and use. And there's bits you can choose in there, and the normalization and the dimension reduction has been set. We've gone through a whole heap of options, and this is the one that worked best with this data set. So that's set, but the other things you can shop and change and choose and play with. So how are we going to make that accessible? So it's written in Python. So we've got a couple of options. It's open source libraries, it's accessible. We could incorporate that into existing analytical software. That's an option. You know, maybe a subscription or a cost to it, but it's a familiar way of working with this kind of data. Something we've done in-house is build a web-based app with a Streamlit. So that's free for anyone with an internet connection. It's not currently published online, but that's something that we're working with CSIRO on. This is an example of what it looks like. I'll just, no, I can't. So this is the demo one we have in-house. It's like I said, it's not online yet, but you can choose the pipeline that you want to do. You can choose the type, like classification or regression or whatever. And then there's up the top there with that red button with the thing on it, that's the push button analytics. So at the moment, it's on the reference data set, and there's some work to do to make it accessible for people. So we're not here to tell you how to suck eggs, right? Data science is not going to do that. There's a lot of work involved in, you know, you get the result, but what does it mean? What is the answer? So you have to do all that yourself still. That's all still a critical part of the system. It's really just a tool to help you with decision making. So some of the future work. So as Vlad said as well, one of the things that the project aimed for is to find out of all these 9 data types here, which ones are the best? What do you need to collect? What contributes the most to the models? So if you as a company had to choose, if you had only, you know, a set amount of money or whatever, which is quite reasonable, what data set do you collect that will give you the best results? So that's something that we still need to nail down. How do you compare data you already have? So say you already have some of the data sets of your own that are in these similar formats. How do you compare that with the reference data set that we've got? So we need to add in abilities for people to upload their own data sets and compare to our reference data set and these mineral signatures that they found. And then we need to make the pipeline available. So whether that goes into commercial software, whether it is our Streamlit app that gets published online, we've still got some work to do on that. So in summary, it's a demonstration that machine learning can work if you have a suitable data set. You need the standardized data, you need things the same. We've developed an analytical pipeline. You still need to do your own interpretation. We're not going to do that for you. We're not going to tell you what the answer is. And there's some future work to make this useful for industry. So the paper that's based on is available in our open data portal. It's report 131958 if you wanted to look it up, or you can go to the CSIRO website and find the paper itself. And this is the team here. So there's Morgan and Tobias and Jim and Neil from CSIRO and David from GSQ worked on this. So, and there's the paper information there as well if you wanted to go and have a read of it yourself. But that's it. Thank you very much.
Thanks, Kate. Any questions for Kate? Yes.
So one of the important things in machine learning is training your models. Is that app you're developing going to give you all the training statistics to review before you do any of the classification or regression steps?
It doesn't at the moment, but that's maybe something that we can work on. It's kind of literally a push button thing. It's for people to explore the data and find these signatures. It's not meant for professional analytics in that way, I guess.
Okay.
But that's an option.
Thanks, Ariane. Anybody else? Are there any questions online? Nope. Okay, thanks, Kate. You are free. Oh, yes, Chris. Chris is up next. Chris Ingles from ANU. He's going to talk to us about inferring ore deposit types and redox conditions from sphalerite. Here you go.
Oh, great. If you want. I don't have a pocket.
Somewhere.
It's really short, so
Yeah,
broad.
that's one. Brains laser, forward and back of the slides.
Okay, wish me luck.
Cool.
Thank you. Hello. How's that? Oh, hello. Testing. Is that the right? I can go. G'day everyone. I'm Chris. Chris Ingles. I'm from ANU. Doing my first year of my PhD on sphalerites. I've been working on it for a few years now, and I'm going to walk you through why it's basically the mineral that we want to look at for the future, or one of. So determining ore types and inferring redox conditions. First off, we've got a few formalities. So I want to say thanks to the GSQ team, obviously. Helen in particular is part of the funding. Vlad for his thoughts. Courtney, I can't see, but she's been sending me sphalerite samples, as well as anyone else in this room. A lot of you might know Mab, Dr. John Mab Reginas. He's my supervisor. He is everything about critical metals down at ANU, and anyone who has sphalerite, send it on to him, because he'll get it to myself and we'll go. So part of this presentation, just quickly, I'm going to throw in a whole heap of sphalerite pictures, because it comes in every color, every shape, basically every location, every ore deposit. If it's a simple sulfide, so we're going to find it in every deposit, and that one's from Porgera, Papua New Guinea. So I don't like to lose people straight off the bat. So I'm going to start with a periodic table, because I know a lot of us here are geochems, but a lot of us are geophys, and I don't want to lose anyone. So sphalerite is, of course, half zinc and half sulfur. We take the zinc cation with the sulfur anion. Now, with the sulfur, we can just, as a sulfide, that's a reduced form, we can leave the sulfur out. But the zinc is often replaced with an iron or a cadmium. So this is in the major to the minor concentrations. We've got the trace elements that it often contains as well, a whole heap there. And we also get a few inclusions of other elements, which I've included in orange. And that's basically the suite of elements that we can find in sphalerite. But important for this conference is the critical metals. So we'll see manganese, cobalt, nickel, zinc, gallium, germanium, arsenic, cadmium, indium, tin, antimony, and even a hint of bismuth in there as well. And that's all retrieved from sphalerite. So if we're looking at critical metals and we're looking towards the future, and we know that sphalerite's found in almost all the reduced sulfide deposits, we can certainly see we're going to need to keep mining sphalerite for a long time ahead. So analyzing sphalerite, this is more of a how do we do it, or what do we do and how do we do it. This one's from ISA, this is from ISA sphalerite. So compare that to the Porgera stuff. It's a completely different color, completely different shape. What we like to do, and I'm going to try and sort of slow this down. I've got a laser here. Yep. Okay. Well, we start with what's called a laser traverse. So we're ablating the sphalerite via a laser, and we put another machine hooked up to it, and it measures down to the ppm level across the sample. What are the concentrations of basically the periodic table that I showed you before? So if you see here, we start here. I think I heard it called a destructive technique yesterday. So it is destroying part of the sphalerite. It runs straight through. And what we're looking at between A and B, they're actually the same image. That's the same sphalerite, except we're looking at one under cross-polared and one under transmitted lights, and C slightly further down on the same sample. And D, E, and F are the same sphalerite again. These are all from Porgera. But you can see under backscattered SEM imaging, so I'm not sure, again, who's part of the geochem crowd, but if you're working under SEM, you can get a lot of information, including cleavage shapes, but under backscattered, cross-polared, and the transmitted, you can see there's a lot of different information that can be revealed. So anyone out there that is playing with sphalerite, I'd recommend firstly traverses instead of spots, because you don't know where you're going to get, and then look under a whole heap of different lights, and the amount of information you can find, you don't know what you'll see. Similarly with G and H are the same sphalerites, right through the clear, it's all sphalerite. Every one of these bands, at no point does it stop. The only part there is a little bit of pyrite. So substitutions are basically the game with sphalerite. Here's one from the Bluebush deposit in Queensland. Again, it's not far away from, well, we're still in Queensland, but the shape and the color is completely different again. And here's an idea. So this is a paper we put out last year. If you compare the iron concentrations in the manganese by the laser, as we go across from A to B, here's our traverse, you can see the sphalerite is changing color, but we can also see the iron concentrations drop, and they're dropping right in line with the manganese. Cadmium, meanwhile, is going up, and cobalt it's bouncing along in its own little fields as well. And similarly with the copper and the silver, we can see a similar trend throughout it, and this is relatively common, especially these porous sphalerites, that copper and silver can work together, and antimony is sort of following along. So what I sort of do, each metal that I'm showing you on the periodic table has its own characters. It has its own personalities. It's actually quite interesting how every single metal on there, every element, has its own traits. And it's even more interesting how most of them seem to work together under certain circumstances. So under certain pH, under certain temperature, under certain pressure, under certain redox conditions, different elements are forming different correlations and coming together. And in the literature, what we like to do is try to explain it with these substitutions. So we take a zinc, which is just a simple zinc divalent 2+, and we can get similar sized metals like iron and manganese, and we can, because they're working together, we can also see that they're working. We can put them in a bunch of brackets. And this is just a nice simple way that we can explain how do we find cobalt in sphalerite? Why do we find cadmium in sphalerite? And because these are traditionally 2s, we can then, well, we can work with the redox situations. It gets a little more complicated when we start coupling them all together. We get a pair, so a copper and a silver, and we can pair that with a trivalent antimony. And that explains sort of the patterns we see along as we go. And this has basically become sort of the game as we run the traverses. So here's one that's thallium in blue and arsenic in yellow, which might be the most toxic combination any of us will see. Thallium is toxic, it's fatal to the touch when it's pure, so that is quite the metal. But here it is in arsenic, and I haven't explained this one yet. This is one I found, but they're clearly following each other, and who knows why. So I just threw one in from Isa because we're in Queensland. What we can see is silver across the top in green, antimony in blue, and thallium again in red. And you can see they follow very similar trends in the sphalerite. So if you were in Mount Isa chasing, say, silver or antimony or thallium, don't know why, but you'd look for the higher concentrations of one and you'd find the higher concentrations of all three. And that's where it starts to get a little handy, is that once we find out which elements you're looking for, which elements it correlates with, then we can find out, well, next slide. For example, of course, all sphalerites not one simple trend. Most of them seem to contain different phases. A little more this way. So if I bump this here, we can actually see there's different sections involved just in this sphalerite alone. Now, the yellow is cadmium. So where cadmium's highest, we can see basically everything else disappear. So we've got lead, gallium, and antimony down here. So gallium's around 100 ppm. So anyone who's chasing gallium, you'd look for the lower cadmium sphalerite, and you know you're going to find your gallium. But if you look for the higher cadmium stuff, you're not going to find anything at all. And this is part of why if we can keep scanning sphalerite, we'll get an idea of just where the elements are localizing within the ore and within the mineral. Here's another quick one. So copper and tin, which are two metals that we've all been looking at, talking about this conference, for a lot of sphalerite, or not a lot, I guess a few, they follow each other together. So that's copper and tin, 1-to-1 basically correlation. So when copper is going into the lattice, so is tin. And what we're hoping to do is find enough sphalerites that we can compare them all from all the different deposits and then say, well, isn't it interesting that when the temperature is 350 degrees, copper and tin are best friends and there's a heap of gallium there. But when the pressure or when the redox conditions change, which is we're signifying an oxidation state change with the, we believe so, we can know we're not going to find gallium over here. And that's why we're hoping to build a whole heap of sphalerite so we can work out exactly what's containing what. And that's what led us to the sphalerite database. And a quick shout out again to Helen, who came up with the phrase database, because it's exactly what it is. I've just been compiling them into a system, but that's a nice phrase. And there's another one from Blue Bush again. All these are sphalerites, and they all contain different trace elements, different metals, different colors. I'd call it a versatile mineral. So here's the fun part. We've got 38 different sphalerite ore deposits that we've been compiling for the last year. We've actually a lot more, but some of them weren't sphalerite. It is a tricky mineral to identify. And we've got a few more just before I go. This is in, I think I saw it in preparation for publications, the correct phrase, meaning it's not far away. But we're also going to add, so we've got Tsumeb, we've got a few Irish deposits, a few more from Peru, and we're going to pump in, I think we've got Century, Balgammon, and Mount Garnet that we're going to add. Of these, we've got the Isabel deposit, there's an Isa, a Blue Bush. I'll actually go through most of them, and the Hilton. So if you graph it all, that's a pretty graph you get. That's 40,000 iron versus cadmium points. Now, what I've chose was iron and cadmium, and I can assure you I've graphed them 1,000 different ways. But if we do compare these two specifically, I'll go through this and we'll get a better idea. So MVTs, I'm not sure how specific everybody is on their ore deposits, but MVTs in America, we have what's called the tri-state deposit. It's the 3 states in America that are all aligned. And we've got Kansas, Joplin, Missouri, and Oklahoma. And if you put them all on the same chart, you can start to see they sort of distinguish together apart, and we can possibly get an idea of fluid migration throughout the area. And just quickly, if you flick the axes on this one, it actually lines up geographically with the 3 states on the map. So look out, there might be something going on there. But if we add more, we've got Vstok, another MVT deposit. We've got Pomazani, that one's in Poland, another MVT deposit. And we've got another German deposit down the bottom. And this is our 6 MVTs, and they all plot relatively in the same field. Key being, oh, wrong button. Key being that the 2,500 on the iron here. So if we squeeze that along a little, we can get a better idea. They're taking up their own little left-hand side. If we squeeze them along even further to now 150,000, we get this left-hand corner here. Now keep that in mind, because this is where it gets real interesting. The sphalerite comparison from some of these Queensland deposits, which is obviously why we're here. So Isa, Hilton, and Bluebush on the same chart, remembering that the MVTs were all in this left-hand field, we can plot the Mount Isa sphalerites, the Hilton and the Bluebush, and this is many traverses from several different depths. This is not just, sorry about that. If we zoom in slightly, again, you'll see they're all very localized in that area. And for another comparison, we can throw in Balmat, which is a similarly SEDEX style deposit from New York State in America. I believe I'm supposed to call them traditionally known as SEDEX deposits. We'll go through the debate for another day. And where it gets even further interesting is if we compare a VMS deposit such as Schreiber with our SEDEX style deposits. Now, SEDEX is, of course, the sedimentary hosted and exhalatives, and the VMS are volcanic hosted, but yet we're seeing them plot in the same area. Now, this suggests that the host rock is not influencing, say, the iron or the cadmium, because we've got sedimentary and volcanic rocks, but they are plotting the same field. And remember, MVT's sitting over here on the left. So let's just see where this goes. Let's add in some Broken Hill type, because Broken Hill is its own thing. If you'll see it starts stretching up from the top here. So we're again looking at our Queensland SEDEX styles, our VMS, and New York, and now our Broken Hills. We've got 2 different kinds of Broken Hill, a secondary deposit, and they both start plotting upwards and onwards. We get to Cannington next, which I am not a huge expert on the Cannington deposit, but Mab, my supervisor, has done a lot of work on it. And from what I've picked up, and I'm sure a lot of people in this room are the people that discuss this actual issue, but it seems to be often compared between, Cannington's often compared, is it a SEDEX style? Is it a Broken Hill type? Is it something of its own sort? And honestly, I think that's why I've been sent here, is to show all you guys that it seems to plot slightly different. It doesn't align with the traditionally SEDEX. It doesn't align quite with the Broken Hill, but there is something, it's very close. What it does align with is the Quad-Aline deposit in Idaho in America, which is a 650-degree temperature Celsius metamorphosed deposit. And they haven't clarified as much information as we'd like from Quad-Aline, but it does amazingly overlap with Cannington, and they're around the same temperature. Now, if we continue, I've got a couple of pegmatites we pulled from Ravensthorpe and Londonderry, and they're also bringing in their own trends. So where we're at the moment is we like to think if we draw a straight line through there, we can simplify into the higher temperature deposits and the lower temperature deposits. And why that's exciting is because we can now take, say, what we're hoping, a sphalerite sample, and potentially judge the temperature on it based on the iron and the cadmium. Now, a lot of work has been done on that, especially in the 60s, the 70s, the 80s. They even took it on to meteorites. There is parts where it doesn't work, but they've never included cadmium in their calculations. So it's always been an iron-based system. They did try with cobalt. So we think we're onto something here, and well, in preparation. Now it gets slightly even better because I've got 6 epithermal deposits. Epithermals, again, different from the MVTs. So if we plot one MVT, 1 epithermal, 2 epithermal, 3, 4, 5, 6. Now again, this is the same scale. Our SEDXs were down here, our Broken Hill, our pegmatites, our Cannington, and our MVTs down here. And the epithermals all plot on the left. Now, Joplin was our furthest right side of our MVTs. I can bump that one more time. So this is the furthest right of all our MVTs. And this is all the epithermals that we've measured. Again, there were 40,000 points that went into the original graph here. And pull it all back, we can now see MVT tri-state, MVT others, which seem to be mostly reduced iron, higher concentrations of cadmium, and that seems to be the key there. Gemma's in the audience, I know you're doing something similar. The epithermals, and we've also got the Isabel deposit from, I believe, Herberton, that field, from Canberra. Yeah, -5 last night down there. Glad to be here, hence the shorts. But if we continue to draw a line, we believe that we're looking at a temperature line of around 4,000 ppm of cadmium, which is defining the temperature, because we've got Broken Hill here on the right, we've got Cannington and Queensland, and some pegmatites as well. And there's something going on here, but I'm yet to clarify it. And last thing I'd point out is that around the 1-to-1 ratio, which would be 1 cadmium for 1 iron, it appears to be either, this is clear, this was barren, clear sphalerite. There seems to be something going on when it switches between a preference for iron or its preference for cadmium. So to sum it all up, we're hoping sphalerite can reveal some redox conditions. With one sphalerite sample, we're hoping we can tell the oxidation state on the metals. And if we tell the oxidation state on the metals, we can tell what it's pairing with. If you're chasing this metal, then find out what it likes to pair with. How does it get in the sphalerite? If you could be working with an epithermal, an MVT, you could be working with who knows what deposit, but if you can run a quick scan or get the sphalerite to me and I'll run the scan, I can tell you where it's going to plot. Or type indicator, which I know a lot of us are looking into at the moment, especially trying to clarify, because ideally you could run your scan, you've found field geos out there, you found one piece of sphalerite, we're hoping you measure it or I measure it, and you could you could just reveal, there's a SEDX style deposit right below you. It could be that simple, just one sphalerite sample to go, we're sitting on an MVT deposit. Not that we're there yet, but I think we're getting really close, and hence why we're also looking at this public database. If I can get it all online, and that is the plan, then you guys can log on, enter your sphalerite details and go, how does that compare to the rest of the world? And that's basically the plan. And actually on that, NASA is sending us sphalerite from space. We've got several meteorites. They've found sphalerite on the moon. They've found sphalerite everywhere. It's accessible. It's a simple sulfide. So within the next month, the sphal's on its way. We'll have extraterrestrial sphalerite, and we'll know how does that compare. Where's it going to plot? I'm equally as keen. So watch this space. Pun intended. More sphalerite, more data. Everyone in this room, if you've got sphalerite, send it to me, send it to Courtney, send it to GSQ, send it to anyone, or send me your measurements. I don't really mind. I just think we're onto something here, and I think we'll find out, at the very least, fluid migrations we track across Queensland, across deposits, across everywhere. And that's where I'll call it. Thank you.
Thanks, Chris. Can't wait for some space sphalerite.
All right, extraterrestrial.
Questions already up the back.
Yeah, super interesting talk.
Thanks,
obviously, you're from the experimental petrology group at ANU.
Yeah, that's it.
So have you experimentally synthesized sphalerite to look at this temperature and cadmium effect?
Thank you for the question, firstly. The first 3 I tried, actually, I'm in the experimental petrology group. I'm not sure if I mentioned that. First 3 I tried blew up. They just exploded in the furnace. It is not as easy to make as I'd like it to be, and we're now looking into some really complicated systems. But what started all this, because it's only sort of coming to the end of my first year, well, I'm hoping to get some constraints, try to work out from the real world sphalerite, what I'm suggesting 650 degrees at the moment for temperature would release about 4,000 or 5,000 ppm of cadmium and iron. So I want to know what can I do and what temperature, and the next year will be exactly that. Work out the constraints. What does the real world sphalerite look like? And then, yeah, we're going to start blowing up more furnaces until we get it right. That is the plan. Thanks for the question, though.
We got a couple of questions online. Is there anyone more in the, oh, look.
Throw them at me, guys. I love this. Also, I can put my email up. It's chris.ingles@anu.edu.au. Like, send me some questions. G'day, mate.
Hello. Thank you, Chris. Yeah, I really enjoyed that talk. I just had a question. So you had your cadmium iron plots up there as sort of a temperature differentiator. I was just wondering, yeah. So I was wondering if you had looked as well at elemental ratios like zinc and cadmium in particular, which is also, or has also been used in sphalerites as a way to differentiate temperature regimes.
Yeah, absolutely right. That is to the traditional use. So zinc over cadmium, zinc over sulfur, zinc over iron. But I noticed it's generally the iron is the major cation that takes over the zinc. So I started looking at zincs over sulfurs and zincs over irons and zincs over cadmiums, and they did all plot nice and neatly. Most of these styles in this graph, I could readjust the way you said it. And I did do it up for publication. It does plot them all linearly and slightly apart. It does look good, but it just didn't look this good. But yep, wait until I finish this manuscript or it's published. And I reckon I might even try this. I'll put it in the appendix. How about that? And that way you can skip, someone can have a look at it. But thanks for that question. Really interesting.
Thanks, Chris. Really interesting talk.
Thanks.
Have you done a comparison of this sphalerite, sort of chemistry against the background chemistry? Because it's really very sort of, deposit specific, for this chemical distribution.
Sorry, I just missed the end of that, the back half of that question. Have I compared it to?
The background chemistry
The background.
of the sort of, the chemical system, in that, the whole rock chemistry being.
Whole rock, I'm not a huge fan of, but my supervisor is. And where it gets interesting is, yeah, where is all the minerals being hosted? Are they in the sphalerite and are they in the accessory minerals? And what I like is that we're comparing accessory minerals from that are formed with the sphalerite. So I think yes, because it comes down to partitioning. So in the lead zinc deposits, are the elements partitioning directly into the sphalerite? And I believe definitely. That's yes. I think they're choosing sphalerite, but only under certain conditions. And if we can work that out, that's my next goal. And I've started a list. It's just comparing each one. For each accessory mineral gets a long list. But yeah, I really think there is something in that, because especially the more buffers. They use iron minerals as buffers. We've got a hexagonal pyrrhotite. So if sphalerite forms with a hexagonal pyrrhotite, then they've worked out that will control temperature. It'll buffer the iron concentration, it'll buffer the cobalt. But then I'm not 100% sold on it yet, but I am looking into it, yes. It's a great question, thank you.
Thank you, Chris.
Thank you.
Do you have any thoughts on what would happen to, say, one of these lower temperature deposits if you metamorphosed and deformed it? What would happen to the sphalerite chemistry?
That's a great question. I have my thoughts, but I believe they're a little controversial at the moment and we're yet to solidify them. Now, if I looked here, low temperature deposits or deposits themselves, I'm a great geochemist and my supervisor is much better at the ore deposits. But what I would say is SEDEX style deposits are very low temperature and Cannington is a higher temperature. And I have heard theories of basically melting a SEDEX deposit, Broken Hill's slightly higher as well. So there might be something to it. There might be something to melting, raising of the temperature, and then I do think it will increase. I will say that the higher the temperature it goes, the plainer the sphalerite gets. So the less characteristic it has. I'm not sure why yet. I'm guessing it's re-equilibrium. But the higher the temperature we go, the less we're getting from it, but the higher it plots on that graph. Does that sort of help? I sort of drifted around there.
Chris, sorry, you're getting lots of questions here.
You're right.
I'd love to get Wolford Creek, not that I'm associated with Wolford Creek now, but just in regard to Wolford Creek, one interesting thing that we noted was that you have a much higher iron-rich sphalerite sitting with the pyrite zone, but in the carbonate zone, you have this light, very honey-coloured sphalerite. It'd be very interesting to kind of see the difference between those two types of sphalerites, which are observably different when you're logging core.
Absolutely. And there was a good example, West Fork MVT. It has a red sphalerite and a bright yellow sphalerite. It seems that the red one was a replacement sphalerite, so it's actually come in at a second later date. And actually that's, most of this here is, I began these deposits looking for stereotype deposits, really defined deposits. What is a typical MBT? What's a typical SEDEX? There is a lot of ore deposits, especially the 38 that I had. A lot of them aren't textbook definitions, and there seems to be something at play between alteration. So I believe this during primary deposition we can get this graph, but I'm working on another one for later alteration, and I think we can. It'd be a matter of plotting where does it start. And then where does it evolve to? So I think we'd start with your one sphalerite and then work out how does it evolve to the other. Do they all plot together? Is this later alteration still considered the same deposit type? These are all the questions I'm definitely considering and arguing. And I really do appreciate the question too. Send me some of the sphaler, we'll find out would be the better answer.
We'll give him some. Yep.
Awesome.
Some Wolford Creek stuff. Okay, we've got a couple of questions online.
Oh.
And I'm going to do those. And then if anybody else has questions for Chris, it will be morning tea soon after a couple more talks, and you can.
I'm here all day.
With you. Yeah, you're not allowed to run away now.
Yeah.
Far out. Okay.
Sphalerite for the win.
Apparently, sphalerite did. Look, apparently we've lost everyone's names online again. We're all back to Prue Osborne, but so Prue would like to know: have you looked at Rosebery in Tasmania? It has two types of sphalerite, honey-coloured low iron and dark high iron in one deposit. So I think that's a similar question.
Yeah, I have Rosebery sphalerite, but we haven't measured it at the moment.
Okay. So
if I actually recall, I think the first one we checked didn't turn out to be sphalerite.
All right.
Yeah, there was one of them which did, and the other one was something, I think it was an iron sulfate. Okay. So it does get a little complicated, but I will look into that. Prue or non-Prue?
Yep, Prue or non-Prue.
And if you could send me some, if you've got that, then keep them coming, guys.
Another Prue.
Another Prue.
Another Prue is asked, do you expect substitution of zinc in sphalerite by trace elements, including indium, more efficient in wurtzite hexagonal crystal system, or in zinc blend cubic crystal system, taking into account ionic sizes, pressure, temperature, and fluid composition?
It's a beautiful question. That is my life. And yes, I'd expect it, yeah, unfortunately, I'd expect it in the tetrahedral face-centered cubic coordination, not the wurtzite form, because indium, trivalent indium is the exact, or it's the right size. It's within Goldschmidt rules. Yeah, I definitely expect it in sphalerite and in solid solution. And if I'm self-plugging, there's a paper we released last year where I pitched indium, trivalent indium is actually in a solid solution with trivalent antimony, trivalent, basically everything of a similar size. So yeah, I love the question. Sphalerite's the answer, and check out the paper.
Check out the paper. Okay, I can put it in the chat if you send it to me.
Yeah, why not? I'll do that.
Online one. All right. Great. Thank you. No more questions for Chris.
Okay, thank you guys. Thanks, Evan. Thanks. Oh, yeah, of course.
Can we please have Brandon Mahan to the table, to the podium?
Well done.
All right, thanks, Chris. Really appreciate that. Brandon, you've got big shoes to fill here. Give us the wow. All right, Brandon, JCU, we've been working with him on copper isotopes in mineral exploration and ore deposit characterization. He's got his microphone sorted out. He's going to take it away.
All right, is everything good with the mic?
Everything's good with the mic.
Awesome. All right. Well, thank you very much for the introduction, Helen. So today I'll be talking about hydrogeochemical ore exploration, specifically using metal isotopes and even taking that a layer deeper, looking mainly at copper isotopes and sort of taking the opportunity because oftentimes I think harmonizing efforts between, academia and industry and government comes down to basically closing that knowledge gap. So I'll be doing a little bit of that here today, and then going through some stuff that we've done up to date and going a bit light on the where can the future take us, in that I hope implicitly by the end of this, everyone will agree that we've sort of built a pretty good foundation in at least validating this technique. And now we can sort of move into the stage where we can really build the foundation of it and potentially start truly deploying it. All right, so I always like to do last things first with acknowledgements. Otherwise, I get wound up and run out of time and I forget to thank people. So without further ado, I'd just like to thank basically everyone within JCU and especially our Economic Geology Research Center, many of which are here today. So I believe Paul and Johan and Kayleen are in the room. Alex McCoy-West, who has been pretty integral to the development and expansion of our isotropics geochemistry lab, which I'll touch on later as well. And then of course, GSQ especially, who have been intensely supportive of this adventure of trying to develop novel exploration tools based on metal isotopes in groundwater, and again, specifically copper. And then there is a number of other people on here, but just for the sake of time, I won't run through the rest of them, except I should make a nod to Ryan Mather. So this is the person who basically first recognized the utility of looking at metal isotopes actually as a vectoring tool, and we've been working very closely with him. Okay, so I always like to give a bit of an orientation on the way the talk's going to run. So here we find ourselves in the introduction, of course. After that, we're going to basically demystify, I hope anyway, stable isotope geochemistry for everyone. And then we'll look at basically what I like to call green exploration for tomorrow's critical metal. Everyone can guess what that is at this point already. And then we'll talk a little bit about goings on at JCU and the developments that we're trying to create to basically have an analytical hub for people both in government and industry to be able to perform this sort of work. All right, so quick recap, elements and isotopes, what's what. This is just as much for me as anyone else, because even though this is my career, I still mix up protons and all that sort of stuff at times. So elements defined by their atomic number, so proton number, they are basically being defined by their chemical behavior, which is governed by the electrons that are in their outer shell. So same for elements, protons and electrons. Isotopes, different story. Atoms of the same element, differing number of neutrons, some decay. Pretty much everyone in here probably is familiar with geochronology, so that's looking at radiogenic isotope systems. Not at all what we're looking at right now. So we are actually talking about sort of the other flavor of that, which is stable isotopes and stable isotope fractionation. And that generally is occurring because of either a physical and or chemical process. All right, so I like to basically define what isotope fractionation is using a fruit metaphor. Thank you very much to Kate in the room for already sort of laying the foundation for that. So isotope fractionation is basically just when a process causes the proportions of an element's isotopes to change. So we have a couple different varieties of that, one being kinetic isotope fractionation, which is basically just reproportioning isotopes because lighter isotopes travel faster and their bonds break easier. Equilibrium isotope fractionation is going to reproportion isotopes because heavier isotopes slow down bond vibrations, and that makes the universe happy. Our universe is always trying to find itself in its most restful state, just like most of us most of the time. And so that is why you're going to preferentially concentrate heavy isotopes in stronger bonds. So the end all of that is when we look at our isotope ratio. So when you have a relative increase relative to basically a baseline state or a previous state, when your ratio increases, say of your heavier isotope to your lighter isotope, we would call that, say, a positive isotope excursion. I'll run back my little apples to apples comparison over here. So basically you're at the shops, same amount of Red Delicious and Pink Lady apples. If you live in a place where people have basically good taste in apples, as you move throughout the day, you start out with the same amount of both. You end up with more Pink Ladies gone because people took them and more Red Delicious left. So you have a positive isotope excursion or a positive excursion in your Red Delicious versus Pink Ladies. Okay, so taking a bit of a deep dive into what we're actually doing in the lab and with instrumentation. So basically everyone here would be familiar at this point with ICP-MS analyses. So people have talked about the virtues of this, and they are amazing instruments. They are basically taking, your pulp after a 4-acid digest or whatever, or your water samples, turning that into an ion beam by from some science magic. And then basically that is going through an electrostatic field that is going to isolate only the ions of a specific mass, and then that hits a detector. The more of that hits the detector, the higher your signal, and that is proportional to concentration. Basically how that works. So what we are doing and basically talking about today is quite fundamentally different. So you can see that this apparatus here or instrument seems quite a bit more complicated, and there's more text flowing on the screen. Basically, same idea at the front end of that. So you're introducing your sample, but the big difference here is we have this giant high-powered electromagnet in there that is basically taking that ion beam and splitting it basically the way that a prism would split rays of light, such that your higher mass stuff is going to be bent less and come out on your array of collectors here. And that is because basically it has more momentum, it's heavier. And that is actually how we determine the relative abundances of isotopes all at the same time. That allows us to get much higher precision, which is why we use these multi-collectors. The bugaboo that we really have is only popping up here at the end. So you'll see there we have 54 chromium and 54 iron. Basically what that is telling you is that these mass spectrometers are really only differentiating things based on their mass. They cannot tell you at all the difference between one element and another. So that means we actually have to try to isolate that element before it ever goes into the multi-collector so that we can robustly determine the ratio of its isotopes to one another. So good example of this for copper, and especially in groundwater. A lot of groundwater has a lot of sodium in it, which can actually combine with the argon that we basically push everything through with. And what that does is give you a spurious count for 63 copper. That can become a real problem. So we need to get rid of all that sodium before it goes into the instrument. Thus bringing us to our groundwater flow chart. So basically this is the way it looks from end to end, more or less. So we start out in the field. If we can, we take water from flowing bores because we don't have to purge them out. And sometimes that can take hours or days. A lot of time involved with that. And then you still might get a somewhat contaminated sample. More work needs to be done to figure out if that's true or not. Basically, we need to filter and acidify that. Then we do our chemistry in the lab to basically separate out that copper. Goes into our mass spectrometer. We try to get these nice signal peaks where nothing else is interfering with that. And then from that, we can try to figure out what those isotope ratios are. The other fundamental difference here between this and radiogenic isotope systems is we have to sort of finagle things with the actual data that is coming out of this, because I said there's a lot of physical processes that can fractionate isotopes, some of those being introducing those isotopes into the mass spectrometer. So on the fly, basically, we need to interpolate what our baseline value is instead of just taking it back to the same baseline all of the time. So you start out with something like this, and I think this is a pretty good pop culture reference here since the new Jurassic Park movie just came out. Basically, we do all the math to compress all of that down, end up in happier days. And for us here, talking about copper isotopes in groundwater, basically the end all of that is ideally anyway, when you're sitting over top of a deposit and you sample water that is interacting with that, you end up with a positive isotope excursion for copper. So that's basically what's here on the y-axis. This is just time or analyses. And when you're off deposit, that drops down to some baseline value. So I always give myself brief intermission so I can take a breath and everyone can sort of hopefully absorb what's going on. And now we'll move into why this actually matters for why we're all here talking about critical minerals. All right, so I tried to do a reference to yesterday's session and find the same graph that Helen had in her introductory statement. In light of getting that, I just directly quoted Helen. So that's a bit tongue-in-cheek and in good humor, but I think what she said yesterday actually really sums this up quite well. It's copper. You cannot electrify anything without it. So this is basically a big infographic talking about the green revolution. Every facet of that requires copper to make it function. And that's why I basically consider copper to be the critical metal. So this is just expanding on that idea. So as basically everyone in here probably also knows, we're basically at this hinge point. So everyone's heard of, like peak oil. Some people may have heard of like peak Drake, again, a pop culture reference. Basically, we are at that point with copper in that the demand for it is starting to far exceed our ability to extrude it from the ground. Basically because, as people have said previously, all the stuff that is outcropping or easy to find is no longer there, and we have to go deeper and go harder to find this stuff. I basically don't need to spend any time on this slide because we all now very well know that Queensland is very well endowed with metals, including copper. So how does this actually function in terms of creating that positive isotope excursion when you're over top of or proximal to a copper-bearing deposit? Basically, the dissolution, i.e. weathering, of sulfide minerals, copper-bearing ones, by surface or groundwater, actually, just water in general, will basically release the heavy isotopes of copper and some other metals actually into water. creating a positive isotope excursion, which is basically what's going on over here. And this is just from some experiments looking at chalcocite and chalcopyrite. In both cases, you drive the copper isotope composition heavier or more positive. So by sampling water bores, especially deep ones, we can sort of sense those underground deposits because we're detecting that in the water that is interacting with them. And that is very good because that's what we need to be doing, because some of these are not very easy to detect by conventional means. The great thing about this as well, and something I really like as a virtue of this technique, is it's quite low impact. You're only relying on existing holes in the ground without having to poke any more in. And in the ideal scenario, again, actually reducing the number of holes that have to go into the ground to find deposits. So basically up here, I'm just saying the same thing. So low impact, low cost. Great thing for exploration companies, for example, is that this provides a pretty easy to interpret signal, especially relative to, say, looking at trace metals in groundwater or otherwise. In that sometimes that can be quite complex and context dependent. But also, if you say just looked at copper concentrations, you could be overlying, say in a validation area, a known deposit and not see a copper concentration excursion, whereas you will actually see a copper isotope excursion, and a hugely significant one relative to what our analytical resolution is. So again, summing that up, it's indicating mineralization where there is no elemental anomaly. And this is basically that canonical work by our main collaborator, basically looking at that at the Pebble Giant porphyry deposit in Alaska. Okay, so what have we been doing at JCU and in partnership with GSQ and some industry partners? So mainly that would be Mount Isa Mines here and Anglo American and some others. We have basically been taking this to sort of typecast areas and trying to understand or basically validate this technique and seeing if it works basically beyond context or deposit type. So the sort of progenitor of all this is the Mount Isa. So we had this huge project, an EGRU project, looking at copper and zinc isotopes in the sulfides. As a bit of a spin-off of that, we looked at some groundwater samples collected by the MIM monitoring team and basically saw the same thing. So when you're near the main Mount Isa copper zinc lead deposit, and especially if you're taking into consideration groundwater flow, you get these nice pings of positive copper isotope excursions close to the deposit that dies off when you go further afield of that, basically larger red dot, larger positive copper isotope excursion. Okay, so then again, in partnership with GSQ, we took this out near Cloncurry where there were some other known deposits and or prospects and tried to see if it would work basically in a different environment, sort of smaller deposits, et cetera, et cetera. So this again out near Cloncurry, and this would be where like the Eloise, Jericho, and Maronan copper bearing deposits are. Basically, we tried to sample everything we could in the area, basically in around a 15 to 20K radius of where those main deposits were. So we ended up getting around 40 water bores sampled. The pivotal thing that we did here was instead of basically having to purge monitoring wells and things like that, we specifically prioritized the bores that were already on pumps. And what that allowed us to do is basically go out and sample all these in, I think, 3 or 4 days. Dom and Dave in the room could vet me on that if they need to, because they came out with us, which was great. Long story short, we see the same exact thing. So similar style spatial map over here, and just showing that when we're overlying those deposits, we get these nice pings of positive isotope excursions again. Not only that, we actually get, you know, what we or I have been calling blips of intrigue. So places where there aren't any known deposits necessarily, where people may have been prospecting, but where they might want to dig a little bit further. We went back 8 months later and doubled down on it to see if there was any effects, basically looking after the wet season. Sampled the same exact bores, saw the same exact pattern, same sort of blips of intrigue. So that was really, really promising. So I basically have to end things there in that we do have some similar projects ongoing. We just can't really say much about them yet. One of these actually is a CEI project. So basically all I can say there is if any of this interests you, stay tuned and those results will be forthcoming soon enough. And then this is basically segueing into talking about what's going on at JCU, in that we are now also including trace element suites in these things, and then some other isotope systems. So looking at trace elements in these waters and actually parsing that out and trying to find, you know, relatively constrained suites of sulfide and oxide associated trace elements that might be also, if not vectors themselves, potentially proximal or even distal pathfinders, or what I like to call wayfinders, for where you might go then to try to find a deposit. Zinc isotopes function actually the exact same way as copper, but the signal is a bit more depressed. So maybe a bit more of a tool that you would want to do in complement to, but not necessarily on its own. And then we've also now started incorporating strontium isotopes, basically because that helps you differentiate water reservoirs. And then you could start to understand something about, say, groundwater flow in areas where you don't actually already know that. All right, so just spend the very last couple minutes talking about goings on at JCU and what we've been trying to build. So in essence, this actually isn't any sort of new facility or anything like that. We have just been trying to renew and regenerate and expand upon the existing facilities that are there and really give it some sort of, you know, entity and brand. So then we can serve as this analytical hub, basically for industry engaged research. And a lot of this has been driven by not only these projects, but also some commercialization funding that we've gotten internally through the university as well, to really sort of try to build this out. So this picture actually was the one I provided, I think, in November of 2020, whenever there was a GSQ UQ workshop in Mount Isa. Basically, this was sort of the state of one of our clean rooms. We actually have two, which is awesome. At the time, nice and clean, which is great, but you can see there's not a huge amount of basically ventilated workspace in there. And now we move into basically the present day. So some of these pictures were taken just a week or two ago. Basically, we've built out our capacity, not just in terms of the infrastructure, so the gear that's in the lab, but also the personnel. So new people, new raw human power, but then also, you know, intellectual capacity as well. And so if I do forget to mention these people, please find their names on the following slides because they're absolutely integral to what we're doing. So some of these were by one of our research officers, Hillary Lewis. And now basically just the state-of-the-art stuff that we are doing at the moment and telling you, you know, the stuff that's on the horizon and that we're building. So we're doing all this groundwater research. We think that strontium isotopes are really important to that. We have this nice fancy robot basically in our instrument facility now where you can take water once it's been filtered and acidified from the field, basically plop it in one end, it will separate out most of the major cations that you want, including strontium, I guess, as a minor cation. You take that out the other end, it puts it in a vial already for you. All you have to do is basically carry that over to the mass spectrometer and you can get your strontium isotope ratios right off of that. Really awesome stuff. So this can all work in the background while you're doing nothing or say at a conference or workshop. And it's really, really precise at what it's doing. All right, I see Helen standing up, so I will wrap things up quickly, which is great because this is basically my last slide anyway. So the other thing that we are doing sort of in the interest of building these larger views of things is we're trying to get a bit more sophisticated with our statistical analysis of our data sets. So I'll run this back again. So this is our Jericho Eloise area out there. So this is just some rough, basically heat mapping of that. What we are now doing with this is developing these Voronoi diagrams that basically statistically describe the regions where you would see positive isotope excursions and therefore might actually see deposits undercover. Basically darker color, higher copper isotope value. And what you can see once this starts to phase in is that we reproduce these patterns really nicely. The great thing about this is that we can start to develop more regional views and then define areas of prospectivity that have actually a better underlying statistical component to them. And this actually was courtesy of one of our new postdocs that has just started, who is bringing sort of an archaeological and other side of things where they actually build these isoscapes. So that's what this thing over here is called, is an isoscape. This is something you can do at this scale, but if we start combining data sets, we can actually build these basically all across Queensland. And that's it. I'll leave it there for questions. And since we can't take people into our clean lab, we have a virtual tour there.
Awesome. Okay, any questions in the room? In a few years, you will all be using copper isotopes to explore undercover. Trust me. Ryan has a question.
Thanks for that. It's a really good talk. Just a question, I guess, on the footprint and how far you expect these isotopic excursions to move away from known deposit. Are you, can you use this as a regional vectoring tool, or is it just something that's going to get you into a region? And then can you make a comment on the constraints on using this to target?
Yeah, so that's an excellent question. I would be hesitant to give a finite answer at the moment because we are still building this up and trying to figure out what's going on. The way that it seems right now, again, being dependent also on groundwater flow and other features in the region, you would maybe pick this up, say, up to a few kilometers out. Again, that's also going to be dependent on the copper isotope composition of your more distal waters, so your baseline value basically in the area, and also the copper endowment that's in the area as well. So you can imagine you have a very low baseline, very little copper in the region, you have a massive copper bearing deposit, you would probably sense that further afield. But because we're not entirely sure exactly where the boundaries of this are, that's actually why we've started to include the trace element suites especially, because what we have seen with those is those can potentially provide you with what I have been calling wayfinders basically, so more distal vectoring tools that sort of tell you the general direction that you might want to go, and then from there the copper isotope work might pick up.
Hi everyone, thanks very much for the talk. Question about using this for deep exploration, where you have aquifers that are not connected near surface. Have you actually started looking at how you could take reliable water samples at say a kilometer's depth or 500 meters depth yet? And what's the technique there?
Yeah, that's another good question. Basically, it comes down to how much time you're willing to spend watching water pour out of a pipe. Where we've been looking, a lot of times we're looking at, say, anywhere from 20 to 100 meters, something like that, undercover. And the general idea is we sort of worked out if you, in the worst case scenario, you had a pretty large casing on your bore, how long it would take to flush out everything and try to get a pristine sample. As opposed to say purging it, because then you sort of know once you've hit bottom, et cetera, and then you need to let it recharge. Basically what we've been doing as a rule of thumb is 5 to 10 minutes of letting that purge out. That ends up being hundreds of liters of water that come out before you're actually sampling. So if you wanted to go deeper, or you knew that you had a bore where you were getting that water from say hundreds of meters of depth, you would basically just run the calculation to get a rough idea of how much you would actually need to pull out of there before you were getting anything that wasn't just the water basically sitting in the pipe getting up to the surface. So in some of the regions that we have gone, we have actually sampled bores that are, I think the record at the moment is close to 400 meters down. So we are actually getting pretty deep, and we are still able to measure the copper isotope compositions of those waters. Again, we still need to really build on this foundation. I was just talking like this morning that we're sort of at that cusp where this seems to be working. We validated it in 4+ different contexts now on top of other people who are doing similar work, mainly over in the US and in Canada. So I think we're at the stage that it's working. We just need to start expanding this out so we can understand those finer details.
All right, we've got a question online from John Menzies. He would like some thoughts around the Great Artesian Basin. He says it can help a great deal to partition the isotope data based on particular groundwater systems. For example, the Great Artesian Basin is quite different to the groundwaters to the west, regards to a number of elements and at least lead isotopes. Copper isotopes he doesn't know. What do you think?
Yeah, that's an excellent question, John. I think that a lot could really be learned on adding, I guess, value to what is already there, I guess, with our understanding of the Great Artesian Basin. So there's been a lot of work there. There is actually still a lot of I guess, not necessarily controversy, but trying to understand the interconnection of various bits of that. But then once you start moving outside of that, what is actually going on? And I think taking a harder look at what else is in those reservoirs, such as copper isotopes, zinc isotopes, strontium especially, and some other bits in there, we can start to develop a better understanding. And that is, a facet, not necessarily for the exploration space, although it would be complementary to that, but looking at those isoscapes and trying to develop these larger views of what's going on so you can actually start parsing these things out a little bit better.
Right, thanks, Brandon. I know we're probably going to have more questions, but Nathan's waiting and we're going to be eating into morning tea time, and that's going to make everybody cranky. So you can find Brandon at morning tea along with Chris. The two of them are going to be hanging out together. Nathan Fox, please come to the stage, and Nathan is going to tell us the latest of what's happening in the UQ GSQ collaboration on sustainably extracting Queensland's rare earth.
Awesome, thank you. Just make sure I was speaking laser. Sure. Excellent, great, thank you. Okay, thanks everyone. I just said to Brandon, it's going to be a very tough act to follow. I've got literally no animations in my presentation at all, so it's going to be a little bit drier. I just wanted to give an update today on the project between GSQ and UQ, which is extracting Queensland's rare earth elements sustainably. So just for background, the overall aim of the project is to investigate the options for sustainable production and reprocessing or processing of rare earth resources in Queensland. It's funded obviously by the DI over a period of about 4.5 years, and we're about 2 and a bit years in already. So the main aims are really to review and test the processes technology for processing rare earths, create more sustainable hybrid processing methods. So not just using the methods that are kind of associated with rare earth processing in countries such as China. We want to try and find ways that we can be more environmentally conscious or sustainable. But the main thing also here is to identify new ore types we can open up for processing as well. So we've talked a lot about rare earths over the last 2 days. Certainly there's a lot more potential out there. So this is a really collaborative research initiative between centres at the SMI and UQ schools. So it's been run and administered to the BRC through Paul, myself and Rick. But we're partnering really closely with JKMRC, the CMLR, the Department of Chemical Engineering, which is the hydromet side of things, and SEAS, which is Gordon Southern and his microbes and bacteria. So we'll talk a little bit about that. Obviously, we can't do this without significant support from the government. So thanks to Helen and the GSQ for support there, and also the industry support from the companies involved. So Metals X, Stewart's here, Centrex and Insitutech. Today I'm going to cover just some of the research that's been done so far in Mary Kathleen, really focusing on the tailings, the peak range volcanics, and if we've got time, the phosphate deposits as well in Queensland. Just as a quick illustration, these are kind of some of the phyto extraction techniques that we're looking at as well. So we can see a great uptake of rare earths by plants, which is great for potential processing and also for exploration. So just by what we all know about rare earths, we all know they're very desirable. Up at the heavy end of the rare earth spectrum, the prices are very favorable, down at the lighter end, less so, but nevertheless, still a really desirable product at the moment. As we've talked about the green revolution and design for alternative energy sources, rare earths are imperative. So we have just a kind of an indication of the average cost of abundance. We all know that rare earths doesn't necessarily mean rare, but they're often hard to find and difficult to extract. So that's why we're looking through this project. So in terms of the alternative technologies that have been looked at so far, there's been quite an emphasis on microbial. So not just extraction of rare earths using microbes, but also how they're potentially pre-concentrated in the first place. So there's clearly a lot of microbial involvement in the formation of some of the rare earth deposits. So we're looking at how we can better utilize those for potential future extraction. Timeframe's a little bit of an issue here, and we can talk about that a little bit later on. The phyto extraction is really prominent. The uptake of rare earths by certain plant types has been known for a long time. We're looking into that in a lot more detail. And hydromet as well. So optimization of these process flows. How can we make them more sustainable and less potentially environmentally damaging? And also, of course, beneficiation, traditional mineral processing routes as well. So in terms of the Queensland study sites that we've been looked at so far, you can see from the map, and for those of you interested, you can see some just snapshot chemical abundances or analyses from the project. We're working around the Mary Kay area from the tailings, the phosphorites at Ardmore and Phosphate Hill, and the Peak Range volcanics. We're hoping to move up into some other deposit types, including laterites, and if we can potentially find some ionic clay deposits as well. The key thing to really take away from this slide here is that we can see a large range in total rare earths from all of these deposit types and different proportions of heavy to light rare earths as well. So on the bottom here, you can kind of see the relative proportion of heavy to light. So for example, Mary Kay, 99% of the total rare earths in the Mary Kay tailings are light rare earths with only 0.5% in the heavies, but that switches over as we move towards the phosphorite. So different targets for different elements. By way of comparison, it's always bad to compare yourself to other things, but these are kind of benchmarked in Australia with some of the largest and most significant rare earth deposits. So you can see over at Mount Weld in the laterite, we see a huge enrichment, which is why laterites are such keen targets. But the carbonatite itself underlying is quite comparable to some of the systems in Queensland. So there's a lot of potential there. And also the Toongi trachyte as well, which is benchmarked by the just south of Dubbo there. Again, an example of an alkaline hosted rare earth system that we're trying to target here. And others. So just some spider diagrams. I won't dwell on these too much, but basically just again for comparison, you can see how the peralkaline systems that we heard about yesterday benchmark up against Toongi and Mount Weld. The same for phosphorite, slightly higher in the heavy rare earth side of things, but significantly Mary Kay by far the most abundant rare earth, but very high in the light side and very low on the heavy side. So that obviously affects some of the economics of these systems. So going back to Mary Kay, this is a nice photo taken by the field team that went out sampling there, and a micro XRF map of an ore grab sample just from the pit. So we can see there's plenty of life left in the ore body itself. The rare earths are mainly hosted by allanite. We do see heavy rare earth in the garnet, and there's rare earths obviously in the apatite and also still like primary phases. Unfortunately, what we're dealing with here, or not fortunately what we're dealing with here, is the results of the previous mining operation. So the tailings dam here, there's about 7.5 million tons. The grade, as it was drilled by CSA about 10 years ago, is kind of on average between about 3 and 4, but you can see from these downhole plots of the assays that it's quite heterogeneous. So that relates to some of the previous processing. The interesting thing that's come from this work and also a previous PhD study at UQ where sequential extraction was done, there's 85% of the rare earths are hosted by allanite, but there's a water-soluble sulfate phase that seems to carry quite a lot of rare earths. So that's quite an interesting aspect of the tailings. That means it could be recovered fairly simply and quite cheaply. And obviously, as these are the tailings, we're obviously looking at fine grain size. So just some of the results that we've seen so far. The water-soluble work was done by Gordon and his team at SEAS. We don't have to dwell too much on these, but you can see the starting composition of the tailings versus the recovery. So for some of these rare earths, we're seeing between 5 and 10, sometimes up to 17% recovery. And a back of the envelope calculation infers that if we were to recover that leachable portion from the Mary Kay tailings using just water, we could potentially recover several tons or thousands of tons of rare earths quite easily. There's a bit of debate. Are we looking at the result of the previous sulfuric acid leaching of the primary Mary Kay tailing ores, or is there a potentially bacterially mediated formation of the sulfates in this system? So that's something that's going to be ongoing. These are examples of some of the leach tests and some of the phases. So these are some of the precipitates that have formed after the leach test has been finished. In a more traditional approach, James Vaughan's been working really hard with his team to try and optimize recovery of rare earths from the allanite. It's a highly refractory source of the rare earths. You can see some of these sequential increase in recovery. You don't need to dwell again too much on these. These are just the starting compositions. And then a series of experiments. So you can see as we move through from a low temperature acid leach to a 15% sulfuric acid acid bake with a water leach. And curiously, a lower amount of sulfuric acid and an acid bake, we actually get a higher recovery. So the whole idea here is to try and optimize these, to try and use less reagents and make it much more sustainable. There was a few more additional work going on by James, really interesting work on precipitation and double salt. So the whole aim here is to actually produce a rare earth product that we can actually keep in the country instead of constantly sending products offshore. The phytoextraction is going reasonably well. We know that plants uptake rare earths. Unfortunately, in lab trials using a range of plants, you can see from some of the controls here, the hydroponic testing, Mary is not doing quite so well, so we need to understand why it's kind of stalling at this stage. But they've assured us that they're working on that. It may have something to do with that, that soluble sulfate phase, and I think that's something we need to look into. But certainly we know that the plants in the area uptake considerable amounts of rare earths, and we see a huge uptake or a huge enrichment into the soil as well, which I think I've got on the next slide. Yeah, so these are some of the soil work that's been done. So essentially nearly everything around Mary Kay is enriched in rare earths, the soils, the plants, and also the biofilms that are coming from some of the previous mine workings. This bacteria that's been isolated through some of the genomics work is apparently ammonia loving. I think Gordon's attributed this potentially to the previous blasting operation. So there could be some remnants of some kind of introduced or bacteria that actually just love the environment, but particularly they're thriving on the rare earths. So the idea here is then to look at how we can potentially capitalize on that and sustainably utilize that for rare earth extraction on a commercial scale. Okay, moving to the peak ranges. We did hear about this yesterday. I won't talk too much about it, but just from the kind of the Australian scale context, we're looking at these very young volcanics, regionally extensive across Queensland and New South Wales related to hotspot activity. In the peak range, we're mainly focused on these domes, Christmas domes, Clavis domes, and Pitts dome, and the geological map from Chandler's Bandler just shows that these are the Adrian rhyolites. So you can see them here in green. And these are the main study sites that have been looked at in this project. In terms of the mineralogy, the beneficiation study was working on mineral characterization. Now, this was on a crushed product, so this is quite different to the sort of scale that Ross Chandler's been looking at. This is using the MLA here at the JKMRC, and you can see that the mineralogy is mainly dominated by autoclave feldspar and quartz, with about 10% Adrian. The mineral phase of interest, or that we think is holding the most of the rare earths, is obviously the bastnite, but that doesn't really even feature. We're looking at somewhere down below, way below 1% so it's a very fine phase that we're looking for. Some micro-XRF work that was carried out by Anthony Venant. He identified, obviously, that we can see or we can track some rare earths. So the question is whether or not the deportment of the rare earths is entirely within these rare earth phases, or do we see some more subtle deportment of rare earths, and that's something we can also follow up on. But in terms of the traditional beneficiation route, you can see that the kind of the PAT here of the bastnite from the MLA measurements is around 10 to 20 ppm. So a traditional processing route is going to involve quite a lot of fine grinding. So we're quite keen to find ways that we can minimize that through grinding trials and different leach test work on different grind sizes. James has also been working hard on this. The main attempt here is to really try and remove the traditional HF approach from the conventional process. So obviously using HF in processing is not a desirable option, and also leads to separation of the rare earths at different phases. So James's new suggestion over here also manages to maintain the tantalum and niobium. So we're going to maintain that critical metal stream as well. Baking an oxidative sulfuric acid leach with an HCl leach as well. We see that these, the rare earths and the tantalum actually follow down all the way through here to the selective precipitation stage. So we're not losing anything out into the leach residues, which is different to the traditional approach. Some of the preliminary results showed quite good recovery for a range of rare earths, but not so much for others. So again, there's work in development optimizing these. In terms of the soils, similar to what we saw at Mary Kathleen, we can definitely see high mobility of rare earths in the soil horizon. Future studies are really going to start looking at the bacterial mobilization of rare earths. So there's a genomic study that's going to be carried out at Peaks Range as well to try and identify those. But certainly you can see there's a lot of prospectivity for rare earths in the soil, so from an exploration perspective, but also the uptake of plants, of rare earths in plants that are widely distributed across the site. So the natural plants here at Peak Range, this is from the CMLR group. You can see that we're up to 100 to almost 1,000 ppm of rare earths in some of those plants. And then we're using the micro-XRF quite extensively to actually extract those, but also doing solution chemistry on those. If there's time, I'm not sure how we're doing it. I'm just going to quickly run through the phosphorite deposits. Again, this is the systems that are quite enriched in heavy rare earths. Ardmore is particularly enriched. There's really prospective ground for the rare earth elements, but particularly the heavy rare earths, and Phosphate Hill slightly lower, but proportionately high heavy rare earths. The work that Gordon and his group have been doing have identified a lot of microfossils within those phosphorites. The inference is, were those microfossils active at the time of formation? Were they actually involved in the concentration of rare earths in the first place? And potentially, could we then utilize that in an onward sort of downstream processing opportunity? So we're looking for really these kind of novel rare earth processing opportunities here. And again, going back to more traditional, I think it's always good to be able to have a staple leach approach that you can fall back on, or you can utilize to kind of drive the economics. James has been working very extensively with Phosphate Hill, particularly, but also Ardmore ores, an average rare earth feed grade of about 400 to 600 ppm. Again, using the sulfuric acid leach, but solid to liquid separations can actually start seeing these rare earths separate into different parts of the stream. Following the rare earths through this part, there's a neutralization by ammonia, which just brings the pH down up, I think. But this ammonia could potentially be utilized from the existing phosphogypsum plant. But essentially, we're seeing a way to kind of concentrate the rare earths in this resin absorption, and then a cycle where we can actually keep using that resin or stripping the rare earths from that resin. So technicalities of this, obviously, with James, and I'm kind of a messenger here, but certainly we were seeing a really good novel way of kind of changing those processes to make them much more efficient. He's also been working on a preliminary caustic pressure leaching approach, which will improve rare earth recovery. So we can see that those rare earths need to improve, the recovery of those rare earths do need to improve for the economics to stack up. So currently up to around 85% on those systems. So the forward plan, very quickly, we're going to be looking a little bit more at characterizing those multiple soluble phases at Mary Kay and looking a little bit more at the rare earth department. We're quite interested in some of the work that has been done at ANU as well in the department of rare earths between the the allanite and the garnet. Further acid baking is going on with James, and really the aim here is to reduce the acid consumption at the current estimates and economics. The sulfuric acid cost could account for about 20 to 40% of the value of the rare earth, so we really need to find an opportunity there to reduce that. He's also stumbled upon this, being formed in the Mary Kay system, which is a lanthanum arsenate, which is actually fixing the arsenic that's in that system, but there's a potential that that could be used as a treatment for high arsenic ores in other parts of Queensland, so that's something that it will be followed up on. The hyperaccumulator work has been extended across Queensland at the herbarium. XRF analysis of this particular plant has shown rare earths in quite a wide distribution across Queensland. So looking at that as a kind of a prospecting tool. As I mentioned, those sorry looking Mary Kay seedlings, they need to be optimized, so they're still being worked on. Last month, we picked up a SCIAPS Z300 from Andrew. So finally, we've got some analytical capability to analyze these. They can be challenging, but we're certainly willing to take on that challenge to try and characterize the rare earths in ores, wastes, and also in plants. And we just heard from Brandon there as well. We're looking at a neodymium isotope study led by James Cook, but feeding off some of the results from the study where we can actually track and trace rare earth from the provenance, but also through the processing. So can we potentially identify or fingerprint rare earth products that have been formed through biological means or through traditional leaching means? And I think that's really good from a sustainability perspective. And that's it.
Thanks so much, Nathan. He's representing a huge team of people there, so
it's all over my head.
It's all over your head. It's all over mine too. Okay, all right. I'm going to start with Jeff, come to you, Lena, and then go to Kate. And we are eating now into both morning tea and Anita's time slot.
Good morning, Nathan. Thank you for that. Jeff Swingler is my name. Having worked on Tungai pre-COVID for 5 years with Australian Strategic Materials, and my colleague Dudley Kingsnorth worked for 20 years on Mount Weldon Linus project. My actual question just on this, and I recognise the benefit of bioleaching from an environmental perspective, how much longer in time frame does the leaching process under bio take compared to our current conventional solvent process?
I don't think anyone's lived through a full trial yet. So I think it's on the order of 10s to 50 to, as Gordon says, almost 300 years potentially. So it's the long haul approach. I think we could probably catalyse that to make it economic. But I think there's other linkages there. It's to try and understand the formation and potentially how we can actually better utilise it. But as you say, it's not potentially an economic option now, but certainly in the future, yeah, it has potential.
Nathan, I was just wondering, what do you think the main controlling, effect where you have this decoupling in behavior of light rare elements compared to heavies? So do you think it faces its stability of some minerals, resistance? What are these factors? And you see this difference in different systems. For example, phosphorite are better for heavy rares and the other for light rares. What the factors?
Sure. Again, probably currently outside of my realm of expertise. I think when we look at the systems though, the Mary Kay system is very different in that hydrothermal formation. We know that it's always been very light, enriched in light rare earths, and we see that in the ores and in the wastes. So there's nothing happening necessarily in the kind of the short term that's changing that. So it's clearly something linked to the hydrothermal system. I suppose the phosphorites, I can't comment wholly, but that slight enrichment in heavies potentially is biologically mediated in some of those systems. Certainly, when we look at some of the results of the biological work or the uptake by plants, that does tend to favour some of the heavies. So potentially there's some fractionation control there, but I definitely know there's probably more experts in the room that could help you with that question.
Hi, Nathan.
Hi.
If I can offer some perspective on the phytomining and the hydroponic plants. So from a previous career as a bioinformatics researcher, we did a lot of work on some weird observations we had on plants uptaking weird combinations of ions. And one of the things that we found was they did that best when they were stressed. So the proteins and the ion channels in the roots switched on, the genes for those switched on when the plants were under stress. So that included insect attack, high salts, not enough water. So can I suggest maybe you try not treating the plants quite so nicely and you might have better luck.
I'll definitely pass that on. They spent a lot of money refurbishing their plant area, so maybe they are treating it too nicely. That was good.
Okay, I'm
Just
just
the
going to
pot in
check.
the garden will work.
I'm going to check online and see if we've got questions. No questions. Okay, I'm going to suggest we break now for morning tea, and we are coming back at 10:40. So you have 18 minutes for morning tea. Nathan, super dog.
the list?
Yeah.
Yeah.
Yeah, no, it was good. Mineral resources guys are still.
Oh, yeah.
Yeah, they're just looking so. Kobie's. Yeah. I'm just going to give a presentation.
Yeah, you're right. All good.
Oh, in your pocket?
No,
Like
yeah.
clip or you throw in your pocket, doesn't
Yeah,
it?
there's
Go?
a-
Yeah.
I can clip it.
Yeah, clip it, do that. Yeah.
Clip it safe.
And just pop this on your
Yep, you're right.
So that's for the online audience.
Yeah.
And that one's for the people.
Try to talk into both.
So you can
Alright.
kind of stand there.
Yep, can do.
This is on.
That bad boy.
Yep. Brains laser.
Alright.
Back to these
Bloody
slides.
bit. Love your work. Thank you. It's been running smooth. You're doing a good job.
So far.
Can't
Yeah.
complain. You would have had some long days, I reckon, in the last few days. Oh wait,
When
yeah.
everyone stands up.
Yeah, I'll wait now. I'm getting too excited.
But you can
Ah.
show that's okay.
Oh, I probably will. Yeah, I did my practice run. It went about 17 minutes, 16 minutes. So that's all right.
Yeah.
I tried to keep the slide, slash some slides down just to
Yeah.
make sure it doesn't do stupid stuff.
Very good.
No, it's all right. Sure, it'll be good. You need a big bell, yeah. You need a cowbell. Oh, that's like the waiters saying your food's ready, isn't it? Nah, it needs a better one. No, you need, you know what you need? The cross-country belt. You know in cross-country, the last lap? Yeah. That's real good, actually. Or just a little drum kit. You do a little drum solo. All the cows coming to be milked. No, there'd be some good stuff out there. I should have went out there. I loaded up on food this morning. Geez, that looks good. Shit, what do they do? Yeah.
Something else.
No, it's all good. No, mine's it's nothing too flash. It's just just something I stuck together.
Yeah, well, you know, that's what we all do.
It's not very, yeah, that's what I was just thinking of the irony because it's probably the least technical talk, but I'm also in technical services. So like, you think I should be a bit more technical, but it's pretty basic. Yeah, oh look, it's not, I wouldn't even call it science. Like geology is, I mean, all the modern stuff is, but basic geology is the least sciencey of all sciences, in my opinion. It's more of an art.
It's a mishmash of everything.
Yeah.
It's very interpretive.
It's an art.
It's the interpretive dance. Of,
Exactly right. Yeah.
Versus classical ballet.
You're right. Yeah. I mean, exploration especially. Oh, you're a scientist. I'm like, I am a scientist, but I wouldn't call what I do science. It's something else.
I might have been.
Yeah, I'm like, it's something.
Budgets.
Yeah. Jack of all trades. It's better to be a generalist, I think. I don't know.
All right.
Yeah, you're right.
I'm gonna go get these.
Yeah, do your thing. There's no rush. It's not super long, and I can cut it pretty easy. You're right.
Oh man, so much good food. What are those things over there? What are those little delicious things? What? That looks good. There's good food here. I should have. What? Look at them. Nah, well, I had this huge breakfast. I was like, I'll eat a big breakfast and I'll be set to lunch. But no, it was a mistake. It was a mistake. I know. I should have fasted. No, that's all right. You live and learn. Pretty good turnout. Has Greg Morrison been here? Have you met him at all? I don't think he's. I know Bimo had COVID, so yeah, I haven't seen him. Yeah, that's a shame. But yeah, Simon Beams and Greg are pretty tight. So if one of them has COVID, the other one probably has it. Yeah, I suspect Greg would probably have it too. In that case, they work together a lot.
They can hear you online talking about food.
Oh, sorry, yes.
Okay, everybody, we are getting started once more. I will get the big ruler out and start smacking tables. There is actually somebody here who knows my father, who is an English teacher. So I've never been to a geology workshop where somebody knows my dad. It's funny. But anyway, we're starting and we're kicking off the mine waste session, which is going to be awesome. Please welcome Kobie Johnson, who works in the Technical Services Group, which is a really weird name for a group that looks after
everything.
Yeah, no, they look after the abandoned mine sites and a lot of other stuff around Queensland. So please take it away, Kobie.
Good morning, everyone. I'm Kobie. I just realised the irony in our department or our group's name, Technical Services. This is probably the least technical talk, despite the name of the day and possibly the whole conference. But I hope you enjoy it. It's a bit of a whirlwind tour around some of the abandoned mines we manage throughout the state and what people are doing on them to re-commercialise them and what we hope to do in the future, I guess. So it's kind of a sales pitch at the end, but the first part's interesting. See how you like it. So what do? We administer the Queensland Government's abandoned mine lands program in line with the abandoned mines management policy. Pretty boring, but you can look it up if you're interested in it. We have a number of discretionary powers under the MRA to manage abandoned mine sites to protect public health and safety mostly, but also environment. The main aims of what we do, re-commercialise, repurpose or remediate abandoned mines to ensure they're safe, secure, durable, and where possible productive, which is what I'm interested in. So I suppose the key, in a nutshell, what we do, we monitor and prioritise the risks from abandoned mines, conduct activities to reduce that remaining risk on those sites in line with our available funding, a lot of consultation with stakeholders, and the bit that I do, which is investigate re-commercialisation and repurposing opportunities at these sites. So when I started with this group, actually 4 years ago, time flies, the problem we had, I know everyone here is pretty familiar with min-op points. Load up min-op points, you get, depending on which version of the data you have, you get about 15,000 plus or minus a few thousand abandoned mine sites throughout Queensland. So how do we prioritise these, mitigate the risks, and in general just manage them? So what we've done is basically we've passed through all that data and tried to identify the most complicated sites that we want to prioritise for works. So from that interesting map there, again, that's what most of you would be familiar with in terms of min-op. They're quite small, sometimes dangerous, but quite small disturbances that may or may not require remediation. So what we're interested in are these big ones. The map's not too flash, but those dots there, we've got about 100, 110 of these program sites that we've identified. So they're a bit more complicated, a bit bigger, and need to be worked on kind of in the short to medium term. You can see all that online if you want to talk to me about it later. And then we've divided the rest into historical mining disturbances or small scale mining disturbances. And these are managed via our shaft repair program, depending on residual risk, how close they are to roads, etc. So part of my job is to develop a program to determine the residual risk, the priority for works, and the re-commercialisation potential at each one of these sites. So I suppose you've got two ends of the spectrum. Once you run it through, we've got a re-commercialisation framework. It's kind of a weighted calculator, I guess. It's been developed over a few years. Two ends of the spectrum. A good example of what we do in terms of rehabilitation, Collingwood Tin Mine south of Cooktown. That's got a pretty significant tailing storage facility that we're doing quite significant works on at the moment, and looking to hand that back to the traditional owners in the near future. That's when it doesn't quite fit the bill for re-commercialisation for various reasons. And then on the other end of the spectrum, you've got re-commercialisation. For example, something like Wolfram Camp Mine, which we also manage. Obviously, there's a heap of benefits to re-commercialisation. It's all about recovering Queensland's mineral resources, beneficial reuse of mineral waste, and also environmental benefits as part of that. Money, that's good. Good to make money, isn't it? Good for you to make money, good for small communities to make money, good for the state to make money. And it's about finding new minerals on old sites, not just the stuff that they used to mine, but also stuff that they may not have assayed for at all, which I'm sure people after me will talk to in better detail than I can. In terms of our re-commercialisation framework, here's a bit of a basic diagram. Some of the things that we think about, there's a lot more, but basically it's a prospectivity analysis, first pass. Looking at remnant infrastructure, a lot of these sites have heaps of remaining infrastructure, which is of value. Some of it's still operational. So some of these sites are kind of semi-turnkey, I guess you could call it, in terms of mining, depending on how they're disclaimed. Reprocessing opportunities, which is, we've got a whole host of researchers doing that kind of stuff, but we've also got our own calculators for that. In terms of, and also quarry potential. So some of the reprocessing, spent heap leach is especially a really good road-based material. They're fairly benign, so that's another option. Basic land and administrative boundaries we take into account. And just as a bit of fun, we've put some renewable stuff in there too for solar, pumped hydro, etc., just to see what comes out. So we put it all through there. What do we end up with? We've got, here's a bit of a couple of sites that I'm interested in up there. Most of you are fairly familiar with them, and we've probably talked about a few of them already. Mount Oxide is an interesting one down there. That's north of Capricorn Copper. This is another one I was out at last week, avoiding being in the office with my my boss Tanya there. That's quite a pretty site. That's not on the internet yet. But I suppose the key consideration for all these sites is data management. So without the data, obviously these things are mines, there's huge data sets, they disclaim or expire. There's a number of different ways it happens, but the first thing to go missing is usually the data, and that's the thing that's worth the most. So a big part of my job is kind of through various sources and methods, picking up that data again and seeing what I can do with it, and putting it to people that know how to deal with it better than me, like GSQ. And then the upside of this is probably our most environmentally hazardous sites are probably also the most prospective. Obviously, you've got a lot, these are all metalliferous mines, with the exception of Greenvale. So all these things generate heaps of acid rock drainage, acid mine drainage, whatever you want to call it. But that's good because it also means there's probably a fair bit of ore there too. I'll just give you a bit of a rundown of 5 of our interesting sites and what's going on at them in terms of re-commercialisation. Mount Morgan's the big white whale, the Moby Dick of our program sites, I guess you could call it. It's pretty close to Mount Morgan, massive VHMS deposit, 8 million ounces of gold, heaps of copper, huge amounts of waste, huge amounts of environmental liability. So this, by definition, isn't actually an abandoned mine because there's still mining leases on it, but there's a memorandum of understanding with the mining leaseholders. So basically, as a department, we look after the care and maintenance and environmental side, and they get to explore it, which is a pretty good deal, I think. So that's got a whole specialised team that constantly look after care and maintenance there. It's a huge site. There's heaps of cultural heritage considerations. All these things are really old and all heritage listed, so that's something that needs to be taken into consideration as well. In terms of deterioration, preservation, asbestos, hazards, etc., etc. And heritage minerals are the ones looking at processing there if you want to have a look at that. I'm not going to talk about what those guys are doing. You can look at that in your own time if you're interested. Cool project though, really cool. Mount Chalmers is another similar one, not far down the road from Mount Morgan, another VHMS, quite a bit smaller, still interesting. That's been on care and maintenance since 2014. This is at the other end of the spectrum in terms of care and maintenance. It's fairly low maintenance, so we just basically monitor that periodically, and it pretty much looks after itself. We've got pump back systems that work pretty well, pump back into the pit, and it's pretty self-sufficient. Q Mines is actively exploring that, drilling it, doing new resource calculations there. That whole corridor is quite prospective. It's something I'm personally quite interested in too, so it's good to see someone doing something there. Greenvale's another goodie. You've probably heard about this in the past, not far from Townsville. This is one of our lower risk sites. It's what we call a surveillance site, so it's something we don't regularly do work on. It's just something we keep on our books. It's under a mining lease application. Australia Mines has lateritic nickel deposit with a bit of cobalt and scandium as well. Fairly significant production from the 70s through to 92. This is actually one of the very few sites in Queensland that's technically been handed back, but via the Mines Inspectorate. So that's an interesting one. Mary Kathleen being the other one through different methods. Obviously, it's probably not quite up to today's standards, but back in the day, that was acceptable enough. Horn Island, really nice place to work, really hot all the time. Beautiful day, really beautiful. Not far from Thursday Island, IRGS, maybe. We can debate that later. Small bit of production underground in the late 1800s, and then more significant open cut in the late 80s. Disclaimed 1990. Care and maintenance, we just look at that on an as need basis. Obviously, there's quite a bit of risk there, being right next to a fringing coral reef, which people use as a food source. So that's something we monitor very, very carefully, but we're lucky enough that the state of that site at the moment is quite good, and we don't have too many massive issues due to all the pump back systems and just the way the water balance works. That's the main pit. There's tailings under there and at least 2 crocodiles. Do we see them? We didn't see them, no. That was good. I was the croc watch guy when the UQ was sampling. That was fun. That seeps a little bit, but the pump back's working pretty well. Just something to keep an eye on. Alice Queen's doing a heap of drilling around there. That's another personally interesting brownfields exploration and also greenfields exploration area that's pretty hot in my opinion. Wolfram Camp, this is, I'm just gonna have a spiel about this now. This is my pet project at the moment. Not far up the road from, well, not far being a few hundred kilometres, but not far from here. Massive tungsten molybismuth horizon. Not massive, small to medium, I guess, but interesting, quite large, big open pit, heaps of historic workings. I'll skip through this quickly. Oh, sorry, that's all right. Good. Oh, I was like, how long have I been going for? Just tell me to shut up. I don't mind. I'll talk about it later anyway. Disclaimed, I think it was actually disclaimed on Christmas Eve in December, so that was fun. I was there not long after Christmas looking for data, which wasn't there, but I've found it now, so it's fine. We use former staff for care and maintenance there, and same with Mount Morgan. So the cool thing about this stuff is when we put people on care and maintenance duties, they've usually worked at the mine for a pretty significant amount of time. So it's a continuation of their work where there's not much other employment opportunities. And they're experts, they're absolute experts. They do mine tours way better than me. They know everything about these sites. That was put under a restricted area just before it was disclaimed because the tailings dam was in pretty poor shape and the water was doing things we didn't want it to do. So basically the aim there was to immediately look after those risks, which were quite high, with the aim of getting rid of that restricted area in the future if the conditions are correct. Conveniently also on unallocated state land, so easy from a stakeholder perspective. Obviously, we still deal with traditional owners quite extensively, but that makes it one step easier. I won't cover the geology. Everyone's gone over this in way more detail than me, and much better, but I've got nice photos, so that's nice. There's five key mineralisation / alteration facies. First 2 are ore, this one's marginal. These 2 are kind of peripheral alteration. Quartz pipe's the main one, high grade, hard to hit with drill holes. We do have good drill core records of this down at Zilmere if you're interested. Quartz Grisen, moderately mineralised, probably the bulk of mineralisation sits in here. Mica Grisen, that's a pretty good example of it there. Marginal ore, these are just interesting from a vectoring point of view. In terms of recent work, if you're wondering what we've been doing with the restricted area that we've had there for the past fair few years, we have done a fair bit of work there. We've used some of the financial assurance to significantly improve the TSF, the tailings storage facility and waste rock dumps. re-veg, hydromulching, all that stuff, using a lot of the traditional owners in the area. So it's a win-win there. Reinstatement of heaps of the electrical infrastructure, which wasn't in such good shape. So that's made it cheaper to run the site. Pretty extensive water management improvement. These two things are my pets, I guess. Picking up drill core, handing it off to GSQ to do their magic with it. So we've actually got some really cool, very nice core from Wolfram Camp, if you're interested in looking at it, down at Zilmere. Very interesting. Data retrieval, very time consuming. I've got it though, it's all good. Next slide. So in terms of the restricted area 442, where do we go? What are we doing with it? We're currently just weighing up our options, but I thought I'd just give you a bit of a sales pitch on what it includes. It's quite a big area, 480 square meters of former mining lease and EPM tenure. You got Wolfram Camp, Bamford Hill, heaps of historic occurrences. According to Almonte's reports before they packed up and went away, between 3 and 6 million tonnes at an average grade of about 2.2% wolframite, combined in their exploration targets they had on hand at the time. Interesting. In terms of assets at Wolfram Camp, it's pretty attractive. There's quite a significant, marginally depleted, I guess, resource there. You can do the maths. The processing plant's still there. Needs a bit of work, still pretty good. X-ray for ore sorter, everyone wants that. I'm not going to give it to them yet. High voltage infrastructure in very good condition. We've fixed that up. Heaps of all the administrative buildings and laboratories still there. Waste rock dumps. Other people will talk about this later. Still a bit of moly and tungsten in there. Cool project. Tailings storage facility, still do it. Moly and tungsten, interesting. So in terms of the re-commercialisation, there's a bit of a map, just a pretty map. I had to hide the scale because it was made by someone who wasn't a geologist and the scale was terrible. Try not to, I don't know what it was. There's like 6 different, awful. But good map, good general map. So this re-commercialisation is actually part of our curative pilot program, which some people have talked about previously. Terrible acronym, hard to say, but good program. We've done a fairly extensive market sounding and consultation with industry, which has given us a lot of feedback, which we're taking on board, and confirmed some of my own suspicions about what we want to do with it. Heaps of one-on-one interviews, talking to all the stakeholders, making sure everyone's on board, and now we're reviewing all that feedback from the market sounding. Almost finished. This is the last slide. So what do we learn from the market sounding? These sites are pretty complicated. As you'd know, there's legacy issues, heaps of previous mining disturbance, and immediate environmental exposures, which we've kind of, I suppose our approach has been to reduce that risk. And the feedback from all our interviewers, obviously geological risk, if the data's not there, it's no good. It diminishes the value significantly, and that's something we've tried to fill in the gaps with. Environmental risk, people want to know what they're up for if they take on these sites, and that's something we're trying to provide pretty good clarity about. Obviously, commercial risk goes in hand with anything mining. Regulatory, that's something we can definitely help with. So what we want to do is a bit more of a risk-based approach, to remediation rehabilitation, rather than gold standard. There's some compromise there, which we can talk about. And a multi-agency approach between ourselves, Treasury and DES. So instead of just dealing with each one of us separately, put it all together, make it easy. And I think there's a lot of financial incentives we can provide. We'll see what happens, watch this space. So that's the goal. That's what the future holds. We're hoping to put together some options and put together a framework. We want to put this out to market second half of 2022 if anyone's interested. Thanks for your time. Appreciate it.
Thanks, Kobie. Any questions for Kobie? Yes.
So if you imagine 5 years out from now, what would be what would be first prize for Wolfram Camp?
First prize, as in what you'd get out of it?
Or no, I mean, where would you like it to be?
Where would I like it to be? Look,
how would you describe it?
Do you want my government hat on or my exploration hat? Which hat should I wear? Okay. Government. I'll put government on. Government hat. I'd like a mining lease. I'd like it to be mining and producing royalties. Exploration hat. Do you want an exploration hat? Exploration lease, and I just drill the hell out of it. There's so much you can do in that package. It's really attractive. That's my explorations field.
Any more questions for Kobie? All right.
Oh wait, I had a question in the back. What was that? Where can I find the information? Oh, you can find it on GeoRes Globe. We have a marvelous bit of software. It's oh, look at that! Look at all those things you can see. You can find some shafts to look at. You can look at it. Anyway, interesting. Have a look at it. It's all on GeoRes Globe. Have a look. The core's in the core shed down at Brisbane. Go and have a look. Pretty cool.
Yes, it is absolutely. Thank you, Kobie.
Thanks for your time.
Thanks for the person up the back that asked the question about.
Good question.
where
Good
to
question.
find Love it. Okay, Anita, Associate Professor Anita Parbhakar-Fox is going to be talking to us about the bigger than the galaxy mine waste project that she has kicked off, grown, and he's taking over the world with. So, exploring Queensland's mine waste.
Sorry, Rick. Next. I'll try not to get my scarf on it. Yes, it is. Excellent. Is it still afternoon or is it the morning? Good morning. Thank you very much for being here today. I'm certainly really excited to give you an update on the work we've been doing. And I want to thank Kobie first off for giving his talk, because he set up a lot of the sites that I'm going to be talking about, and it's detail that I didn't include. So I'm thrilled that you went first. But before I kick off, I have to acknowledge the wonderful team of people who've been working on this work with me. I guess last time I probably stood in front of this audience in person was probably 2019 at the Digging Deeper event in December, and it was just me, and we were just kicking off this program. And I think Dominic, you and I were about to go in the field, or we had, I can't remember quite the order of events, but since then it's just exploded and the team has grown immensely, and we're about to sort of take on a couple of new postdocs too. So we're very excited by all of the work that's been going on and all of the interest in mine waste in Australia and indeed in Queensland. But, you know, in terms of the survey, we have to thank so many people there. So I'm just gonna, you know, I'm not gonna name you all, but you know who you are. You know, you've helped us tremendously on this journey, which is not over yet. So thank you very much to everybody. And if you wondered what My Watch was, because I did say that we were the My Watch team on that slide, but I didn't say it with my mouth. We're the Mine Waste Transformation through Characterisation team. So we're a new team at the BRC, and we're sort of working across, you know, I guess the life of mine, as it were. So we're looking at better or improving the environmental characterisation of future waste materials at the start, so at the exploration phase, but where they already exist, we're kind of looking at the opportunities to, you know, recharacterize, valorize, improve kind of the environmental outcomes of those materials moving forward. So today we're going to be sort of focusing in this part, and as I said, Kobie set me up really nicely for this talk, so that's awesome. But I just want to take a step back before we get going. So who saw this program on the television quite recently? So it was the Four Corners. It was well, I guess it was a program which featured critical metals. I never thought I'd be sitting there with my kids dinner time watching something about critical metals and minerals in Australia. And I thought it was fantastic because obviously globally, in Australia, well, not in Australia, obviously it still seems exotic to me, in Europe, in the Americas, everyone's talking about critical metals and critical minerals. And here we were, sort of TV program focused on exactly that and the opportunities we have here in Australia. So I guess just to show of hands, who saw the program? It was great. And obviously, Jeff, your colleague Alison was featured in that, which was really great to see GA's participation in the program. And when we look at sort of the opportunities we have in Australia, I know that obviously I joined online yesterday, so I know this was probably discussed in great detail, but certainly in Queensland specifically, there are many opportunities for these new economy or critical metals or minerals, whatever you want to call them. And I've just highlighted some of those there. But there was something to me that was missing, really, really bugged me in the ABC program. And that was the discussion of mine waste and its role in this whole conversation about sourcing new critical metals or minerals. And so I guess my team and I, we sort of put a piece together with the conversation just to sort of highlight where, you know, there are the opportunities. So I guess the Four Corners program touched on some of the challenges with managing mine waste materials, and Kobie's also mentioned about acid and metalliferous drainage. But what are the opportunities? And, you know, Kobie, again, he kind of touched on the fact that there are these opportunities, but in terms of new economy metals and minerals, there are heaps. And so I guess one of our former postdocs, she kind of sat down and put together a bit of a lit review, sort of thinking about what the main waste types might be for these new economy metals that we're searching for. So that's just kind of summarized there. I'm not going to dwell on it too much, but I guess what our program is looking at is, you know, where are these actually sited here in Queensland? And so if we just focus on tailings storage facilities, there was a paper that came out probably about last month. Not necessarily thrilled with the entirety of the paper, but it did certainly aim to pull together information regarding where, you know, the number of tailings storage facilities, for example, there are in Australia. And so we can see in Queensland, it identified 78 inactive tailings storage facilities and 80 active tailings storage facilities, which says to me, you know, we've characterized 23 sites, we've got another 22 planned, but we've certainly got a lot more to go. And this is just tailings storage facilities. That's not thinking about the waste rocks, the slags, and all the other metallurgical wastes. So there's a lot of material out there potentially to go and characterize and start this whole realm of secondary exploration to look for new economy metals and minerals, but also maybe some traditional commodities too. But, you know, this whole business about remining, repurposing, whatever you want to call it, it's a complicated thing, this business case development. And I know that Helen's been working really hard with a lot of different stakeholders in Queensland to sort of bring it together and sort of identify what the barriers and the challenges are, and to, you know, for government to kind of step in to help address those and, you know, make it easier, make it, you know, more of a logical process to actually go back to these sites. So I'm not really going to talk about those though. What I am going to talk about is this all fundamentally is underpinned by decent characterization at these sites. You have to know what's at the site. You need to know what's there. You need to know how it's there. You need to know how hard it's going to be to get it out. And also, what are you going to do with the new waste? And so for us and our team, these are probably the 4 key questions that we have when we think about characterization of these materials. And so I guess a bit more formally, this has been pulled together into our project objectives. And I know I've spoken about this before, but just for anyone who's not heard me talk about it yet, basically there's 4 things that we're trying to do in this 4-year project. And that's basically to find deposits of, or potential deposits of critical or new economy metals and minerals. We want to look at the relationship between the ore deposit geology and the mineralization style to, you know, what's actually contained in these waste materials, and also how these waste or these critical metals actually behave in these superficial environments. So once they're there, they're then subjected to, you know, they might be sitting there in low pH waters. We've obviously got quite a dynamic climate here. There's all sorts of things going on in those TSFs and those waste rock dumps that actually are very important to understanding what the future geometallurgical recovery could be. As Nathan was saying, you know, when he identified, or the team identified that the rare earths actually look like they're in those sulfate phases. So that obviously makes it very interesting in terms of thinking about, you know, simpler methods for that recovery. We're also looking at new methods for drill core analysis to actually identify these critical and new economy metals. I know that Olivia and Andrew will be talking about that a bit later on, so I'm not going to dwell too much on that. But also, you know, when we get there, we're trying to look at new mineral processing options for green recovery. And Nathan touched on that with rare earths, but there's a lot more to do than just the rare earths. And so the program is broken into 3 streams. I'm probably just going to talk about stream 1 today. And that's basically where we've been nipping around Queensland, sampling whatever we can get our hands on in terms of waste and characterizing it using geochemistry and mineralogy. And so this is typically what one of our programs looks like. Obviously, the time estimate there was something that we put together before COVID really happened, and then weather happened, and all sorts of things. So, you know, in essence, in an ideal situation, it should take, you know, from sampling to report about 6 to 9 months. But certainly when we get our samples, we put it through that geochem assay program. And we're not just assaying for 1 or 2 things, it's a full assay program. And that's the problem when we go back to the historic records. Only a few things were analysed. So in some cases, for some of our study sites, we've just been actually taking the samples that they've already collected in previous programs and re-assaying them to really get that full suite and that understanding of what's there. And for some sites, you know, when we find the commodity of interest, say we're after cobalt, what we'll do is we'll go through the assay data, we'll find the ones that really sing for cobalt, the top 10, and we'll do a really detailed mineralogical investigation to work out how that cobalt's there. What are the parameters of the minerals or the particles they're hosted in? What are those? Because those are the things that metallurgists need to know when they start sort of getting started on the mineral processing. And the final thing we need to know is how the element is actually, you know, in the mineral of interest. So that's why we use the laser ablation ICP-MS. And where we have the opportunity, where we have core, we like to try and get some chemical maps, some in situ chemical maps using techniques like micro-XRF. So we've done a fair bit of work already, which you can see here, and there's certainly a lot more planned, which is great. As I said, there's no shortage of waste to go and have a look at. But what I'm going to do now is just walk through basically some of the results for some of the key commodities that we've been looking at. So cobalt, you know, we kicked this program off looking at cobalt. It was the thing that we were chasing, you know, it was, you know, the motivation for this work. And what you're looking at there is a summary of the assay data. We can see that there's probably, you know, there's 5 key sites where we've got quite significant endowments of cobalt from our sampling. And if we look at that spatially, we can certainly see there's this concentration of those in the northwest, which is no real surprise. That's true. And certainly, you know, it looks like the IOCG type systems, the sediment hosted and the epigenetic coppers, they seem to be the things that actually have that cobalt in their waste, which is of interest to us. And in terms of where this is going forward, now we have a few, I mean, obviously when things sing for a particular thing, so, you know, these sites of sort of, you know, green light for us in terms of cobalt, we then move it to stream 2 and stream 3. So stream 2 is where we have our PhD students doing detailed research. And stream 3 is where we actually do metallurgical testing. So you know, members of this audience have probably heard a lot from Lauren Nichols at various GSQ meetings and so forth. And what she's already done is she's looking at the core at Capricorn Copper, and she's looking at the tailings, and she's also now tracking where the cobalt's actually going through the circuit. So we're really looking at this from ore to tails and what's actually happening to the cobalt from those different ore bodies and how it's actually reporting to the tails. And what you can see there is some of her MLA work that she just completed last week. And we can certainly see that in terms of our perception of how cobalt might have been, you know, deported in the tailings, our thoughts on that have changed radically. So it's not just cobalt in pyrite, and I definitely thought there was something carbonaceous going on there, but we also can see a whole host of different cobalt-bearing minerals. So we've got agglomerates of cobaltite, in kaolinite, we've, you know, there's catarite, which I don't think I've shown in this, but there's certainly a whole diversity of cobalt minerals. And that's actually just in the upper part of the historic tailings storage facility there. So that actually is a bit more akin to the Mammoth waste and not actually to the Esperanza South ore bodies, which are supposedly more endowed in cobalt. So that's obviously an interesting story unraveling there. So she's also been looking at using micro-XRF to really pull apart the relationship of the mineralization with cobalt in those different ore bodies. So that's work that's continuing. So that's really good to see. In terms of Rocklands, which was another site that I'd showed had good cobalt endowment, we actually have a collaboration going with JOGMEG at the minute. And what we're doing is we've been out to site and we've kind of collected a lot of the material that you're seeing there. And that's the cobalt distribution from various augured drill holes, if I can call it that. But certainly we can see that there's a bit of a hotspot of cobalt here. And so we're kind of unraveling the mineralogical hosts of the cobalt there. Certainly it does look like it's pyrite that's containing the cobalt, but I'm sure there's probably a bit more going on there. And certainly with cobalt and our collaboration, we're looking at, well, they've undertaken quite a fair bit of metallurgical testing to work out how we can actually recover that. So we're in the process now of sending them a bulk sample from this cobalt endowed area here, where they'll be applying the methodology they've developed to actually see what the recovery will be. And certainly for us, with our new postdoc, Thomas Jones, he'll be undertaking bioleaching work. So another thing that we are quite interested in is bioleaching. I suppose, you know, it was pointed out earlier, obviously, that bioleaching can not be time effective, but certainly from an environmental point of view, it can be sometimes a preferred methodology. So we want to have a look at what the indigenous bacteria are there, which Tom will be kickstarting, and see if we can harness those to actually drive bioleaching processes to recover the cobalt. Another site we've been working on is Osborne. Again, I showed that had quite high cobalt relative to the other sites that we'd sampled. And what you can see here is in September, there was a drilling campaign based on, I guess, a similar investigation to this and finding cobalt hotspots. And we took basically some bulk samples, which are now being worked on in collaboration with Cobalt Blue. So what we're doing now is we're putting it through, I guess, a metallurgical test work program where at first we're going to be subsampling and then sort of decomposing the pyrite using pyrolysis, and then we'll be leaching it and then testing sort of our cobalt recovery. Again, Cobalt Blue are working closely with Helen and the team to sort of work out what the opportunities are here in Queensland for their technology. And if theirs works, that would be great, because in a lot of places where we've been sort of seeing high cobalt, it's certainly been pyrite contained. And so that's a technology that works in that particular mineral. And I think most recently, perhaps one of the things that excited me a bit too much, I think I may have sent it around on the BRC WhatsApp chat group, but certainly some of the material that we collected in Great Australia with Emma up the back there, we had this opportunity to just sort of pop onto site and just do a bit of opportunistic sampling because we'd finished a different campaign a little early. We haven't done the most sampling. We do definitely need to go back and see in the cobalt numbers. I mean, some of the waste rock grab samples we took were sort of over 7,000 ppm cobalt. So we can see there's certainly something very significant going on just to the south of Cloncurry in terms of cobalt endowment. So that's something that requires further investigation. I certainly hope to go back to site to continue with our sampling campaign there. And so I guess, this is probably just highlighting some of the other sort of mines in the area that I think we should probably go back and do a bit more sampling at. And certainly, I guess when we look at the grades of cobalt that we've already measured in the waste, potentially there's an opportunity there to be a global leader for cobalt recovery from waste. There's certainly, some decent grades there. Now, if we just flip forward to copper, and I realise that time's pressing, and I have a number of slides yet, so I'm just going to cherry pick a few commodities. But certainly, obviously, just before morning tea, there was a discussion on the importance of copper. And I guess in many ways, sometimes it feels like it's forgotten, but certainly not by us. And some of the places that really sang, as Kobie sort of pointed out, was Mount Oxide for us, and also Upper Pindora, which was quite a small operation, former heap leach operation, which Dom and I sampled. But certainly we can see there's some very significant endowments of copper too. And if we look at that sort of spatially, we can see, obviously, again, we've got that concentration in the northwest, but we also actually have some hotspots starting to appear in other places. So around Mount Morgan, we didn't sample the tailings, but we did sample the slag. And certainly within that slag material, we're seeing a bit of a kick of copper. And also up here at Balgammon too, but I'm going to let Olivia drill down on that a bit later on in her talk. And in terms of our plans for copper, certainly the spent heap leach material is a super fascinating waste stream. And if you think about the opportunities to actually valorize that material, we could develop some or a valorization process or pathway or flow sheet here in Australia, but there's so many obviously similar spent heap leach deposits over in South America. So it'd be nice to sort of actually get cracking in terms of thinking about what we can do with this material to then transfer that flow sheet to other parts of the world. But certainly we did have a PhD student who'd started work on this and unfortunately couldn't continue, but we're certainly looking to get another student who's going to start towards the end of the year to pick up where she left off. I guess the opportunities we have here is that we have spent heap leach material. It's got the copper, it's got cobalt, they could be recovered. As Corey pointed out, we have the opportunity there to valorize the rest of the waste through looking at, road base. There's also an opportunity there for tailings sand, if I can call it that. And certainly at Mount Oxide, we've taken some bulk samples and we'd like to continue with our stream 3 work and actually do some hydromet tests to see if we can recover both the copper and the cobalt from those materials. I'm going to skip past a few of these, but certainly I'm happy to make this presentation available if anyone's interested in looking at some of the data. But I'm going to just hover on vanadium for a sec, because obviously vanadium is something that's been increasingly discussed as this program's evolved. And we've obviously assayed for it in our suites. And so overall, we can see that for the most part, the vanadium hasn't really sung in our materials, except for when we started to sample some of the coal combustion materials that we've collected just down in southeast Brisbane. And so I guess that's what I'm showing you here. We've got a bit of an endowment here at Swanbank, which we sampled the ash dams there just in March. And so we're seeing that could be potentially interesting. And I guess what I thought was interesting was that also correlated with scandium, which obviously you heard about yesterday from Katerina Savinova. So I guess in terms of what we should be doing there, thinking about the coal combustion products is, a bit more work. So I suppose you may or may not have noticed that we have, in terms of sample numbers, not so many yet from Tarong. We went out once for a couple of days, and we weren't actually able to sample below the upper 1.5 meters. So we've got an opportunity now to go back and actually sample some of the deeper material and do some more sampling to work out, if there is actually a significant endowment of vanadium, scandium, and rare earth elements in these materials. And the same thing here at Swanbank. We've obviously done our assay campaign, but now we're just waiting for our mineralogy to actually confirm which the hosts are. So we've got things like mullite in there, for example, and various other oxides. But actually, what is the host? and what then could the metallurgical opportunities do for that recovery. So stay tuned on that one. Indium, definitely not going to dwell on it because Olivia is going to be talking about that, but certainly, you know, a bit of a spoiler alert there. Tungsten you've heard about from Kobie and others, so I'm not going to dwell too much again on that one, only to say that it also looks like we've got a bit of a kick of tungsten here at Mount Morgan, which could be something to consider when we think about some of the reuse opportunities for the slag. Yeah, I guess I'm going to linger on this one a little. So tin is here. And I guess there's no surprise. There's tin in the tin mine waste. No surprises there. But I think some of the other things that really stood out though was what else could you do with this material? So I guess at Mount Garnet, and you have to note that the samples that we chose for mineralogy here are sort of skewed towards the thing that we were chasing at first. So at Mount Garnet, we were chasing indium because it's well known that obviously Balgammon material was processed at Mount Garnet. So we thought, oh, great, we'll find indium there. So we were kind of biasing our mineralogy there towards the sulfides. But certainly there's a lot of cassiterite remaining in these materials too. But what it does highlight is there's a lot of pyrite there. And obviously it's a site where there's, you know, and it's probably fair to say, Kobie, it's a site where there's AMD issues. So, you know, we've talked a little bit about informally about some of the acid deficits that we have potentially in the state and other opportunities to actually valorize these mine waste features to actually produce acid, which can then be used in other metallurgical processing. And for us, when we looked at the mineral chemistry of this pyrite, it was pretty boring, I have to say. So we were kind of a bit sad, but also like, well, actually, you need acid, we could oxidize this to make acid. Maybe this is actually a potential reuse opportunity for the Mount Garnet materials. And similarly with Herberton. Now, it is a site that has been rehabilitated, which is fair to say, Kobie. There's certainly a clay cap on there. But if you actually went back to the site, I think there are, and you know, again, fair to say, Kobie, there's some AMD issues associated with Herberton. But if you went back and you reprocessed, removed the cassiterite, maybe the rest of the material that's left over could be a prime candidate for tailings sands, which one of our former colleagues, Artem Golev, was having a bit of a look at this data and thought, yeah, actually this could be quite reasonable. So it's not just the recovery of those new economy metals or those critical metals, there's actually those other opportunities too. And that's why we need to think about what to do with the future waste. And I mentioned those 4 key points a little while ago. Now, maybe I'll just finish here because I'm on 21 minutes and I've just seen Helen stand up, sorry. Okay. That was all right for a bit of waste rock, I think we can all agree. So we were kind of out sampling with Kobie, and yes, we didn't see any crocodiles. I was a bit disappointed actually, because we could have cracked into the tailings a bit more. But certainly, you know, in terms of gold hotspots, Horn Island for the win there. And it's actually really important to point that out, because if we look at actually the acid-base accounting properties of the materials that we sampled, and I hope the resolution of that's okay, you can see that, you know, if this is the dam wall here is shown in the, I guess, the golden circles. But you can see that on this Ficklin plot of NAG pH against sort of the summation of 6 key metals, you can see that, you know, the dam wall material actually plots in the high acid, high metal to the extreme metal fields. I mean, okay, there are some that don't, but there are definitely some that do. And if we think about the grade of gold here, then perhaps there is that opportunity for that environmental de-risking, because, you know, a lot of this material is reactive, will generate AMD. Kobie's pointed out the environmental sensitivity of this site. So it's worth kind of thinking about, you know, it's worth remembering that there's sort of an environmental aspect here of de-risking, as well as sort of making it a few bucks on the side. And Mount Morgan is a site that we've just finished looking at. And we were looking at the slag, so I was really happy because I love slag, and it was the first slag site that we looked at. The red oxide slag is really important because underneath the red oxide zone, and I think this is right, is where one of the highest grades of gold occurs in the tailings. And so they were very keen to understand, you know, what potential value could be in the tailings sitting above it. And unfortunately, the most valuable slag actually seemed to be in this bridge area here, which they call it on site. So I've sort of adopted the same nomenclature. But certainly the gold grades here were a bit better than they were over there. But in terms of, I guess, the general properties of the slag, what we can see is it's slow cooled, we've got pyroxene phases, we've got clinopyroxene, I should say, olivines, and the sulfides, which look like they're the main hosts of, you know, anything that's kind of been shown to be of interest. But the actual processing costs of that might be insurmountable. So perhaps there's an opportunity there to consider this for aggregate or concrete, which was previously considered by carbine resources. But if that was something that one was going to do, of course, they need full environmental characterization before proceeding with that type of approach. Now, my husband talked to you extensively about rare earth elements, so maybe I'll just leave it there. But just to say, we've also had a bit of a look beyond Mary Kathleen, which obviously was the winner for us in terms of rare earths. But we also had some interesting sniffs from Balgammon, which Olivia might touch upon, but certainly even at places like Wathen-Camp, even at Phosphate Hill, where we're looking at the slimes and the phosphogypsums. And you know, in terms of like mineralogical host, this was by far the most diverse of all the wastes, you know, in terms of where those different rare earths were sitting. Definitely seems like there's a north-south corridor of rare earth endowment here. And there's certainly some endowment in the coal combustion products that we've sampled thus far. So I guess we probably thought there would be, but it's nice to actually see some numbers actually being put to that. So I guess I tried to summarize what I thought some reuse options could be, given that the talk was titled reuse options. So I guess, you know, you can see that there's some things that are still under investigation. So we're still kind of completing our mineralogical assessments. We've got back all the assay, but now we're in the mineralogy and the mineral chemistry phase. But for other things, you know, we're kind of thinking about, you know, we've got a couple of things that have moved to stream 2, which you've heard about and we'll hear about from the students. And it's great to actually partner with the METS companies to actually look at what that repurposing or reprocessing opportunities could be, like Cobalt Blue and JogMeg. Lots more opportunities in terms of thinking about other processing technologies. And so our former postdoc, Anne Whitworth, wrote a couple of papers sort of summarizing some of the new opportunities that are out there. So if you're interested, you can download those papers. So that's, I guess, thinking about the unconventional, the upcoming methods to actually recover critical metals from mine wastes. And there's, you know, there's a whole bunch of reports and presentations that sit behind the detail of everything that I've presented in summary today. So if you're interested, get in touch and we can certainly make those available. I want to just say that this is a growing collaboration. It's extraordinary. When I started in mine waste many years ago, I can't remember how many years now, but certainly it was so hard to get people excited about mine waste. And now we're in this position where we've got, kickstarted by Helen and her team, we've got the whole of Australia now wanting to know what's in their waste. So for someone like me, this just feels like a dream come true. So we've got New South Wales, they're sort of soon to kick up a program next month where I think they'll look at 20 sites, Northern Territories 3, GSA, they're sort of starting their journey. And Jeff, of course, from Geoscience Australia, they've also commissioned a project soon after, well, actually, I guess it's about this time last year. So it's just fantastic. The support from companies, state governments, I really think we could do something different with our waste as we move forward. So I will leave it there. Just want to say thank you very much to everyone for listening. I know I talk too much and I don't know why I always think 46 slides can be done in 18 minutes. Obviously it can't, it's 26 minutes. So if you've got any questions or comments, please, if there's time, ask me. If not, email me or just come and find me in the lunch break. So thank you for your attention. Sorry.
It's okay. I knew you would go over. It's fine. Now, let's take one question for Anita if we've got one, but we are now cutting into Olivia's time. And Evan is a strict timekeeper.
Well, he's not going to be putting me on his Christmas card list, is he? Let's explain that one.
Do we have any questions for Anita? I know that we are already chasing companies in the crowd to, you know, like the new fetch.
Thank you for the talk. It's really great to see that there are so many critical minerals in all of these waste. My question is, what about, usually in the waste goes also what we don't want, the deleterious elements. Did you analyze for this? How is that playing into the game?
Yeah, we have analysed for them. I haven't shared that data in this talk, but no, we certainly do. What I would love to see though is that for some people and their lists of what they consider to be critical, things like cadmium and arsenic previously, well, don't want that in the waste. Now it's like, great, it's on the list, bring it. So I guess we've kind of seen this transition of things that were once deleterious now falling into that category of being sought after. So in one regard, kind of nice to see that in terms of driving remediation. But yeah, we have analysed for those, yeah.
All right, I'm going to bring Olivia up to continue. Oh no,
it's Andrew.
Sorry, it's Andrew. Yeah.
I was really worried when you said I'd cut into Olivia's time. I was like, oh,
well,
really stuffed up.
Oh, there is a question online Anita, so what I might do is if you hang out here, we can type an answer to the question
you're right.
online, or we can actually answer it. Let's answer it while Andrew's getting his microphone up. Another Prue Osborne, because everybody's Prue Osborne online these days. Do you consider chemical properties of minerals more important than mineral structures and their physical properties for extraction of critical metals? And it's Valeria.
Okay, thank you. Testing. So thanks for the invitation and the opportunity to speak to you today about LIBS, an emerging new analytical technology for the analysis of all sorts of materials, but today we're going to be focused specifically on the analysis of geomaterials. As a disclaimer, I'm from SCIAPS. We're a manufacturer of field portable equipment, including a handheld LIBS, but I'm going to discuss today more generally the LIBS technique, and we'll make mention of some of my complementary pseudo-competitors, I guess, that are more in the installed benchtop and in situ core scanning environment. So LIBS, you may have heard of it before. It's an analytical technique. The acronym stands for Laser-Induced Breakdown Spectroscopy. Okay, we're going to talk a little bit today about the approach to the analysis of geomaterials, and in particular, different ways that we can actually extract value from the data that they generate, both qualitatively and quantitatively. So it's an optical technique. It's actually a form of optical emission, an atomic emission spectroscopy technique. I've got a little typo up there. The advantages, a lot of people would say at the moment that, some of the advantages are really in the light element space. Certainly the analysis of lithium is fairly interesting for a lot of people at the moment. But there's a lot of other stuff, including carbon, which is probably the key element for us in some of our key markets for alloy identification and carbon analysis. And but also fluorine. It'll do many elements that you can do with other techniques, and is both complementary to those techniques and also creates opportunities that don't exist with a lot of other techniques. So it's a very fast technique. We are using typically pulsed lasers here. We can generate a spectral data set in parts of a second. So we can acquire, stacked spectra, a lot of data over a large spatial area, and then agglomerate those data to look at digital images of the elemental distribution and individual spectral information at each of those locations. So it is spatially precise, as I'm saying here. And the laser spot size does really have a lot of relevance to the type of work you're doing. Certainly, we probably don't go down to the same sort of scales with LIBS typically as things like an electron probe, which might be in 1 to 5 or 10 microns max, and then certainly laser ablation these days. We're getting down into quite small spot sizes of maybe 10 microns up to 50 on an older system, and we're right at that sort of scale. We're at about 50 to several hundred microns for some of the larger standoff systems. So we're using an optical technique, as I said, using a pulsed laser. We're focusing that beam down through to deliver energy to a sample interface. And at that sample interface, with the laser energy, we generate a plasma. Now, with our systems, it's very important with this technique to take an appropriate time slice in the response that we're trying to measure from the cooling of that plasma. Now, we use an optical spectrometer system to bring that light through onto a detector array. Typically, these detectors are just a CCD detector array, and the actual bandwidth of your detector array will determine how much data you capture in one single grab. So we can measure all sorts of different materials, including liquids, okay? But the coupling of the laser with the sample is very important, and certainly the methodology around sampling liquids is very important in terms of the way that you ensure that you're not getting splashback onto the optics, that type of stuff. So like I said, this is an event that occurs over time. So we're looking at a specific time slice, but essentially we are wanting to look at the information that relates to the atomic makeup of the material that we're looking at. Certainly there's other techniques that are associated with this. LAMIS, for example, which is a much longer time domain, time slice that we take, which could talk to you about things like the molecular structures that are at play in the material that you're looking at. So the other thing that we can do, and there's a lot of interest in at the moment with LIBS spectra, is generating this very data-rich geochemical fingerprint for mineral ID material classification, provenance mapping. There's a lot of applications about the unique spectral fingerprint that these devices and this technique can generate. This is just another representation showing the optimal time slice we're wanting to take is actually when that plasma is cooling and all of the electrons that are in the shells of the atoms that we're looking at in that sample are coming back to their steady state. They're emitting photons that we're measuring in a spectral data set. This is an example of the data quality that you get basically at the earlier stages in the plasma formation compared to that time slice that I showed up there, where there's much better signal to noise, much clearer spectral data. So GeoLIBS, as it's been termed, the analysis of geological materials with LIBS, has been used extensively in a wide range of geological and environmental materials over many years now. Certainly commercially, these products that do LIBS analysis have only been commercially available for probably less than 10 years. And certainly with the handheld system, SCIAPS was a pioneer in this space, and we released our first handheld LIBS about 7 or 8 years ago. So the ability to obtain data across a spectral range from about 190 or 200 to 900 nanometers is kind of critical if you want to get a comprehensive geochemical data set. So those sorts of bandwidths we achieve with a 3 spectrometer system that'll go from 190 out to 950. But other systems, some of the larger installed and benchtop systems, may even have broader bandwidths than that, using up to 4 spectrometers. So as I mentioned earlier, the laser spot size is different between different systems, and it can actually relate importantly to the ability to resolve different class within materials. If we're looking at geomaterials, certainly the grain size we're looking at does have a lot of relevance if you're trying to look at elemental distribution to the laser spot size you're using. And that's similar, I guess, to some other microanalytical techniques. What we're seeing as well in these microanalytical techniques is generally the concentration or the amplification of geochemical signatures to within the individual mineral class or zones within those minerals, as some of the laser ablation stuff showed pretty clearly. So the laser wavelength and power do relate to data quality, as does the geometry of the system. So some of these systems are standoff, termed standoff LIBS. For example, the Mars rover uses a standoff LIBS. That's optimal field of view on the actual system that it's using could be several meters in a Martian atmosphere. Our handheld unit does require contact with the sample to allow us to both purge using an argon or helium gas to improve the spectral data quality, to remove atmospheric gases, which could potentially be misconstrued as part of the sample within the plasma formation. So certainly if we're trying to do things like carbon analysis, nitrogen, these oxygen, these things, we don't want the atmospheric gases contaminating our analytical data. This is an example, I guess, of the kind of the systems from lab through to a field lab or in situ material analysis approach to the handheld devices here. And you can see there's quite a bit of variation. This unit's from Applied Spectra. These guys are L-emission, and we're SCIAPS here. These guys here at Applied Spectra have also the capability to do simultaneous laser ablation and LIBS, which I think is really powerful in terms of creating a baseline data set that we can work with in terms of calibration. So all of these devices, I guess, are complementary and form an ecosystem, which also fits in with other microanalytical and bulk geochemical techniques. That's what a LIBS spectrum looks like, and they do get a little bit busier than that as well. So certainly, I think Nathan mentioned earlier, some challenges with LIBS analysis in rare earths, for example. Obviously, the heavier the element you get, the more potential responses that you can see in a spectral data set like this. And as you can also see, there's a lot of peaks, a lot of features in here. This allows us to get these characteristic geochemical fingerprints, but it's also really important that you have good spectral resolution in these regions where we have a lot going on, if you want to be able to resolve interferences between neighboring peaks. So there are, I guess, a lot of potential interference locations here between coincident elements in different matrix types. And that does create challenges for universality of calibrations, for example. We typically use a univariate, but are moving more so towards looking at multivariate techniques for quantitative analysis to avoid some of these potential conflicts and create more dynamic calibrations rather than the quite rigid empirical approach. One interesting thing with the handheld LIBS is as it being a laser, you don't have the same kind of inherent radiation risk that you would with a portable XRF. So for field sampling of small chips of materials, you can safely hold a sample in your hand like that and not have any worry about ionizing radiation. Okay, the systems that we use on our latest Z903, which is again very, very similar to the Z300 that the guys at SMI have just bought. We're using an almost identical analytical system that we use approximately a 6 millijoule, 1 to 2 nanosecond pulsed laser. Some of those larger systems, including the Curiosity, may run femtosecond lasers as well. And the repetition rate that we're running here at 10 to 50 hertz, they can run up to 1,000 hertz. Okay, so they're quite quick in terms of the type of analysis they're doing. And then after each of those laser pulses, we use that time slice at several milliseconds to optimize the response. The system we're using uses a shortwave infrared laser, so it's invisible, 1064 nanometer. And then, like I said, our laser spot size is 50 microns. But in the geometry that we're working with a sample, that would typically relate to something like a 70 to 90 micron sample area. And it's very much a surficial technique as well. So when we're looking at materials, we have to consider things like if you're working with mounts that have already been coated with carbon for SEM work, certainly you don't want to be doing carbonate analysis without potentially setting up a regime of cleaning shots where you can take non-analytical shots as part of the routine and clean that surface. So you're analyzing fresh rock. The ability with these systems, most of them have either X, Y, Z stages, or they have the ability to scan the laser across the sample. We've got some examples of what some of the other larger systems will generate in terms of a raster pattern, but here's some of the little typical raster patterns that we can do. We can do large area scans, and by large area with the handheld, that's only a 2 millimeter by 2 millimeter square, so it's fairly small field of view. We can mathematically stitch these images together. But in here, we're actually looking at, this is a homogenized material, and we're looking at a pattern there of 12 locations, 3 rows of 4. So that's like a 2 by 1.5 millimeter scan area. So the calibrations, as I mentioned before, using especially an empirical univariate approach, can be very matrix or even mineral specific. Okay, the LODs vary. Certainly we can test, or we can see almost every element in the periodic table with this technique using that spectral range. But the disclaimer, I guess, like some other elements with other plasma techniques, chlorine is fairly poor for us. But things like lithium, sodium, we might have LODs at 1 or 2 or 3 ppm, so very, very low. We're not, as you would with a laser ablation technique, basically ablating the sample and then entraining it and analyzing it through a mass spectrometer. We're just looking at the response from the plasma after we've ablated the sample. But that interaction, as you can see, is destructive. It's a very small crater that we generate, but it is a destructive method. So if we're looking at the way forward with this, some of the systems, I know Elemission now have a software package using a range of different approaches that we're also looking into with a couple of R&D projects for multivariate methods where we can actually in a first step classify the spectral data, and that allows us to get mineral IDs and that type of stuff out of the data. We have had a lot of success post-processing our data, but it's not an onboard capability for the handheld yet, but watch this space. So in terms of sample prep, with our unit, we do need to reconstitute or pelletize a pulverized or a particulate material. Okay, some of the other systems with being standoff, you can actually ablate a soil material fairly effectively without too much dust and issue with the optics. But typically we prefer to work with solids. So drill core, certainly sawn drill core is an ideal sample. Drill chips out of RC rather than the fines like you would maybe test with an XRF. We'd prefer to work with the chips. So it'd be more of something you would assist with logging of individual mineral locations rather than trying to get a bulk geochemical analysis, unless you're prepared to do that work and reconstitute a particulate sample. That's a good point here, actually. Surface contamination. So this being a surficial technique, if you've had geologists licking samples or just handling them, fondling materials, you definitely want to be able to clean that surface before, as per the carbon, because you will see things like sodium. If you're trying to do identification of albite or something like that, if you see sweat and skin cells, you're going to get carbon, you're going to get paper, you'll pick up calcium, titanium, all sorts of interesting stuff on the surface of the sample if you don't clean it first. Here's just a few comments around methods for field prep in particular, but ideally we would prefer with a handheld in particular to work with a solid material. Here's just a few more images of some ideal pulverized samples and some of the ablation marks. This is actually not one of our ablation marks. This is from the DET CRC site. We would work with commercially available field presses. There's a range of them. This is a reflex press. Certainly that's been used by some people even for improving field portable analysis with XRF, and is a perfect sample for use with a LIBS system. Quantitative analysis, as I said, is achieved using an algorithm development. We typically use relative intensity ratios to normalize pulse-to-pulse variability in the spectral data, where we have target elements in a numerator with matrix-forming elements, usually major element or even local spectrometer regions, to normalize the overall peak height fluctuation. And that allows us to get effective calibration curves, which generate quantitative data using the software on our instruments. And other systems similarly have their own approaches. Here's some examples though with some of the data improvements that can be caused by doing multivariate analysis on the data rather than a univariate approach. And we can see that allows us more elasticity in the breadth of the matrix types that we can expose those calibrations to and get reliable data. Certainly, if you really try and work on a specific mineral phase, you can get this kind of data using a univariate approach. But when you put real geological samples in front of things, they have a matrix variability in them that's inherent. But things like lithium, beryllium, boron, you can see we can achieve effective results for quantitative analysis. Here's a point, I think it was mentioned, certainly in critical minerals, certainly in some of the stuff we're talking about where fluorine can be an important thing, hard to analyze as well. We can actually get reasonably good performance on identification of fluorine in mineral samples. Our LODs are dependent on the purge gas. That's why I've put this up here, because there are some interferences caused by argon peak positions on some of the fluorine peak positions. So if you were trying to focus in on identification of fluorapatites or material that you're trying to look at in the field or in the lab, then you would consider using a helium purge gas rather than the argon, which is our standard. And that's some examples of the data quality improvement that you can get here. And these are some different concentrations of fluorine shown in the peaks. This is a fairly new area that we're working on with fluorine analysis, and also working in some unusual applications like fluorine in ski wax and fluorine in Teflon and non-stick coatings in consumer products. So here's some examples I wanted to put up on core scanning. Certainly, as I said, a sawn core with a flat surface is an ideal sample for LIBS. And this line scan is actually from another system that first adapted applied spectra system, which was actually designed to feed core through. And you can see we can either do spot analysis for individual mineral IDs or investigation, or we can actually just scan down and get overall change analysis on a broad range of different elements and potentially minerals in that core. And as I said, it's very quick. So this is some of the LIBS images that have been taken off that same study. And you can see here a much larger scan area that's possible when you use a standoff LIBS system. But here's iron and copper, looking at the distribution of these elements, very effective for microanalytical and elemental deportment work. And this is one of our systems compared to, obviously, this is Maya data, so it's about as good as you get in terms of resolution. So our stuff looks pretty pixelated. There's no smoothing applied to this. This is really just a pseudo color image applied to elemental distribution in a 2 mm by 2 mm area on a carbonate vein here. So we're looking at fairly specific parts of the sample, and certainly with our systems, you can then plot these data as well in things like iogas. You can look at multi-element associations that might be indicative of specific mineral phases as well quite quickly. Or you can tease the data out, look at individual spectral responses from parts of that location and achieve quantitative results on those parts of the sample. So for precious metals and things in particular where we have fairly inhomogeneous distribution and fairly small specks of materials, you can look at things that are quite specific around those individual locations and look even at things like gold chemistry, alloying in the gold, for example, for provenance. This has been employed across a lot of different minerals. We've currently just engaged with MDRU in a porphyry hydrothermal footprints mineral vectoring project. So this kind of stuff is going to come out, and we've certainly done quite a lot of work on the downstream data handling, which we're now putting into our PC-based software as well. And this is off a L emission system, so you can see the sort of resolution, but they can actually pick out individual specks of gold in these systems and then zoom in and look at the chemistry on those specific grains of gold. There was quite a lot of work done as well. Just go back here. In looking at this native gold spectra was taken on samples out of the Smithsonian collection, and they were able to, predictively identify provenance and location source of gold. Similar things have been done for conflict minerals as well. And here's the stuff I was talking about with our little tiny 2x2 millimeter guys that have been stitched together mathematically, looking at alteration around hydrothermal veins. And in this case, we're looking at the chlorite speciation of identifying the chlorites associated with mineralizing fluids versus barren hydrothermal fluids. So this is an exciting and powerful technology. It is a lot of data, and we're still grappling with how to get the most information that we can out of it. Certainly, it's something that has a place in most field programs. I think if you're using portable XRF already and you've got holes in your data, this is something that you can work with as well in the field or in the laboratory or on core. It's a highly complementary, and it's a different type of data, but it's also very powerful in terms of what the outcomes can be in the information that it provides. So the current advanced areas really sit around interpreting the spectral data, okay, and getting instantaneous mineral ID and mineral chemistry in one single grab is something that I think we're already achieving on some of the larger systems, and certainly we've been able to prove in post-processing with the handheld systems, and I think something that'll be on board in the next couple of years as a standard tool. So thank you very much for your time. I've got some acknowledgements and thanks up there too for people that have contributed.
Thanks very much, Andrew. And that is related to the whole mine waste story, because we're going to hear more
I'm just the
about
curtain raiser for Olivia. She's going to actually tell you some stuff you can really do with these things.
No, I think it's good, and it's really good to be able to see a tool like that we can use on gold. So does anybody have any questions? Yes.
Well, hang on. Andrew, great talk. Thanks very much. I missed what you were saying about the sampling. I think the answer was you can't do it on liquids or soils that easily at the moment. Is that correct?
No, you can certainly sample liquids. You just need an appropriate setup to do it. So we use a slightly different front end on the instrument when we're doing liquid analysis to avoid any kind of splashback onto the optics, okay, that we use with the standard setup. And for soils, typically a direct in situ measurement on a soil using our approach is a little bit trickier because we're right up against the sample, you know what I mean? And what happens when you fire the laser at a particulate material, we're heating up that plasmas at like 10 to 15,000 degrees Kelvin. So all of the air spaces between the particles expand very quickly, and the sample basically its density decreases. We get a poorer response based on that alone, but also we can affect the optical pathway on the instrument by putting dust and dirt all over the protective lens that's on the instrument.
So the follow-up question then is, based on what we heard this morning, is there any chance of measuring stable isotopes using this method?
There is examples of that. I know when I first started working with LIBS several years ago, Kurt Kaiser, who's no longer with us, he brought that to my attention. I said, mate, I've got my hands full just doing elemental stuff, so I don't want to even talk about isotopes. But it is definitely in the literature. LIBS has been used for isotopic work, and also things like this LAMIS technique, the longer time delay on the capture of the data. I've seen that used in things like carbon isotope differentiation in particular, for looking at things like plant communities and historical geobotanical studies on areas where they've been covered by forest or grassland. So yeah, there is definitely applications in LIBS for that. We don't personally, SCIAPS, we're not touching that just yet. Thank you.
All right. Thanks so much, Andrew. If you want to know more about how to apply LIBS on your field samples, Andrew will be here for lunch as well. Now, as he said, he's the curtain raiser for Olivia Mejias from SMI, who's going to continue the mine waste story. But of course, as you might have guessed, using LIBS to analyse indium samples from Balgan. Thanks, Olivia.
Okay. Thank you. But it's turned on. Okay. Can you hear me? Yes. Okay. Good morning. Good afternoon. I guess we are in the middle. Thank you, Helen and Ivan, for this opportunity to present today. This talk is based on my PhD research. I am in my last stage of my first year, so I'm very excited to show and share with you today part of my progress and some preliminary results, and of course using LIBS handheld. So as an outline, I will talk very quick about clean energy and indium. And before going to indium in northeast of Queensland mine waste, I want to talk about indium from ore deposit to mine waste environment, like an overview. So I guess it's very important when you want to study mine waste, understand as a reference or as a background, the primary ore, and hopefully some natural environment before contamination by mining. So this map shows the percentage of electricity in Australia in 2021, which came from wind and solar energy. However, by 2050, Australia and many countries must grow to 100%. So it's not just about to increase the use of low emission technologies, such as solar panels. It's also about we need some critical metals. So for example, the case of indium is an essential part of solar panel. So if we can also increase the use of this technology, but also decrease environmental issues is a big goal. So one of the idea is recovery indium from mine waste. So you can achieve both point of view. And we know that Australia, in terms of solar, is the best solar resource. But also now, and especially in this workshop, we know Australia is also a high potential in indium too. So before going to talk about indium in ore deposit and mine waste environment, I will use some information that I recopilate in my literature review, and also this is in a preparation and correction stage for publish very soon a paper. So the idea was, okay, maybe if not just recopilate or collate information as a writing paper, also collect numbers. So the idea was indium concentration from different minerals and different ore deposits and different environments. The idea was to collect. So now this paper we have about 400 of data about indium. So we can have some overview. So one of the information based on this data collection was also update the quantification of resources of indium, because one of the last information came from 2016 from Werner, but from that year to now, there is some new updated in terms of quantification of indium. So again, scan is the #1 in terms of quantification of indium, but also volcanic massive sulfide and epithermal too. And this map shows part of the data, all the data collection in terms of mineral chemistry. With this information, it was enabled to cover 25 countries and more than 113 mine sites with different information of indium. This map just shows the average, considering all the minerals that we can identify. And you can see most of the cases in terms of research is focused on epithermal, also Australia. And in case of IOCG, it's very scarce information, just one article in Peru, and also some information in Australia, but no official published. So now when you see some paper or articles, this is just an example in 2020, and all the paper connected with this specific paper, most of the cases you can see always the same list: sphalerite, chalcopyrite, esthanite, and cassiterite, like the high minerals which host indium. So one of my question was, okay, it's sulfide and oxide, but we have more opportunities in terms of to achieve zero waste and try to understand if indium is housed in another groups. So after this data collection, we can not just identify sulfide and oxide, also silicate, arsenate, hydroxide, carbonate, sulfur salt. So it's a huge number of group of mineral which can host indium in interesting concentration. But also in the case of hydroxide and carbonate, even though show interesting percentage, is a really scarce information worldwide. It's just a few number of paper in total. So now if we consider all the data, there are at least 44 indium-bearing minerals identified. If also we consider indium minerals such as rockosite and others, it's around 45. So it's a really huge list. It's not just sphalerite, esthanite, cassiterite. And also a lot of lack and gap in terms of submergent environment. So if we organize the data in terms of the maximum concentration, of course, sphalerite is the number one. One of the articles, the maximum concentration identified worldwide is almost 150,000 ppm, and followed by tetrahydrite group, esthanite group, chalcopyrite, cassiterite, pyrite, but also other minerals, for example, garnet. There is an article in China focused on scan, and it's very interesting, the concentration of ppm of indium in this kind of silicate. So again, it's important in terms of have more information about the opportunities to recover indium, not just from sulfide and oxide. So one of the minerals which is repeated in each article is sphalerite. So in that case, the data collection is about 130 data. So one of the questions was, okay, if I have the information in terms of the original resource or the original source, the primary, maybe I can identify which kind of ore deposit can have the highest indium concentration from sphalerite. So one of the patterns repeated in different articles is porphyry, but not all the porphyry, tin and tungsten porphyry, and not the porphyry itself is specifically veins related to the porphyry. In the case of epithermal, most of the case is at intermediate sulfidation epithermal, not all of them. And the case of skarn is proximate copper part or zone. And in the case of granite related is specifically infill sulfide massive texture, and of course, also volcanic massive sulfate. So if you have information about what was the original source of your mine waste, you maybe can target and go to exploration of indium with a high opportunity to find indium enriched sphalerite in this kind of specific ore deposit. Because in terms of SEDEX or another sedimentary ore deposit, as an average in terms of sphalerite, indium in sphalerite is less than 200 ppm. So it's a really high difference if you compare with this kind of ore deposit. So now if we move to environment, the idea to create this diagram is to show in a friendly way how is the indium concentration in different environments. So it's not just about indium in ore deposit, as I already showed, it's indium in natural environment. So how is the range or approximately in lake sediment and soil and stream, river, in geothermal water, for example, you can see in this kind of type of aqua system is more higher the concentration, or in coastal seawater, sea sediment, etc. So all this information is worldwide, different countries. It's not too much, but it's enough to understand at least how is the range of indium in natural system. So we can compare now with some indium range from mine waste. So for example, in tailings leachate, waste rock, sulfidic, or waste rock more oxidizes, a stream affected by acid mining drainage, and also some sediment and water affected by smelting processing. So now we have some comparison. We can understand how is the potential of indium if we calculate just an average as a baseline of uncontaminated environment in waters or aqueous system. And if we compare with tailing leachate, indium can be up around 55,000 times higher in this kind of system, or also about 100,000 times higher if the water was affected by smelting. And in the case of solid mine, the average calculated was 0.4. So it's around in tailings, waste rock, and also sediment affected by smelting around 120 times higher. So now we can maybe understand indium is not just a high potential in solid tailings, also could be in waters. And also we can compare in terms of baseline of background, in terms of number, not just crustal abundance. So in terms of quantification of indium is a really scarce information. Most of the indium is calculated from concentrate, but if we can consider really indium estimate from, for example, waste rock or tailing, there is 3 examples from Germany, Namibia, and Iran. It's around 1,400 ppm. So one of the questions when you can see indium in aqua system and also in tailings, if maybe indium has mobility is one of the questions, and it's still no clear understanding. So after to overlap a few quantity of articles, most of the paper show or expect that could be indium free, the +3, in acidic condition. So maybe for this reason in tailings, leachate, and also in water affected by smelting, we can find high concentration of indium. And also some experiments suggest that indium could be precipitate, co-precipitate, or absorbed in hydroxide minerals, but this is still not clear. But some of this information could be maybe be related with this some paper. And also some minerals that are already assessed from my waste is again repeated some sulfide, but also some interesting concentration in carbonate and also goethite. So now indium in our East Queensland mine waste. So this is some of numbers, it's a huge opportunity. And we already know that at least mine waste, which is related to volcanic massive sulfide, epithermal, granite related, could be a high potential to find indium. So this is just part of some examples related to mine site that after to review some drill cores, so thank you to Department of Resources and Kobie, so we can find some targets and also some articles, a little bit old, but very important, from Moltavon area, and also from German mine site, and of course, Vladimir. So this is one of the examples from 2003, 2006, and since 2016, Fox and Parbhakar-Fox also include more information about indium. So in the case of these 2 more old articles, in terms of concentration of indium from waste rock and tailings, and also some tailings leachate is a really high, but we don't have information about microanalytical techniques. So we don't know really in these 2 examples, where is indium and where is the concentration in the minerals. But in the case of Vladimir, we have some information about the list of the potential minerals and more techniques, and also some correlation. For example, this is a PCA, and we can see some relationship between chalcopyrite, sphalerite, and not just indium. Maybe it's not clear, but this is indium, silver, and cadmium, again, related to sphalerite and chalcopyrite. And for this specific study, in part of my project, the idea was not only we want to include laser ablation or microprobe, also new emergent technologies such as handheld LIBS. So one of the idea, as Andrew mentioned, was to use clean surface of drill cores. So the idea was to use some samples from Valgaemon, from our primary deposit as a reference, and after to move into mine waste samples. So after to clean the surface and to check this flat, the idea was just with visual identification. Okay, I want to assess chalcopyrite, for example, pyrite, arsenopyrite in different texture, and try to recognize if LIBS could be recognized different intensity in all these mineral examples. So one of the, after to select different areas, in total was 133, we choose this app, GeoChem Pro, and we explore heat maps because the LIBS could recognize and assess very fast indium, but we face a specific challenge that indium, even though Valgaemon is a high resources of indium, indium is still a trace element. So sometimes this software can recognize like a high abundance relative in the case of trace element or critical metals. So one of the idea was explore all the raw data and work with MATLAB and create a specific code and programming method focused on indium. So the idea was compile all the information because it's really big number of files and start to focus on indium. Indium has different emission line. So based on literature review and understand where is the option to indium can host, try to select a specific emission line that can show in the better way which mineral could host high intensities of indium. And also apply the same workflow, but for another element and try to connect the original mineral, but for each shot, because we work with this area is 256 shots. So after that, and also to create a new file where we can connect each shot with each sample, each texture, each mineral, and also the intensity for 59 elements. This is a future work, but we can recognize in terms of intensity that chalcopyrite is one of the minerals that would be host or expected host high concentration of indium. And also how is this distribution in different textures. So one of the ideas, one of the steps now is apply in mine waste. We already ran one sample. So again, it's chalcopyrite, one of the minerals which hosts high intensities of indium, but you can see if we compare with the ore primary, is in less quantity of intensity. So now one of the next steps is to take this fieldwork and to recognize like an scope what Mansai could be a high potential to sampling and also quantify, include multi-scale mineralogical characterization and try to quantify which mineral could host a concentration of indium, but also quantify the result by LIBS using another microanalytical techniques. And of course, try to understand by geochemical modeling what is the mobility of indium, because it's a really scarce information about that. And with mineralogical, geochemical information, try to build geometallurgical properties that we can give us some opportunity to recover indium from mine waste in the northeast of Queensland. So thank you again to the Department of Resources, Martin Valenzuela for his collaboration and LIBS programming method, Andrew Friend and Emma for helping with the waste rock samples too, of course. So that is, thank you so much.
Thanks, Olivia. That was really good and a good follow-on from Andrew's talk as well. Do we have any questions in the audience for Olivia about mine waste at Valgaemon or around the world? I think indium is one of those things that's still nobody quite, you know, it's not familiar to us.
No.
So it's
I was interested to see that Sarcheshma in Iran has high
Yeah.
indium and a porphyry copper
Yeah.
deposit. Was there any more details on that about how it occurs or why?
Maybe one of the reasons more than the porphyry itself was that all this waste rock is high in sulfide. So when you have a high concentration of sulfide and sphalerite, the opportunity to have high concentration of indium could be high. So maybe it's the reason specifically.
I think the more we analyze, the more we'll find, right? Yeah. Okay, thanks very
Okay,
much,
thank
Olivia.
you.
And now we'll welcome Avish Kumar from James Cook University, who's going to continue the indium and Balgaman story, but this time from the aspect of hard rocks and mineral petrogenesis. Thanks very much, Avish.
Hello, everyone. I'm Avish Kumar, and I'm a final year geology PhD student at James Cook University. And I'd like to thank Olivia for actually introducing the topic on indium mineralization. And I'll be talking on indium mineralization in the Herberton mineral field. My supervisors are Ivan Stanislav and Paul Dex, and I have two collaborators, Henrietta Keddy from QUT and Laura Martin from UWA, and I'd like to thank Geological Survey of Queensland for funding this project. So this is just an overview of what we'll go through. So just the regional geology and deposit scale geology, indium distribution in the Balgaman and Isabel deposits, timing of indium mineralization, and the role that the granites play during their deposit, right? So the geology, so here's the legend on this side. The oldest unit is the Hodgkinson's formation, and you can see the workings for all the metals that I've plotted in here. And this Hodgkinson's formation gets intruded by the Kennedy Igneous Association. And the suit that is actually carrying most of the metal is the O'Brien's Creek supersuit. And at the site, the Balgaman and Isabel, they are the Jumna granite and the Herberton Hill granite. Now this gets also intruded by the Almaden supersuit, and which is the Kalunga granodiorite. Now Kalunga granodiorite is the more mafic end member of the granites that occur within the Herberton mineral field. And then we have a post mineralization unit, which is the Udan supersuit. And at the site, it is the Watson Vale granite. So we have two suits of, two groups of volcanic unit. One of them is the featherweight volcanics up in the northwest. And then at the site, we have the Coolmoon group, which is over here, here, and here. And this is the group that we're interested in. And they are the Slaughter Creek volcanics, and they have two phases. One of them is the intrusive phase, which basically consists of porphyry dikes, and the extrusive phase, which consists of more or less rhyolitic flows and pyroclastics. So getting really into the geology of the Balgaman deposit, so you have the Hodgkinson's meta sediment, and it roughly dips around 8 to 10 degrees southwest. And as you go towards the intrusion, the dip increases to about 40 to 30 degrees. And that is intruded by the Una porphyry. And the Una porphyry is faulted, and that's what carries the tin mineralization in this deposit. And that again is sort of cross-cut by the Slaughter Creek volcanics, and they're mostly porphyries. So establishing the timing of sulfide mineralization. So we know that the Una porphyry is early phase of tin mineralization, and that is cross-cut by the sulfide veining. And we dated the zircons from the Una porphyry to about 330 million years. And at the site, when we were mapping, we saw quartz feldspar porphyry dikes of the Slaughter Creek volcanics that cross-cuts almost everything, but they leave behind a trail of sulfide alteration, right? And these quartz feldspar porphyry dike were dated to about 290 million years. The zircons were dated. So a bit more on the mineral paragenesis from Belgamen. So this is the Una porphyry that is chloride altered, but is overprinted by cassiterite, as you can see over here. And if you look at this cassiterite in the massive sulfides that occur in Belgamen deposit, so the cassiterite actually starts to alter into sternite. And with it, there's also some sphalerite. We'll look at this image again later on. And this is actually a very interesting texture that occurs mostly in the deeper sections of the Una porphyry and in the Belgamen deposit. What it is, it's basically a chalcopyrite with an exolution of pyrrhotite along the grain boundaries of chalcopyrite. You can actually use that texture to estimate the temperature of your deposit, but we will not get into that in this talk. We'll estimate the temperature through other means. And within it, there's inclusions of sphalerite, and they're quite rich in indium. Right, so the geology of the Isabel deposit. So the oldest unit is the Hodgkinson's metasediment, but you have the Herberton Hill granite that has a lot of working for tin mineralization. And the deposit is hosted within the abrasiated metasediment and volcanics. And we try to establish the timing of this deposit by dating the porphyry dike that cross-cuts the deposit, and we dated it to about 290 million years. And we dated the cassiterite. So this is actually an early cassiterite. You can look at the texture of it. It's slightly porous. It's chalcopyrite has started to sort of replace it. And we dated it to about 314 million years. And it's quite similar to what we saw in Belgamen. Right, so I'm really into the veins that we see in Isabel. So we have two types of veins, and one of them is a sphalerite vein with the inclusions of chalcopyrite. And this sphalerite vein is cross-cut by chalcopyrite and pyrrhotite. And they are quite thin veins that cross-cuts these sort of large veins. And the other type of vein we have is the galena and sphalerite. The vein is composed of galena and sphalerite. And within it, we start to see sternite that occurs either in this sphalerite or in the along the grain boundaries of sphalerite and galena. And sternite is where basically a lot of indium is also sitting. So the mineral maps, so these are from our microprobe analysis. So this is iron, indium, copper, and tin. So I'll quickly go over the tin one before I'll get into the others. That is because the tin one highlights the occurrence of the sternite minerals. And if you go from the tin to the indium, you can start to see most of the sternites have high quantity of indium. So from the iron maps, you can see that sphalerite occurs as inclusion in the massive sulfide. And within it, the sphalerite is actually zoned with respect to indium. in the core, we have about 0.28 weight% of indium, and in the sort of the grain boundaries, we have about 0.92 weight%. In this slide, in this image over here, what we have, so this is at a more, if you look at the scale, it's about 10 micron. So we're looking at how actually indium is concentrating in these massive sulfides. And what we find is that it is forming sternite as cassiterite is dissolving and remobilizing, and it gets deposited as a sternite along these fracture planes and mineral grain boundaries. So some sternite from Isabel deposit. So Isabel deposit actually has slightly larger sternite. But the sternite in Isabel deposit actually tend to have some silver associated to it as well. And there's a particular type of sternite, they're called petrukite, that actually occurs in the Isabel deposit. So looking at the sternite, so there's two kinds of sternites. One is casterite and the other one is ferrocasterite. Casterite is what's used for making your solar panels. And casterite are the ones that actually concentrate high grades of indium. So you can get about 6 to 10 weight% of indium in the casterites. In the ferrocasterite, you normally tend to get about 1 weight% of indium. Right, so just predicting the temperature of formation for both of the deposit, that is. So once sternite is formed, it actually reacts with sphalerite, and it goes through a mechanism where it sort of switches iron for zinc, and you can actually model that with respect to the temperature for partitioning of zinc and iron between the two phases, sphalerite and sternite. And the temperatures that we got out of it were in the range for Belgammon, it was 270 to 300 degrees Celsius. And for Isabel, that was about 290 to 315 degrees Celsius. So looking at sulfur isotopes, so what we see from the sulfur isotopes over here is that they're quite constrained, right? So this is chalcopyrite and this is pyrrhotite. And samples were taken from different sections of the Belgammon deposit. So this, for example, this one is from the deeper sections of the mine. This is from the Una porphyry. This is from the contact of Una porphyry and the meta sediments. And these ones are like the massive sulfides that occur within the meta sediment. This sample is from Isabel, and Isabel does not have so much chalcopyrite or pyrrhotite. So these ones were taken from the veins that occur within the type 1 sphalerite veins. And what we start to see is that these the isotopes are quite constrained between 0.5 to 2 parts per mil. And what this sort of points out to that we have a closed system when these things were being deposited. Okay, so we'll start off with this diagram over here. So what is this actually showing us? That we have both sort of things like tin deposits and copper deposits occurring together. And if you look at tin systems, they are in a fairly reduced conditions compared to your copper system. And the way to actually switch from your tin to your copper, you need a mafic input. And at our site, what we saw is there's like a granodiorite that is associated to it, right? And the age that we get out from the cassiterite dating and the zircons from the granodiorite, they're quite similar. Now moving on, just to look at like how indium was mobilized in this hydrothermal environment. So I modeled the so indium actually gets transported in your hydrothermal environment as a chloride complex, and I modeled the decay of indium chloride complex with respect to temperature and pH. And we already know the temperature that this deposit more or less formed. And if you drop a line from that point over there, we reach to a pH of 2. So I also modeled the mineralogy of this deposit. And if you draw another line from there, so we basically end up to the mineralogy that we see in our deposits, right? The mineral paragenesis. So more or less, in terms of like in your hydrothermal environment, the conditions that were necessary for mobilizing indium were like around pH of 2 to 4 and a reduced condition. Okay, so this slide, I just like to highlight the signature of the fractionated granites that we sampled. The fractionated granites were that, and they host your tin and your tungsten deposits were the Jamuna granite and the Herberton Hill granite, and they normally have a very high rubidium content, and also they have a very negative europium anomaly. So this is just a slide that's compiling all the ages that we get from dating the granite samples, and these yellow points over here, they sort of show us our sampling points. So what we have over here is the Stoddard Creek volcanics at about 290, and the Watson Vale granite at about 285 million years, and the Kalinga granodiorite that could be responsible for switching the mineral system from tin to copper at about 315 to 313 million years. And then you have the Una porphyry at about 330 million years, and Herberton Hill granite at about 340, and then you have the Jamuna granite at about 365 million years. Now, one interesting thing that we sort of found is that the Una porphyry from Belgammon has a inheritance age as well at about 362 million years. So this is just some cassiterite dating results. So this is a CL image of cassiterite. It shows nice zoning. Sometimes they're fractured, but the dates that we get out from Una porphyry is about 309 million years, and the date that we get out from the Jamuna granite is about 330 million years. So there is a bit of lead loss, and the way we calculated the age was through intercept. So once you take all the geochronological result and you combine it with the geochronological data that is already out there in the Geological Survey of Queensland databases, we see 4 peaks of magmatic episodes, and the oldest one at 337 million years. And then we have 322 million years, 305, and 285 million years, right? And from cassiterite dating, we know that tin occurs at around 308 million years and 330 million years. And indium occurs with those volcanics at about 290 million years. So more or less, we're sort of situated over here with regards to indium mineralization with the moly tungsten episode, and with it the sulfide mineralization. So this is basically putting everything together. If you're an exploration company looking for indium mineralization, you're looking for a granite with a high EU anomaly, right? And that's where you'll get your sort of your tin, and then later on, as the system switches to copper, zinc, and indium, and that's when you start to form your indium mineralization. This is just a bit of theoretical work over here. Temperature at about 300 degrees Celsius, pH of 2 to 4. And so I haven't drawn any lines showing the how the connate or meteoric water is moving, because we assumed that the system was quite closed because of the sulfur isotope constraints. And if you look at Belgammon is probably more or less closer to the heat source. Isabel's mostly composed of the sphalerite, so it's probably slightly far from the heat source. And thank you, that is all. And if you have any questions, please feel free to ask.
Thanks so much, Avish. Does anyone have any questions? Yes. Coralie.
Have you considered doing hafnium and oxygen isotopes in those zircons to constrain the nature of the sources and where those metals may come from?
We have done that, but I haven't shown you the result. We're still interpreting those results actually at the moment.
Okay, is there another? Yep, Paul.
Thanks, Avish. That's a complicated story for all the sulfides in their history there. I just wanted to double check what I thought I understood from what you were saying is that the tin deposits are sort of 330 to 308 forming the cassiterite, and then the indium was forming those inclusions later at about 290 associated with the Watson-Ville granite. Was that what I was understanding?
So not exactly the Watson-Ville granite, the volcanics, that is the slot-diatric volcanics, and they're more have a porphyry texture. The Watson-Ville granite is actually not mineralized at all. It poses this mineralization, and it occurs at 285 rather than 290. There's a bit of a gap over there.
All right, great, thanks. Any more questions for Avish? All right, and they're none online. So you are free to go, Avish, and we can all now follow up the conversation out in the foyer for lunch. So thanks to everybody for this session's speakers. All right. It's okay because Stephen is still figuring out his microphone anyway. All right, we're going to spend the next hour. How long did we give you? About an hour and a half, or a bit less, to go through the work that the SMI team have been doing in collaboration with Euclidean.
Oh, yeah. How do I change that?
And GSQ, of course, on creating a digital twin of Queensland's geology, which we're calling Digital Earth, but I realise that that's actually a name that other people use for similar things. This is something we sent the links to you yesterday or the day before. So if you've had a chance, I hope you've all downloaded what we asked you to download. And I'm really stalling for time after hurrying everybody up and getting them quiet, Steve. Whenever you're ready. Are you ready?
I'm just trying to sort out the online.
Display, see where it says display settings up at the top? Unless you need the notes there, just.
It's going to be really good.
Display settings, no, it's.
Okay. You can keep talking now.
Oh.
Yeah, it's gone, hasn't it?
Oh, move that top thing there. Just here.
Yeah, you go for it. You drive it. Ah, hiding. Yeah.
No, can't do that.
Duplicate?
Duplicate, yeah.
That's fine. Duplicate's good.
Oh, actually, now I got it. Sorry. Right, just duplicate.
Cool.
Sorry.
Thank you. So hopefully it's working on for everyone online. And hopefully you can hear me online. So testing. We're all having technical issues. Helen's computer's died. Microphone wasn't quite working. Hopefully everyone can hear me online. Great. All right. We're good.
Just before we begin, I'm actually going to step back and do a quick acknowledgement to country again. You know, I think it's actually shocking that I've been coming to Townsville for 15, 20 years of my life, and I don't know who the Indigenous people groups are that own this land. So I want to acknowledge my mistakes and sins in that regard. And I want to acknowledge that there are traditional owners and custodians of this land on which we meet. And I want to pay respect to their ancestors and their descendants who continue cultural and spiritual connections to the country. And I'm going to try my best to be better in this space. Right, now, moving on. Let's see, is it working? It's not working. How do we move? It's a great start, isn't it? So the most technical workshop of the evening of the workshop, and we're having computer issues. But what we're dealing with today and this afternoon is really the issue of big data, and this project that we've been building, which is really to create a digital twin of the geology of Queensland. At the moment, it's in prototype stage. We're experimenting on Northwest Minerals Province data largely. But you can see there's a cast of thousands who've been involved. And this is a collaboration between ourselves at SMI. These names down here, Ethan Bellecourt, Frank Hart, Steve Moore, Sana Wu, all from Euclidean, who are our technology partners. And then of course, GSQ and Matt Greenwood has largely been driving this from the GSQ end. But I've got to acknowledge the help and contributions of Dom Brown and Janelle Simpson and the support of Helen in all of this, which has been great. Now, before I go any further, Steve Amore, can you stand up, please? For those online, I'm pointing to a man at the front of the room. So Steve has been a brilliant interface for us at Euclidean. And what we're going to do, hopefully you've all received the link, and some of you will probably have opened it up and have a browser on your computer. And we'll have a little explore with Digital Earth over the next hour and a half. And Steve can help troubleshoot any issues there as well. And he might be able to field questions. So those are the browser links if you haven't got them. Steve asked me to remind people in the room, or to say to people in the room, if you have your own personal hotspot, give that a go. The more people that load the room's internet, the thing will slow down a bit. But I'm tethered to my phone, and I have run this digital twin off one bar before and had very few problems. So it can be quite robust in fairly low Wi-Fi strength environments. And you can also, I mean, we're not going to do that in this workshop, but you can work offline. So you can have, if you need to, you can have data on a hard drive and things, and you can still be using this tool in a field environment. All right, then why are we doing this? Okay, we're all very aware in this room that there is a wealth of data out there. And as explorers, you know, the last day and a half, we've been talking about all the GIS products, geophysical products, geochemical products that are available on the internet through various portals. I'm just showing you a selection of them here: Ozscope, the Exploring for the Future portals, the GSQ Open Data portal. And it can be quite confusing, to be honest. Quite hard to know where to get what information, and it's quite hard sometimes to mine those portals for everything you're after. And I've had an experience of knowing that there's data available in some of these sites and typing in keywords and still not finding it, and having to, you know, actually email someone directly just to help them, ask them to give me the link. So the challenge really is that in Australia, we're data rich, and in Queensland, we're, you know, one of the premier destinations for mineral exploration because of the fantastic work the GSQ have done in getting data out there and making data available to the industry. But such large volumes of data, pre-competitive, it's hard, first of all, to put onto one laptop and to show it all in one piece of software. And sometimes it's hard to find it. So how do we make sense of it? How do we discover the richness of that data? How do we visualize it, in other words? Can we search one location before investing, with all the data in that one location, before investing time in downloading it? And how do we avoid our laptops and our tablets falling over when handling that amount of data? So that's the challenge statement. And the vision really of this project is by creating a tool for us and for the general public that is really easily accessible in most environments and that shows everything in it from a regional scale down to a microscopic, then we hope that that can help unlock future minerals supply. We hope it's going to help people make more cost-effective decisions, not rely so much on their own proprietary software or the need to get hold of proprietary software, and be able to explore at a very early stage, even before coming into the state, what's available in 2D and 3D. All right. This slide we can skip over very quickly. It's just a snapshot of the organization I work for, which is the Sustainable Minerals Institute, and the breadth of things that we do. But I think you're all probably very familiar with us in this room. However, I do want to introduce Euclidean, and Steve, you can probably comment here if I miss anything or misrepresent you in any way. But Euclidean have come, they're a data visualization company, Brisbane-based. They came a long while ago, originally from the gaming industry, I think that's correct. And they've got this technology which we're utilizing and adapting for geoscience applications, which enables us to really put an unlimited amount of data, spatial data, into one place at any scale. And it relies on two things. One of them is some fairly smart ways of processing data, so that the algorithms behind it, you convert a lot of our geological objects into point clouds, and you can really speed up the processing speed. And then the other thing is, of course, basing it in the cloud. So you can put a huge amount of data into the cloud, and your computer never really sees it, and therefore you're not hardware limited anymore. Have I missed anything there, Steve? For those online, he's shaking his head, saying I've done a good job. Euclidean provide sort of two products: UD Cloud, where you can store the data, and UD Stream, which is really the front end, the utility where we can start visualizing it. And what we're doing in this project is we're adapting UD Stream, we're adapting a lot of the tools, we're helping Euclidean learn what the hell geoscience data is and all the different formats, enabling them to absorb that and then spit it out. But we're trying to get to a point where we can do this entirely automatically, so that the digital Earth model, whatever format, whatever way that's served up, will sit on top of GSQ's open data portal, and every hour or every week, whatever you need, it will suck out data that's been updated there, and it will automatically visualize it in this environment, which I'm going to show you in a bit. Okay, so this has been a year-long project. It's a prototype at the moment. It doesn't have all the data in there, but it's got a fair bit in, as you'll see, for the Northwest Minerals Province, and we couldn't help ourselves. We began to expand out beyond that area and even across Australia. It's a seamless visualization, and what I mean by that is, as you'll see, you can go from the thousands of kilometer scale, and you can zoom right down to literally the microscopic scale, and there's no need for tiling, there's no lag. It's pretty smooth, so you don't have to wait around while your computer thinks about it and then rebuilds the images in front of you. And the final component to this project has been run with Karen Connors, who unfortunately is sick today. I would love to have had her up on stage with me. So she's joined us online. But Karen has been working particularly with Dom and Janelle in reinterpreting the seismic for the region. And we've built now a first pass 3D model from that seismic, and I'll show you some images from that as well as we go. All right, let's hope this works. Oh, there we go. So, digital Earth. As I said, massive amounts of three-dimensional data. We could literally put petabytes in there if we want. We don't have petabytes at the moment because there isn't that much there. The video you're seeing playing on the right is actually a very old version of the model, but it's just showing you the seismic, a few cross sections, and we're zooming right now into drill core and then across to some TEMA microscope images that were put in there. And this is all work, you know, really I basically have to acknowledge Rick Valenta here, because he did a huge amount of the initial work of putting all these data sets into this environment. And what you're showing there, that video is slightly speeded up, and which made it unpleasant on the eyes. But actually that was fairly real time. So you could see we went from that regional scale down to the microscopic without freezing. And there's lots of different types of data in there, which we're all going to explore in a minute. The key areas of focus for this first phase of the project has been, how do we actually visualize the data? You know, it's been a big learning curve for Euclidean. They had never seen magnetic or gravity data in the past. Seismic was their first. In fact, Steve, who are your main clients at the moment? Which industries? Okay, so for those online, Steve said mainly defense and basically infrastructure, so roads and railways and things. And I know that you had a project in France where you were using LiDAR data for 2,000 kilometers of rail at one point, which was pretty cool. 15,000 kilometers, 50,000 kilometers, wow. Any higher? Okay. Another aspect of the project has been to demonstrate that we can automatically convert data. So we've managed to do that for drill core. And that is not in this model that you guys are going to be playing with or have up on your screen, but we have shown that you can automatically convert drill core data from Open Data Portal and display it here. We've also built prototype query tools and data discovery tools, so you can do things like search on different elements and their concentrations. And we have also had a focus on showing that this can integrate. So the digital Earth model is agnostic of where you display it. It can come through a browser. It can come through its own little desktop app. It can integrate with ArcGIS, Esri products. And there's another product out there called Cesium, which is another type of open source 3D visualization environment. And everything we do with Euclidean can be visualized or placed within those other environments. And then finally, the other final two aspects of the project are just to have a look at things like data standards and legacy data, and think about, you know, how we can handle these problems, issues of data moving forward, and to demonstrate the potential to visualize other types of data than geoscience data. So can we put anything in there? Basically, the answer is yes. You know, we had to look at infrastructure and a few of the data sets, and we've got mining leases in. We haven't got mining leases in the particular project you guys are looking at, but we have put them in into this environment. Okay, so how does it get served up? We can serve it up through a browser, as I mentioned, through a desktop app, and we're even now, a few weeks ago, I spent some time down at the Euclidean offices, and everything that you'll see today, we were looking at through a HoloLens and walking through the data, which was pretty damn cool. So lots of fun. First thing to say is the data is regional to microscopic, and as I mentioned earlier, you can zoom between, you can move between those different scales pretty seamlessly. At the regional level, we've put in AEM, magnetotellurics, seismic interpretations, air mag, radiometrics, gravity, and so on. Regional geology, we've got models in there, we've got types of volume data, we've got some cross sections, and we've got a lot of geochemistry, thanks to David Armstrong. You can look at mine site data, you can look at publicly available regional data sets, and there's cartographic data in there as well. And I'll show you all that in a minute. I'm just actually wondering whether it's worth my while breaking out from the presentation and us having an explore of all that right now. So I might do that just so everyone has a bit of a break from death by PowerPoint. Okay, so for those of you who have it on your screen, how many of you are actually trying to look at it? Oh yeah, I've got a few hands up there. Great. Are you seeing this? Yep. All right, awesome. So the difference between what you're looking at and what I'm looking at is I'm using the desktop app and you're all coming through a browser version. But I'll just quickly, don't want that. I'll just quickly explain the layout of this thing. So first thing to say is it's much easier to drive with a mouse, but there are tools that we built to do it touch screen. If I left click, I can rotate. If I move my scroll bar, I can move in and out. And right click, you can translate it around, shift it around. And hopefully you can see that Australia is moving. The display on the left where my cursor is showing at the moment, I call that the project tree. And it's exactly like, we're very familiar with driving things like GoCAD and Leapfrog. So very similar idea. In the project tree, you can see all the data that is in here, and I can expand that out. And you can see we've got mine site data, we've got regional geology data, we have regional geophysics data, we've got some cartographic information such as railways. And if you if I turn off the regional geophysics for the moment and the geology, and I just come in and I double click on the ISA railway, it will zoom you in roughly to the location where that object actually is in 3D space. Now, what I've done here in this particular model is I've taken the satellite image of Australia and I've moved it down to 10 kilometers depth, so it doesn't obscure the rest of the data, because I want to be moving around and looking at the geoscience data very easily. So that's why that's why it looks like the roads are floating in the air. The roads are actually at the surface. Australia is sunk. The range of geophysical data is pretty cool. I mentioned we got AEM. I couldn't help myself. We started putting in the statewide geophysics here as well. So that what you're looking at there on the statewide is, oh, that's magnetotellurics, sorry. The statewide mag data is the analytical signal that we're seeing at the moment. And if I just turn that off, you can see underneath it, we have all the regional seismic lines in for the Northwest Minerals Province, and we've got shed loads of AEM. And if we actually zoom in and come down and have a quick look at the seismic, this is Karen Connor's interpretation. I'm going to turn the AEM off here. So these are Karen's latest interpretations in 3D. Sorry a second. And Janelle and Dom, yes, absolutely. But what you can do is also, you can see the original data that underpins it. So if I just turn off the interpretations, you can see some earlier SegWi data with earlier interpretations. So we've got a historical record of an evolution of interpretation here. And we can also put in the actual raw SegWi without any interpretation on it. So there's just an example there where we've put something in just recently that is a seismic raw data set without the interpretations imposed on it. All right. Just briefly go back to the presentation. So that just gives you a flavor for what we're looking at. Any questions? Cool. If there's any questions online, Helen and Rick will let me know. Yeah. Oh, it's done that display thing here. There we go. Is that working for you? Great. Okay. So just going back to the workflow that we've been through, here we have, again, the UD stream environment. And as I mentioned, I'm just showing you an image of drill core from the Stara deposit, but this drill core was brought in automatically. So we've built a workflow, and it took about 2 minutes to convert that data, and it sucks in the collar survey, lithology, assay files, and then automatically projects them, and you can obviously go in and explore that. And we'll dive out of the presentation in a short time, and we'll actually look at drill core data. Oops, didn't want to do that. How do I go back? There we go. Some of the challenges around the drill core data, I just wanted to mention because this really emphasizes what Vance was talking about yesterday. So as Vance stood on stage, he mentioned there were 7,000 different ways in the current GSQ database of describing copper in the assay files. And so that's a challenge for any kind of visualization environment. If you're trying to put in big data, you cannot manually inspect every piece of drill core and make sure that that the visualization environment recognizes that this column is talking about copper assays, and that column is talking about longitude, and that column is talking about latitude. You have to do it automatically. And to do it automatically, we need to basically address the problem in a few ways. And so that's emphasizes the need for data standards. And hopefully you guys can all recognize that, it's going to be a bit of work putting our data into a standard template, but the end result is going to benefit all of us because we can build tools like this and we can serve it back up. And that means that we as an industry can now discover the data more thoroughly and comprehensively around the state and make much better exploration decisions. The other way we can deal with it, which is a complementary way, doesn't replace you, is we can use something known as aliasing. So we could take all 7,000 copper terms and put them into something like an XML table format and help the software recognize that whenever one of those terms is used, it's really referring to the same thing. And then finally, at the university, we have the joy and privilege of readily available slaves, otherwise known as undergraduates. And those undergraduates can come in and they can do some data harvesting and cleaning and legacy reports, which is obviously really manual work. But it's actually cool because it gives them an exposure to professional environment, and it helps us deal with the more difficult data that at the moment no form of machine learning or optical character recognition is able to deal with. And there's a few special cases where there'll be like thousands of reports that just can't be consumed with our current technology. Now, just jumping to drill core. So I'm going to I'll show you this on the screen, and then maybe we can go and explore it in the actual digital Earth environment. But you can visualize a drill core, and you can do anything, similar things to what you do in Leapfrog and GoCAD. You can obviously display the core by lithology, or you can color it up by assay. So here's the core string shown just where my cursor is. And at the moment, it's colored by assay. The other thing to note about this scene is that we've been able to project the core tray photos right alongside that core. And you can put images in there at any kind of resolution you want. So at the moment, some of them, they're pretty good. We'll have a look at it, but you can zoom in and you can see actual individual textures on the core, but we can make it even high resolution if you wish. And the other thing we can do is we can query on that. So what I've done, what you're seeing now is the same drill core, but we've done a query and we've asked the question, where in this core is copper of a percentage above 0.01 ppm and below 0.1 ppm? And it's now showing you all the lithology where there's some copper within that assay range present. So we're not trying to replace the leapfrog, we're not trying to replace the GoCAD, but we are trying to put in there just one or two tools which help us as geoscientists explore the data quickly and make some decisions about whether it's worthwhile for us downloading. So I might quickly jump out of there and let's have a quick drive around and see if we can reproduce some of that core work. So I'm back in the desktop app, and maybe you guys online or in the room who are using the browser can go there as well. I'm going to go over to the project tree on the left, and just to clear things up, I'm going to turn off. Now which link did you follow? Did you follow the simple one or the? So there was two links that were given, weren't there? Now one will get you to the project tree, and one will with the tools, and one will give you the simple. Steve, you might want to go and just check. Yeah, go and have a look. So while Steve's sorting that out, what I'm doing here is, I think I'll turn off the regional geology as well. And we're going to go to mine site data. And then we're going to go to Ernest Henry. And under Ernest Henry, you can see that there's a project layer known as that's called drill core. So, and that's showing mostly the core tray photos and also this thing known as a UDS. So I'm actually now going to double click on one of those, and it'll just zoom us straight in. And I'll turn off the geology map, and you can see we're suddenly looking at the copper ore shell. We're actually looking at several versions of the copper ore shell. And a whole bunch of core. Oh, sorry. Gone missing. There we go. So if I zoom in on some of this core, you will see the textures begin to appear in quite high resolution. And there's just a bit of a browser issue going on there, but you can see that some of it's showing up quite nicely. And we can actually improve this to any degree you want. It's not limited by the environment itself. And now if we zoom out, I hope this is going to work. Need to find move the toolbar over. The way to query it is actually in this little toolbar on top right. So you can do what we call a custom attribute query. And again, we've got copper % up there, but if you want, you see where my cursor is, you could search for gold or arsenic or moly or anything you wish. Let's stick with copper for the moment. And I'm going to just, I don't know, put those same values in we had earlier, which was 0.01, wasn't it? 0.01. 0.1 and 0.1. Oh, no, that's the. Hopefully what we're going to see is the core, just showing you those areas are colored up by the copper percentage. So now you can see how the core has changed and has been colored by the copper percentage in that particular core. And then if we go back to custom attribute and we go down to attribute query, this is where I take a deep breath. Where's Steve gone? Ah, oh, we just crashed. I thought that might happen. Yes, so the query attribute tool is a little bit unstable at the moment, which is what you get with prototype developments. But you can see that when it is working, it enables you to search the core on a set of criteria. So I'm just going back to my presentation now because it's easier while the Digital Earth comes back up online. Something to work on. Now back to geophysics. We've put a lot of geophysics in there, and I showed you the site. I showed you, the regional quick snapshot of what was there, and we'll go and have a quick explore of it in a second. But at the moment we're working with prioritizing things like mag and grav and AEM, and we've put the seismic in there. With the mag and grav, we're looking at geotiffs rather than GRDs and converting them into this UDS format. The other thing to note is this software does absorb surfaces, so it can take in OBJ files, and we've just recently managed to bring in GoCAD surfaces as well. But it's better if you convert it to a point cloud, because that's what makes this thing so fast and seamless. So a lot of the work we've done to date has been dealing with things like the images or converting the grid files to point clouds. And one of the issues with that we just solved was things like some of the AEM data, you get a decreasing sample depth, a decreasing resolution with sample depth. So some of the earlier data that was in there at the beginning of the year, you would have seen, those of you who were exploring it, it had this texture here where you could still see what the data was representing, but as you got down to a few hundred meters depth below the surface, the points were more and more spaced out, which wasn't very satisfactory. So we've worked, Sasha at SMI has worked hard, and she's managed to come up with a way of interpolating between those data points that also remains faithful to the original data. And we should also thank people from GA, some of Jeff's colleagues, particularly Neil Simmons, I think it is, Neil Symington, who was a really great help in solving that problem. Surfaces and blocks, as I mentioned, we can put surfaces in there, and we've got the OBJs in there where they were put in at an early stage. Just recently, we managed to open up, crack the problem of putting in GoCAD surfaces and GoCAD volumes as well. And so what you're looking at here is the Quambie model, which is available through the Allscope portal. And that was brought in, and again, it just took a few minutes to convert. It's on both, actually. Yeah, you're right. Quambie is on GSQ as well. Rick Valente, for those online, Rick Valente was just saying that he thought that came from GSQ, and he's right, it comes from both GSQ and Allscope. Okay, I'm just going to escape out and go back to Digital Earth. Move this around. How's it going back there, Steve? Yeah, is everyone up and running with the browser now? Cool. All right. This really is, in some ways, a case of what do you want to see? I'm going to just dive in temporarily into the AEM data, which we've just been looking at in presentation. And you can see we can zoom in and zoom in. Oh, it's taking a, wow, it's a bit of a lag there, isn't there? That's the internet. But the size of it behind it is doing quite well. So this is just internet speed that's slowing it down at the moment. And there we go, there's the AEM. So you can see now the AEM has none of those spacing, none of that spacing issue that I was talking about. But if you dive into the project tree, you can actually turn off the old, the latest in AEM, and you can just see the older ones. So this is a way of comparing new data with legacy data. And there you can see the legacy data with that legacy issue about of decreasing spacing. The other thing I really wanted to show you was this ability to go from this regional scale. So let's zoom back out to that regional view of Australia. Let's just put everything on. And we're going to go from this scale here, and we're going to zoom right down into microscopic. So you see how quickly things are able to turn on. And what we're going to do is we're going to go back to the mine site data. And we're going to go to Ernest Henry. So I'm closing up some of the layers just so you can see the project tree more easily. So we're back into Ernest Henry, and we're going to go and look at an X-ray tomography scan of some drill core that's been lined up, of a drill core sample that's been lined up with some of the core. This is actually, it's a bit of an experiment, because actually this isn't actually an X-ray tomography scan of that particular piece of core. It's from a different piece of core, but we just wanted to demonstrate that you can do it. All right, so what we're going to do, I'll just turn off the regional geophysics, and we'll turn off some of the geology data around Ernest Henry, so that when you zoom in, you're not obscured from seeing the actual data. Oh, managed to miss one off. Ernest Henry geology, there we go. Cool. There we go. So here's the drill core that it's aligned up with. If I just click on this a few times, it's going to drive us through the drill core and out to the other side. And there you go. That's actually microscopic scale X-ray tomography scan of the mineralogy of that drill core, lined up against the core trays. So those individual pixels there actually represent density, as I zoom in, on a micron scale for this particular sample. But it doesn't have to be density, it could be mineralogy. So if you were doing, if you were using X-ray tomography and mapping out feldspar or sulfides, you could also put that data into here and see the distribution of your sulfides in your drill core in 3D. Right. Is there anything people particularly want to, oh, I know what we can do. Anything people particularly want to see? Or have an explore with? I think what I'll do is I'm going to show you one of the things Rick really likes is the outcrop scans. So we'll just to show you how we're doing for time.
Do we want to see if there's any questions while we're driving around?
Yeah, yeah, go for it. Ariane and Jeff at the back.
Just got a question. If you click on some of those layers, do they link to the source report or anything like that, so you can get the metadata for each of those sort of things in your tree there?
Yeah, great question. So that is the objective of the project in the medium term. So we haven't got that in this particular model, but we've shown, yes, it's pretty easy. That's the whole idea. We're visualizing all this data in one place so that you can then do something like click on the magnetic and a little window will come up, or you go to the project tree and there'll be a URL and it'll take you straight to Open Data Portal or to Ozscope or to the GA portals, and you'll be able to download that data directly. So the whole point of this project is not to replace what we do in our day-to-day analysis of the data. So when we're using Leapfrog or GoCAD, we still want to use Leapfrog and GoCAD. This is to be able to show you everything in one place so that you can then decide, I want that piece of data along with this drill core, along with this surface geochemistry, and I want to download that so I can work on it in my own time, in my own office. So yeah, thanks for that question, Ariane. That's exactly right.
Hey, Steve, only two questions. One, where are you getting the drill core imagery from? And two, when you're displaying it down, so where did you get the drill core imagery from?
Oh, yeah.
And two, when you're displaying it down hole, obviously you've got the core trays running out sideways, it's running to the bottom of the hole.
Yeah.
They're just spread out evenly down the hole. Is that the way it's displayed?
Yeah, good questions. So the core imageries, a lot of the data of drill core that's in there at the moment is actually from the Northwest Minerals Atlas project. And so a lot of that high logger data isn't yet publicly available or served up through Open Data Portal, but I know that Courtney and the team are working very hard on doing that. And it is available through the Northwest Minerals Atlas data sets. The question about the display of the core trays is, you're absolutely right. We've chosen in this prototype to just take the core tray photos and line them up according to their depth along the core. So if you wanted to do it more realistically, you would obviously strip out the individual core racks and then line them up along the survey. And obviously things like products like Imagio do that already. Actually, personally speaking, as an explorer, I really like seeing the core trays displayed like that, because I just, for some reason, my eye is able to absorb the information a lot more easily when it's displayed in the core tray format rather than when it's stripped out. But is that what you were thinking about? Yeah, the stripping out. So we can, I think technically the point there is we can do both, and we're not limited by either. Yeah. Cool, thanks for those questions. Anyone else? No. All right. Oh, Rick.
I was just going to backseat drive a little bit. Yeah, after you go to my iPad outcrop photo, I thought just jumping around from IOCG grade shell to IOCG grade shell might be kind of interesting, just to show.
Sure.
Because I mean, you can put all this stuff in Geoscience Analyst, but what you can't do is put them all in Geoscience Analyst. You got to open the file, close it if you want to go to another one, and so on and so on. So yeah, that was the only thing I was going to say.
Yeah, thanks for that, Rick. Yeah, we'll do that. Yeah, so that obviously is something we touched on at the beginning of the workshop, the talk, is the fact that you can't put all this data into one area, so into one piece of software. So we'll play around with the ISCG shells and show you jumping from one project to the next. Here's also one of your innovations, Rick. Rick, one day when he was in Townsville, no, Mount Isa, just wandered out with his tablet with the little new LiDAR capabilities and scanned the Urquhart Shale. And there you go. You can put outcrop in here in 3D, and you're showing that outcrop here with the background of some of the cross sections from Mount Isa. And there's drill core and all sorts of data in there that we could compare it to. So ISCG shells. Whoops. There we go. So we jump over to Mount Dore. Oh. And there's the copper shell for Mount Dore. And then, oh, sorry, I'm just driving through. That's my user error there. And then we want to go to, we've been to Ernest Henry already, but we can go back there. Jump over to Ernest Henry and again, turn off some of the data that's obscuring it. The thing I love about this particular model is, what's hiding it there? Some of the regional geology is, you can see this right above the magnetotelluric finger of God. Where's that gone? That's under MT up here. Yeah. Oops. There we go. I think that's actually one of the old coarser versions of the magnetotellurics. Oh no, that's okay. So there you can see the copper ore shell for Ernest Henry right above one of these positive conductive anomalies that lie deep within the earth. And then you can go in and you can look at the actual drill core data that we've already looked at. And then we can jump from there and we can go over to, I don't know, let's go and explore Walford Creek, because that's a site that I'm fairly familiar with at the moment because we're working on it in terms of the seismic at SMI. So Walford Creek's really nice. Dan Johnson, who unfortunately has had to just leave for the afternoon, gave us a whole bunch of data for the Northwest Minerals Atlas, and Rick particularly was able to put a large amount of that in here. So we've got the seismic in here, we've got the radiometrics, we've got various different types of geology, soil geochemistry, different cross sections, and of course things like the fault, the actual geology surfaces and so on. So anything at Walford Creek we should look at particularly? Turn off those sections. And we're going to have a look at the radiometrics, I think. There we go. So you can see very quickly, just by turning on and off, we've jumped from Ernest Henry and we're now at Walford Creek, and we're looking there at the potassium values of the radiometrics, and then the thorium and obviously the uranium all here. And then you can turn that off and you can zoom in and you can see how they compare to the seismic that's been interpreted in that area. So pretty neat. Anything else on the mine geology? Anything that people want to have a look at that they've seen up on that scene? Good, all right. I'll just jump back to the presentation. The regional MT, you mean? Yeah, so Jeff is asking if we have any other types of MT in there, and he was asking also about the way we were displaying that data, which are actually really good questions, and Janelle may well have some comments here as well. At the moment, we don't have any other data in there, but we can obviously put it in. We just wanted to demonstrate as a prototype that we could, and at the moment. Oh, you're right. Yeah. Yeah, Rick's just added there are some shells in there. So we have, you know, you can take those ISO services and display them as an OBJ file, as a mesh, and we can put those in. We've chosen in that display I just showed you to actually visualize all the conductivity values that were 1 ohm meter or higher. Less? Higher?
Lower.
Lower. Thanks, Janelle. And that really highlights, you know, those deep-seated crustal structures that you get. But other ways of displaying it, you could potentially bring in the full grid data. The problem with that in an environment, in a 3D environment like this, of course, is, you know, how do you actually explore through that? It's not easy to interpret. So my preferred approach is to serve up some ready-made products where you can actually see the surfaces or a representation of them. But if you have feedback on that, I'd love to hear it, and any ideas on different ways we can show things, we can do it. We just need to know what you're after. Yeah. Yeah. So Janelle's getting there with the microphone, but yeah, Dom's just mentioned that we could easily put the depth slices in there, and absolutely right. As you can see, as you saw, we had all the regional magnetics and radiometrics in there. It's exactly the same base data, type of data. You just put in as a geotiff and you can display it and you can project it at the right depth. So we could have the GA, the regional GA data set that shows you the boundary that all the major mineral deposits sort of line up along, that Carol Sonota published on a few years ago. That would be nice to show in there, actually. Cool. Anything else on MT or AM or anything? All right. Oh yeah. So I did mention that Karen, as part of this project, has also been reinterpreting the seismic. Interesting to note, this is a leapfrog model using the seismic. And just as an aside, complete segue, look how the seismic in leapfrog, you have to actually sort of break down into almost like a panel-like way of displaying the data. You project the image onto the surface, and you know, it's not that smooth, but actually in Digital Earth, we've managed to take the CDP point. So you've got a smooth surface that is has integrity relative to how the data was originally collected. And so you can actually see the seismic without those sort of panel-like segments. But that was an aside. What Karen's now got done in collaboration with one of our students called Ron Reed is they've taken the interpretation that Karen and Janelle and Dom have come up with, and we started to build up a 3D model of the area, a new 3D model of the basement area. And here is just a snapshot of the major structures in that region. So where my cursor is currently, I hope you can see that online. That's the Gigia fault. And here are some displays of some of the major basement blocks. So over here on the left of the model is the new Pitta block that Karen's interpreted. And then we move over to the right, and that block is separated by the Gigia structure. And we come into the Numal terrain and the Abingdon terrain as examples of some of these really major basement blocks that we can see in the seismic. And that data is going to go into Digital Earth. It's just not in there this week. All right. Steve, quick question. Steve Amor. Question to you, yeah. Should I be brave enough to try and show the section tool? Will it fall over? Give it a go. All right. Now you can't do this in the room because we turned off this tool capacity for the public access link. I'm not quite sure why. Okay. Yeah, so Stephen said that the reason for that is just because it's a browser memory problem. Okay. So let's put up some of these 3D models. Actually, let's go to the Queensland model, which I showed you earlier. I'll turn off that Northwest one. Okay. So home viewpoint. Sorry about that. All right, zoom in. Okay, this is that model that we've stolen from or brought in from the Allscope portal. And if you turn that off, you can see that actually it's sitting in the same location where the magnetotellurics are that we were just looking at. And I'll just turn off the magnetotellurics so that it doesn't come up in what I'm about to do. But essentially, Steve and the team have developed some tools that can enable us to quickly produce cross sections and even a cross section view at the base of the screen. So I'm going to give that a quick go here. So if I go add cross section, you can see almost instantly that model and the data that was displayed there is turned into a cross-section view, and you can see the individual surfaces. If I remove that, we're going back to we can actually see the model again. Another way of doing this would be with the box filter tool up there. But what I want to show you, or try and show you, is this add section view. So you click on a part of the model. Hope this works. Click on another. Escape. And then that cross section is automatically drawn for you at the base of the screen. So that's kind of nice functionality. It's again, as I say, we're not trying to turn this into a tool that's going to replace GoCAD or Leapfrog or anything, but that is a way of exploring the data when you come across an interesting area that you want to see the 2D views in more detail. And you can show on that cross section any of the data. I just chosen here to illustrate that point with the Queensland model, but we could have had the MT data on there. We could have had the drill core data on there, and that would all be coming up in that cross section as well. Okay, how are we doing for time? So I think we're nearly at an end. Oh, great question. So the question there was, can we print those and export them? I'm going to let Steve answer that question. The answer is there's certainly some nice ways of capturing the images, and Steve can explain it.
Yeah. I'd suggest there's a screen capture tool where you can go up to 4K, or you can specify the resolution to save it. We are looking at making it bigger. We've been asked about seismic doing longer posters. I also wanted to say, Stephen, that Stephen's been using the desktop version. So if you go to our website, I think I'll give you the link. If you let everyone have the link, you can download the desktop software for free as well. So you might have to register with an email, but there's no charge. So if you want to do things like some of the section tools and all the other tools, the desktop is a bit more stable than the browser, but we've given you the link to the browser. Are you going to leave the model link working for everybody after this workshop?
I'm very happy to do that. Yeah.
Okay.
You mean the one that we issued?
Yep. So you decide. If you do, send an email around. We'll send you the link so you can play with it in the future, and then contact us if you've got any questions about the tools.
Yeah. It's an easier way for people in the room or online to get access to it without having to register and so on. So, did you have a comment about that, Helen? You look like you want to say something.
No, I'm just loving the work.
Good. All right. So just moving towards the end of the workshop now, or the presentations. I did mention that one of the things we're really trying to achieve is demonstrate that we can integrate this with existing tools. Now, the motivation behind this is that the Department of Resources already have a GeoRes globe, for instance. And so the question is, can we show all this 3D data in GeoRes globe environment and enable you to search for it there in a much more easier way than is perhaps possible at the moment? And the answer is yes. And Euclidean actually have ways of, software developer kits and APIs, so they can interact with Unity engines, with Cesium, and with Esri in a fairly straightforward manner. And this next year, we're going to be focusing on that and developing, hopefully, a fourth tab in GeoRes Globe, so that GeoRes Globe will go properly 3D. And you'll have everything that you can see here, you'll see in GeoRes Globe. And that's really important, because at the moment, you could potentially display the outline of where the seismic data is in 3D in GeoRes Globe. But what we can do is we can show you the seismic itself with all the interpretations and all the texture. So that functionality will hopefully appear within the next year.
Steve, John Menzies online is asking how he downloads the desktop version. So Steve, just for John's benefit, we're going to share the link for that.
Yeah. Well, that link can come out through Evan.
That link can come out through Evan.
Great. And so what I'm showing you here now is just a demonstration of the fact that we can actually work with GeoRes Globe. So what you're looking at is a mock-up of the GeoRes Globe environment. It's an Esri mock-up. You've got all the sort of standard GeoRes Globe layouts on the left. And what we're doing is we're displaying some of the data that's in GeoRes Globe, and we've highlighted with a little polygon a particular area in the Northwest Minerals province that we want to look at more closely. Oh, we're frozen. Why are we frozen? There we go. So we're just going to zoom in on that area, and we switch in the fourth tab into the UD stream environment, and you can see that in the UD stream environment, what that search in GeoRes Globe has done is it's now just highlighting all the data that is in that polygon that you selected in 2D. And if you zoom in on it and actually explore it, that's the result. So I can't demonstrate that to you today, because that's a separate model, if you like, and a separate demonstration. We just don't have it with us. But I've given you screenshots of the fact that what you search for in GeoRes Globe can then be displayed in 3D in all its Technicolor in the UD stream environment. Right. So one more, I think I'll jump out one more time. I just want to show you probably one more thing, which I think you can also do for those who have the browser controls. We're just going to have a look at the surface geochemistry. So I'm going to turn off some of the mines data, turn off the regional geophysical data, turn on the regional geology data. And you can see here it says geochem. Just flick that on. And what we're looking at, if I expand that out, we actually have geochemistry data for the whole of the state. So, and that geochemistry data at the moment is rock chips, soil sediments, stream sediments, and whole rock. And I think that's the entire data set for Queensland, unless there's some that hasn't been, that David wasn't able to harvest. Dom, is there anything in there that we're missing? Oh, there is, okay. There's lots of surface geochemistry data we've still got to put in there. Yeah. Thanks. Paul is saying that geochemistry data is in the wrong location on the browser version. It's under geophysics, is it? Yes. Regional geophysics, so sorry for that. Okay, so we've got a lot of data in there. Dom mentions it's nowhere near the full amount, but there's still shed loads of data. And what we're going to do is I'm going to turn all of it off, apart from the stuff that's relevant to the Northwest Minerals Province. And just highlighting it there. And you can, oh no, bugger. We crashed. What we were going to do was actually look at how you could search on that, which let's see how quickly we can load up. Okay. That was very unfortunate. But kind of a nice experiment just to show you how quickly you can turn this thing on. So what happens when you turn Euclidean on is it starts to load in all the data, and you can see these little yellow triangles. That's just basically telling you, okay, I'm bringing that data in now. But as soon as it's in there, it's really very quick. So I can turn this thing on and off, and it doesn't freeze or anything like that. I can turn all the mag and radiometrics off, and it's quite happy. Right, let's have another go at that geochemistry. And if we fall over one more time, we'll just have to give up on it. So the geochemistry data is still coming in. It's just pending. You see how it's got this pending sign there? So that might take a little while. So while that's thinking, I'll quickly go back to the presentation. We'll do that at the end. Yep. So say that again, Steve.
Did you say 340 models and 140 gigabytes, just for the people online?
Yeah, there you go. So that's what's being displayed over a Wi-Fi system that's really struggling. Next time we'll bring it on a hard drive as well, eh? Make sure make sure we don't have to suffer the Wi-Fi issues. Okay, so thinking bigger, despite the crashes, hopefully you can see that we can basically put in there any spatial information you want. And so thinking bigger, what could this look like in the future? And at the moment, we've focused on geoscience data from just the Northwest Minerals province, but obviously we can bring in the abandoned mining and tailing data sets that Kobie was talking about. There's no reason why we can't have the water and the environment and the regulatory infrastructure. And that's really important because it wasn't so long ago where some of the Department of Environmental restricted areas for exploration weren't even on publicly, weren't even on the website in a very easy to find way. And that had some impacts in some exploration programs I know about. So it'd be really nice to actually be able to show the exploration data alongside some of the, the infrastructure data and the environmental data at the same time. And if we, in previous exploration programs I've been involved with, if we also had access to some of the groundwater information, that would have helped us in our planning for our drilling programs. And again, that's all just spatial information. A lot of it's available in some website or other, and we could easily visualize it in this. We want to extend, I'd love to extend the scope to the whole of Australia. There's no reason why we can't have terrestrial and marine jurisdictions. And we basically want to get to a point where we have production level browser interface. So you won't have these crashes. This prototype will look a lot smoother and a bit more stable, but it'll all be part of an ecosystem. So you'd have this sat on top of Open Data Portal and interacting with GeoRes Globe, and there may even be on the side other tools that the Department of Resources provide in terms of analytics and so on. And now one question we get asked a lot is, what do you do with industry confidential data? And so if you're an Anglo-American or a South 32 or a junior explorer, it will be possible to bring your own data into this environment, show it alongside the publicly available data that's displayed there, but keep it private to yourselves. And we can actually do that right now, but obviously we haven't launched this project yet in a public way. All right. So the immediate future in the next 2 years is, for next year, we're going to really focus on this integration with GeoRes Globe, putting a lot more data in there, bringing in some of the useful things like extra information, like lease information, and really doing a much better job of scoping with you guys and getting your feedback on what you want to see in there and how you want it to work and how you want it to look. And then in phase 3, we'll probably be implementing a lot of that feedback, into putting in all the state mineral data and probably having a focus particularly on high logger information, not just core photos, but the mineral interpretations, which really goes to that question we had at the back of the room earlier on. And as I say, move towards having something that's really a production level tool. And then finally, have capabilities implemented which would allow you to do kind of, for those of you who are really interested in that sort of thing, you could do augmented reality or virtual reality visualizations of the same thing. And again, that's something Euclidean have already been working on and can already demonstrate to some extent. Right, that's just, I think that's it for me. Put this up while Helen's coming up with the microphone. We'll just have a...
Sure, good job. Thanks so much, Steve. And Steve squared. It's a group effort. Any more questions from anybody in the room or online? Really encourage you all to have play and give us suggestions or just become familiar with it. Here's Jeff.
Thanks a lot, Steve. It was really good. I might be jumping ahead a little bit here now, but given you've sort of spoken a little bit about your vision of where this is going and how much different sort of information could be in there, and I guess that widens the user base and so on. I'm just thinking, do you have any sense of if this becomes the go-to platform, what kind of overhead or requirements are there for custodianship and maintenance and troubleshooting, and kind of how do you keep it working well for the user base if it becomes in everyone's expectation that this is a tool for daily use?
Yeah, no, that's a really good question, which is the question that every single survey has whenever we show this. So I'm sure Helen has an opinion and a preferred position on this as well, and Helen's holding the microphone. But I won't put you on the spot just yet.
Look, from our perspective, GeoRes Globe, which is the online spatial tool for the Department of Resources, it's moving towards 3D, but it's really not doing that very well. Sorry to the people who are in charge of that project. So from the geoscience perspective, we know how big geological data is, like the scale of it, and it's not two-dimensional data, it's three-dimensional data, even when it's just surface data. So being able to just kind of leap ahead and go with something that's already been developed, but that we can easily integrate into existing systems. If we're going to be doing it anyway, we'll be paying somebody. So might as well just go for it.
So I guess you're saying that from a GSQ perspective, that there will be, once we get it to a production level, you'd be very happy to have maintenance costs and ongoing. That's something we'll negotiate.
But yes.
Yeah. So I mean, there's two ways of doing it, and Euclidean, Steve will also have an opinion. Steve A. Moore over there will have some comments on this. But you can build a product which then the provider, there's an ongoing annual license. The thing is regularly updated and it's maintained, and they have background software support, software development support, and that's what we do with Esri all the time. So that's one way of approaching it. Euclidean are also able to build a standalone product which would be yours to own in perpetuity, and then the advantage of that, that approach tends to be more expensive as a one-off, but then the survey has control of it, and you're not reliant on the provider down the track. But the disadvantage of that approach is the survey has control of it, and there's no expertise within the survey to really maintain that and keep it functional. And one of the problems with, if we want to be able to show big data, we need to be able to do it from a cloud environment, and notwithstanding the browser issues we've had today. The problem is browsers developed by Google and Firefox, they are changing all the time. And the way that your visualization interacts with them can suddenly become non-functional because they've changed something in the JavaScript. And so, I'd say that second approach is actually fraught with lots of pitfalls, even though on the face of it, it gives you more control. Steve, do you have any comments to add there?
I just wanted to comment a slightly different point about the data ownership, if you're worried about who owns the data. So the actual technology that we've done, you can actually store it anywhere. So whether it's on your own drive or we use Azure, I think we have an AWS version coming out. So the technicalities these days is you can own an Azure blob that we've set up, but then we transfer ownership. So you actually own it. So it's separate. So as far as where the data lives, it can be anywhere. So for data sovereignty, you can own it, but then you have to maintain it. As for browsers, yes, everyone wants browsers. we've really pushed the limits of what we can do with browsers, what you've seen today. But they are starting to allocate more memory to browsers, so we can do more and more, but we're definitely at the whim of Google in particular. We didn't mention at the moment we don't work with Apple mobile devices. That's just a constraint that Apple has done, which is what normally happens. So products like Esri, ArcGIS, you know, everyone uses desktop ArcGIS Pro because it's not browser, and you don't really do serious work in a browser. So that's exactly the same problem that you see across the industry. So
yeah, you're not working with Apple products, but you are working with Galaxy and Samsung and
it works Apple desktop, Mac, but it doesn't work Apple mobile.
Yeah.
Apple is catching up with Chrome. They are choosing to finally adopt the standards that Google does, but this is not a Euclidean specific problem. This is every browser application you've ever used.
So while Helen's just going to the question at the back, I'm just showing on screen what I was trying to show you earlier, the ability to quickly search geochemistry data and highlight areas of importance. So what I'm doing there is I'm just coloring up the surface rock chips by a particular value of copper. So you can very, very quickly hone in on where really high copper anomalism is present in the surface environment. Right, sorry about that. Go for a question.
That's all right. So just following on from that in terms of where the data sits, and I think I've asked this question before when you might have presented this to us at the South Australian survey a little while ago.
Oh yeah.
Are you looking at having an option to be able to consume web services and things like that to be able to bring data in?
Absolutely, yeah. And in fact, we've already done that for some of the maps and cartography information. Yeah. Simple answer. It was a close question.
Any more questions in the room? Check online.
None online.
None online. All right.
And I think that's good timing, isn't it? Because you wanted me to finish now.
I wanted to go and have afternoon tea.
Yeah. All right. Well, thank you everyone for your patience.
Thanks, Steve. Thanks very much. All right. Well, people are free to stay in here and continue playing with the Digital Earth if you like, but there will be afternoon tea out in the foyer, and we will come back in at 3:20.
Cool.
For the Northeast Queensland Deposit Atlas extravaganza.
Thanks a lot. I'm just going to leave this running. Have we got enough battery here? How are we doing for battery? Not really, no. Okay.
There.
Okay. That one in your pocket. Yep. I might there. Yep. Just pop it in my pocket.
Yeah.
Great.
That's right. One off the left hand side of the room. So.
Okay. All right. Thanks. Great. Okay. I don't want to do a
They had a food conversation earlier.
yes. Yeah. What was this? Oh, Peter Dutton, wasn't it, at the Pacific Forum or something like that? Yeah.
Someone's always listening.
I think it's all good. Thanks. You can hear that all right? You can, yep, all good.
We are online and ready to go for the last session of the workshop. I really appreciate everybody hanging around, and I'm going to talk even louder for the people that are chatting up the back. Sit down, be quiet, pay attention. Thank you. All right, last session of the workshop. I really appreciate how many people have hung in for Paul's sake, as well as ours, and out of respect for the deposit atlases, which far out, we love them. And I know that you all love them as well. So Paul, it's yours.
Okay, thank you very much, Helen. And thank you. I can see plenty of table space here in the room. So there's lots of white tablecloth showing. I did have a lot of people over the last 6 hours say, "Oh, look, I'm sorry, I have to go do this, I have to go do that, I've got a plane to catch, etc." But that's all good. So I think we'll be pretty gentle this afternoon. So I'd like to talk about the Northeast Queensland Mineral Deposit Atlas, and Nathan Fox also will be up doing some talking as well. I guess many of you are probably familiar with the Mineral Deposit Atlas concept here in Queensland that we've been undertaking, particularly in northwest Queensland, where I think there was about 20 22 deposits maybe that were in that Northwest Mineral Province Atlas. And now we've been looking at Northeast Queensland. I obviously want to thank the GSQ for funding the project and for providing a lot of input. It's fantastic to be involved with the GSQ. And as well as the GSQ, there's a bunch of names up here. Myself and Nathan and Rick are here in person. Jenna McGovern is also here over at the table, who did a lot of the work on the Deposit Atlas as well, as well as those other names that you'll see there. So let's step on. Oh, I guess before I should give you an idea of, I guess we're scheduled to go for about 90 minutes. It may not be quite that long. We'll see how it goes.
And there will be drinks in the bar out the foyer for those who stay around.
So about 30 minutes then. Yeah.
Thanks for coming.
So the 30 minutes will consist of me talking for a while about a general introduction to the Northeast Queensland Mineral Deposit Atlas, and then Nathan is going to give an overview of the Mount Carbine tungsten deposit, which is one of the Atlas chapters, and he's also, I think, on the end of that, he's going to tack on some information about some of the new work that he's doing up there. He's doing some work up there with EQ and Chronimet. It's really exciting stuff, looking at how you could potentially use ore sorting up there. Anyway, I'll let Nathan talk about that. And I sent around a link yesterday, or Evan graciously sent it around on my behalf. Thank you, Evan, which was to the Geoscience Analyst download, which is the free viewer available online, and also the link to the Bell-Gammon 3D data set. I was sort of dreading to ask this question. Did anybody download that at all? Oh, that was a one yes there. So I was going to run a bit of an interactive exercise, but I think maybe I'll just have a bit of a run through so you can see what sort of data's in there. And then there's a few questions at the end. We have a short Mentimeter survey, I guess, just to help us improve what we're doing with the atlases, and also plan ahead for another potential atlas as well. And I guess it was great this morning hearing Kobie talk. So much of that stuff and deposits that he mentioned are actually in this Mineral Deposit Atlas, and a lot of the data actually came obviously from Kobie's scouting around on Boxing Day, by the sound of it, to go and get that data from those mines that were going on to care and maintenance. So thanks very much for that. So the Mineral Deposit Atlas concept, I won't talk too long about this, because I'm sure that most people in the room are over this. When I say over it, I mean across this. So the concept is to act as a reference and a compilation document with a focus on the deposit characteristics and the halo and signature from an exploration perspective. So it's not to document the deposits, genetic models, reasons for those genetic models, or timing, etc. It's all about understanding what the data looks like in common exploration data sets, be that geology, geophysics, or geochemistry. And each chapter is comprised of two parts: a descriptive document, and in that document, I'll talk about it in a minute, we've tried to put in as much, I guess, visual material as possible. Basically, it should be an enjoyable read, and for those who love looking at rocks and different data sets, that's what it should be about. And the 3D Atlas, which is done in Geoscience Analyst. I'll talk about that in a moment. So the 3D Atlas, Geoscience Analyst platform, but also the raw data is provided for those who wish to use their own platform as well. And I guess that we heard Steve talking about the Digital Earth platform, and part of the I guess one of the big pushes behind the Digital Earth is to move away from this concept whereby you download software, you download data sets, you install it, you activate, you register, etc., etc. So that's what the Mineral Atlas is at the moment, but the objective, I guess, is to move towards that Digital Earth online, easy access type arrangement. So hopefully all of this sort of stuff should be going into Digital Earth over the next year or two. Let me just hide this here. Okay, so this is the deposits. There are what, 11 of them, covering 4 metal associations, and I should note that compared to the Northwest Mineral Province Atlas, the Northeast Queensland was very much focused on critical metals or critical minerals, and it was funded under that GSQ project. So you'll see that the deposits are focused on tungsten, nickel scandium, tin, and then a couple of base metal and tin deposits. And it was it's really nice having a look at Northeast Queensland over the last couple of days in the data, and I've forgotten who it was, but someone was talking about those base metal deposits up at Mount Garnet and Balgammon, and I certainly agree with that. I think this area has a lot of potential for these sort of mid-sized base metal deposits as well as the critical metals. So just a quick look, excuse me, a quick look at these deposits and what they are and when they were found, etc. Those of you who've seen the Northwest Queensland, Northwest Mineral Province Atlas will notice a big difference with this table. Primarily, if you look at, well, not only the metal and mineral associations and the types of deposits, but the date of discovery as well and the method of discovery. So whereas in Northwest Queensland, the discovery in the early days was, as you see here, that word prospecting runs all the way down here. But in North Queensland, you had a lot more recent discoveries, particularly around about 1990, I think it was, when those 3 world-class deposits, Cannington, Ernest Henry and Century, were found up there. But in Northeast Queensland, well, you'll see 1984 was the last sort of discovery of the deposits in this atlas. So very, very different dates of discovery, and the method of discovery is primarily surface type activities, which is not surprising, A, given there's so much outcrop, but B, given the types of deposits that were being looked for, etc. So, you know, you don't tend to find people drilling to 500 metres undercover for tin horizons or anything like that. So it's not a surprise that they're mainly surface type discovery methods. The types of deposits, they're pretty much all of them, maybe apart from Scony, are related to magmatic systems. So you'll see Grisons, stockworks, sheeted veins, etc. And even the alluvials, the tins, were typically derived from magmatic related primary mineralisation. So the data sources, well, you'll see the first comment there, particularly from abandoned sites. So if you look through the deposit atlas, you'll find that the deposits with the most data really are things like Balgammon, Wolfram Camp, that were abandoned mines, as well as Mount Carbine, where Chronomet and EQ very kindly supplied us with a lot of data from their current operation. There's historic research, you'll see theses, collaborative research projects, etc. Public material, published papers, stock exchange releases, and I guess probably most importantly, the government databases from GSQ and Geoscience Australia. The regional data sets, we've tried to put, I guess, the same scale, same area data sets, and well, it doesn't really matter so much because they're not hard copied, they're digital data sets, PDFs, but at A3 type size, so there's plenty of resolution, and you can really have a good look at those data sets. And you'll see here a couple of examples, you know, geophysical, geochemistry, and geological data sets, so you can compare them all at the same scale and same area. So I just wanted to briefly touch on, and I won't go through this in too much information because I guess we've heard a lot about these tungsten deposits over the last couple of days. But the tin deposits were mostly down around Herberton and in the south, and as were the base metal deposits. And then these tungsten deposits, 3 tungsten deposits, well, Watershed and Mount Carbine, as you'll see, are up in the north there, and Wolfram Camp is down to the south. And what it's essentially representing is I guess, it's interpreted, particularly, you know, there's a lot of great work done by JCU up in this neck of the woods, as well as I see Vladimir Lisitsin sitting down there in the back row there. It's pretty much interpreted as a change of erosion level. And so what you'll see in this map, for example, is all the pinks down the bottom of the Kennedy Igneous Association, and then all the blues up the top of the Hodgkinson Formation sediments. So those two big tungsten deposits at Watershed and Mount Carbine are both sitting up there in the Hodgkinson Formation, and presumably in higher erosion levels. And so you'll see when you look at them there that there are a couple of granites exposed around that area. But when you look at the gravity data, you know that those granites, those low density granites, are much more vertically extensive and haven't been eroded down quite as far. And this is what we see here in the geophysical data. So there's some fantastic data sets here. And it really struck me, Dave Purdy, I think it was talking about the alkaline complexes and noting, you know, how much heterogeneity there was in their compositions. And I think that the geophysical data sets are a great opportunity to really map out the varying lateral compositions in some of those igneous complexes. Wolfram Camp. So when you look at the JCU work, they tend to break the mineralisation styles up here in northeast Queensland into three types: tin mineralisation, tungsten mineralisation, and then tungsten moly bismuth mineralisation. And Wolfram Camp is typically considered I guess JCU considered the type example of the tungsten moly bismuth. It's I guess like so many of the mines up here in northeast Queensland, a lot of them were discovered back in the 1800s or the early 1900s, and so hence the historic type photos. So what we've done in the 3D is to in geoscience analysis is to take that 3D data that was available, whether it be drilling, old cross sections, regional geological maps, etc. And we've tried to sort of pull it all together. And you'll also see here at this is the I think it's the moly grade surface, and you'll see that there's also the underground workings, for example. So a bunch of data came in from this being an abandoned site. So we put that together in 3D, and just to try and give that context of what these things actually look like. And so for this example. You know, you can't quite see it in this diagram, but if you go into the 3D model, you'll see how that granite relates to the mineralisation that basically wraps in the top of the granite at the contact with the Hodgkinson Formation, it being a grise and all. So it's basically trying to take these old systems that are well documented in papers back in the 1960s and 70s, and to a certain extent from JCU in the last 10 years, but then to try and really give people an idea of what they look like, their geometry and their zonation in 3D. And that's one of the old sections. So you can see that's basically a grise in the outer skin of the I guess what's called the James granite, and then in contact with the Hodgkinson Formation. And what we've also tried to include where possible, which has been a bit difficult in some of these older deposits, is shots of what the rocks look like. So some nice examples of the grises with all the mica and the quartz and the different sulfide mineralisation. You see the molybdenite and the bismuth and wolframite up there. So I guess if you can't get out to the site to have a look at it, I guess there's a great chance in Queensland you can now go and look at the core from here. It sounds like it's in Brisbane at the moment, but it might end up in Mount Isa eventually. So what the rocks look like. And then we've put in the geophysical data as well, as I mentioned, so that you know, as I was saying, the magnetics and the radiometrics in particular are fantastic tools out here in these sort of felsic magmatic terrains that have a lot of potassium and uranium and thorium and variations in those elements. And we also include the stream sediment data that I guess we all know exists, however many million points there are in Queensland now. Mount Carbine, Nathan's going to talk about Mount Carbine. It's a spectacular deposit. When you go and look at the 3D model, we got a lot of great information from EQ and Cronimet, including some drilling information, some surfaces representing the different veins. That you can see all those veins in the wall of the pit here. I think this was a photo taken by Nathan or Anita when they were up there. And that's a very simple diagram. And I think the next is a... Thanks, Nathan. I've ripped this out of your presentation. This is just to give you an idea of what's in the Geoscience Analyst project. So we have the regional data sets, the satellite imagery, the regional geology on the topography, etc. This is just a grab that Nathan had put together from Geoscience Analyst. And then we have a look at some of the geophysical data so we can tie it in with the geology. And then you'll see in the middle there, starting to appear is the detailed data around the data set. So that's probably the detailed magnetics there. Plus you can see the pit and a few other items there, the decline, etc. And then you start to see all of this material is in the Geoscience Analyst project that you can download. Okay, so it's the logging, it's the assays, and those shells of the different geological surfaces and the veins, etc. So it's a really nice resource that allows you to really understand what this deposit looks like. So that'll be the veins that you're looking at there, and some of the faults in those other surfaces. So this is I guess what we've aimed for is this sort of 3D information that gives you a really good understanding of the deposit. Let's see. Watershed is the other big tungsten deposit up there. You know, when you look at this neck of the woods, it's really Mount Carbine and Watershed that are the two big deposits. Watershed is itself sort of a deformed sheeted vein system, I think. Slightly different. It's more calcareous rocks, but still part of the Hodgkinson Formation that host it. You see in that in shot number D up there. Yes, that's it, number D up there. That you know, it's a real myelinitic fabric through the deposit, so it's very different to Mount Carbine and Wathen Camp in terms of being highly deformed. And this is just some material from Jaime Poblete, who did his work at JCU on this deposit. So we've sort of tried to suck as much information as we could from all the studies that we could find, and he did a great job up there, some very detailed mapping. And that's a screenshot of the deposit itself in Geoscience Analyst, the material we could get together. And in this case, you can see that there's the soil data that's been collected over the top shown there as well. All right, so this is just a summary. Those are the deposits. How the atlas is delivered is the hard copy, and you can see a couple of examples there of from the front pages of those different deposits. And then there's the 3D model that you can see down the bottom here. Now they're available for download from either the GSQ data portal you'll see there, or also from the SMI website as well. So it's all up there, and you can download it, and there's a lot of information. Hopefully it'll help people get a good understanding of what these deposits look like, and I guess most importantly encourage people to be exploring and discovering I guess the next generation of particularly critical metal deposits up there around northeast Queensland that you know, we'd all obviously love to see another deposit come online. Okay, thank you very much for that.
Thanks
so
Helen.
Much, Paul.
All right, before we bring Nathan up, do we have any questions for Paul? Yes.
Thank you. Is this the end of the Northeast Queensland Atlas, or are you going to look at the copper deposits too?
This is the end of this current Northeast Queensland Mineral Deposit Atlas. We're looking at another round and talking to Helen and GSQ about another round of Atlas. And I'm going to put up a bit of a Mentimeter poll. I guess we'll cut to the chase a bit later to get some recommendations about what should be in there. So log onto your open your browser on your smartphone and enter all those names of the deposits in there that you think should be in the next round. Yep.
All right, any more questions for Paul? Stand in the middle of the room. Visit round. Are there any online? Oh, here we go. Yeah.
Okay.
No, I think
yeah.
it's just John Menzies sharing the link.
I'll let you get it off, Evan.
Yep. Okay.
Thank you.
All right. Well, then next up and following on from Paul's great introduction will be Nathan Fox,
sure.
who's going to talk to us about Mount Carbine.
Again, try it out.
Okay, thanks, Paul. That was obviously another great introduction to the Atlas series. I suppose one of the main things about this talk is the data is available online, the Atlas is there, the data is there. We probably don't need to dwell too much. We do appreciate it getting on a little bit. I guess one thing I just kind of want to highlight is obviously, as Paul has already, the huge amount of people that put a lot of effort into putting these together is an extraordinary amount of work and it's really appreciated. So I think there's a lot of people here that contributed. Mount Carbine was pretty much the only one that I really did contribute to, so I tend to talk about it when I get a chance. I'm just going to quickly go through some of the discovery and processing history. I think it's a really important story, particularly as we're going back to reevaluate mine waste as well. This is really a kind of a success story for that model. The regional and deposit geology, I think I'll briefly mention as well as the genetic model as well. I'm going to focus a little bit towards the end on just a couple of new projects, some relevant to the atlases and one not really, but kind of an interesting forum to kind of talk about it anyway. But I won't keep us too long. And yeah, just to note that in honor of Andy White, who passed away last year, they EQ Resources renamed the open pit. So there we go. That's a nice picture of the pit. So discovery and processing history, as you know from Paul's introduction, located 80 kilometers from Cairns within this cluster of tin tungsten deposits, so Mount Carbine, Watershed and Wolfen Camp. It was discovered in the late 1800s based on outcropping quartz veins. So clearly a very, very visible surface expression of this style of mineralization and picked up early by those prospectors. The early small-scale extraction finished in about 1920 and produced about 3,000 tons of wolframite concentrate. This is kind of the important part, I suppose, in the 1960s. An initial reprocessing campaign was launched by the Roach brothers, and then they moved on to an ore sorting approach. So this is kind of like, well, they saw an opportunity and they tried to use technology to automate that. The optical ore sorters were not the most appropriate for that particular type of ore, and we'll talk a little bit about some of the ore sorters that are using now on site. But through that operation, they managed to produce nearly 15,000 tons of tungsten. So yeah, quite a large operation at the time. Obviously, another commodity that's fought with kind of at the mercy of the stock market or the metal price. Obviously, the mine had to close down in the late 80s. Currently, though, owned and operated by EQ Resources. The JV with Chronomet was originally for the reprocessing of the waste, but they're still highly involved in the operations as well. The current resource from the EQ website shows that they've probably got about 27 million tons of ore and equivalent to nearly 7 million metric ton units of tungsten. Some of these are not necessarily now included in their report, so the optical rejects and the tailings, but they will intermittently reprocess that through their plant. But this is where they're kind of concentrating most of their effort, is the hard rock zones. They've done a lot more drilling recently and tried to improve this hard rock resource with the aim to go back into the open pit in the next year or so. In terms of the regional geology, most of you in the room know it's hosted by the Hodgkinson Formation, which is part of the Paleozoic Mossman origin. It forms this really distinctive northwest trending belt, and we can see that through the geology and through the regional geophysics as well. But obviously the granite relationship comes from the Permian and Carboniferous granites that intrude, and they're part of the Kennedy Igneous Association. In terms of those grey rockies that are hosting the Permian Hodgkinson Formation that hosts mineralization, they're metasedimentary rocks. Grey rockies, lower gracious metamorphism. But again, you can see that they have this pronounced northwest structural fabric, and the age of the granites around there are around 280 to 285. Apart from Mount Alto granite sitting over here to the southwest, which is slightly younger. So some of the data sets you see in the Atlas and also in the Geoscience Analysts package includes the magnetics and gravity anomalies. This is obviously the magnetics, and you can see that the Hodgkinson Formation is quite responsive and has this distinct northwest trend as well. Some of the other data sets that are obviously quite useful, the stream tungsten and tin, you can see that this is a really bad map, badly optimized for this, I'm so sorry. But if you take my word for it, the tungsten increases around the base of the Mount Carbine granite, and so does the tin. So these data sets still seem to be quite relevant. Perhaps there's more coverage that could be done. I'm not too sure about whether or not that's something that's on the agenda, but certainly in terms of exploration, the regional stream sediments seem to be highlighting hotspots for these mineralization styles. The deposit geology was really covered in the 90s and 80s. The high strain zone through the center of the deposit, which seems to be causing the lineation through all of the the veins and the structures, is really still pronounced in a very northwest trend, but we do see some variation in those vein orientations towards the northeast. And that's something that EQ are following up on with their recent exploration drilling. There are variations in mineralization. So as you move towards the east, the Iron Duke system has been rumored to be a kind of almost skarn-like, but I certainly see an increase in scheelite towards the east there as well. The scheelite and wolframite relationship has been talked a little bit about yesterday as well. And I think it's something that's going to be quite interesting to look at. And I've got some slides towards the end that might be touching on that as well. And then just to highlight that there's some dikes as well that cross-cut the high strain zone and the mineralized veins. In terms of the mineralization, the deposit is highly structurally controlled. Obviously, in these very broad quartz veins, they do tend to vary in thickness between 1 and up to 200 centimeters in width. The models that Paul's shown shows these kind of groupings of the veins, but it's important to note that there are subtle variations within them. Some veins are mineralized and some are barren. And one of the aims of the future work is to really try and understand the fingerprints of those mineralized versus barren veins to help selective mining along the way. And because of that, the grade ranges quite dramatically between 0.12 and up to 2.8% tungsten oxide. But they do tend to extend very prominently laterally. And as you can see now, also towards the deeper part. So there's some historical adits that have been put through here that haven't been accessed yet, but there's going to be future attempts to try and get in there and potentially to find an underground resource. The resource is cut at the South Wall Fault, but the sense of displacement is a little bit uncertain. So I think they're still thinking, where could they pick up the other part of this ore body potentially? Yep, so as I say, extensions to depth and EQ are trying to drill those out as well. And this is just one of the older pictures of the Mount Carbine open pit from 1986. So highlighting the thickness of those veins and the kind of very distinct vertical nature of them and pretty high bench height as well. So the mineralization is really characteristic here. Very dark Hodgkinson formation with biotite tourmaline alteration, but then cut through by these very distinct quartz veins. The problem with the nuggety mineralization is, how do we know if one of these veins isn't mineralized further along strike? And quite, vice versa. If you see a mineralization in one vein, how do you know if that vein has mineralization within that further up as well? So yeah, just showing some of the intrusions, the rhyolite porphyry and the tonalite porphyry. Yambo Cheng did quite a lot of work here back in when he was at James Cook and presented a new paragenesis. And I think this is going to be quite key when we start integrating some of the new data sets I'm going to talk later, seeing how this holds up and if we can actually use this as a predictive tool to better understand mineralized veins in the pit as well. I suppose the main thing to bear in mind is that there was an early phase of veining which is these kind of wispy, partly deformed veins that are part of the Hodgkinson Formation. They've been cut by the very straight-sided, either mineralized or barren wolframite and scheelite bearing veins. We do see some apatite, salvages of biotite, salvages of tourmaline, and we've already heard from Courtney about this from yesterday as well. There are variable amounts of sulfides as well, so it's not a completely sulfide-free system. We do see chalcopyrite, pyrite, and arsenopyrite. Historically, the ratio of wolframite to scheelite was assumed to be about 7:1. But I think as they're doing more and more studies, we're realizing that's actually not necessarily the case, and there's a really complex relationship between the scheelite and the wolframite. Nearly all of the wolframite has this kind of dusty overprint of scheelite, which is kind of causing some, not necessarily some troubles, but sometimes that scheelite does get lost to the fines. Okay. So this is just some of the kind of characteristic work that we've, or characterization work that we have done at UQ on some of these samples. So this is an example of one of the mineralized veins. You can see in shortwave UV light, the scheelite shines very clearly. We wanted to try and understand what the difference between the mineralized veins and what we interpret here to be a barren vein. We don't see any scheelite or wolframite in the RGB image or in the UV light. The micro X-ray images are a little bit raw. They haven't been processed fully, but you can see the tungsten picks out the scheelite very clearly. It is very, very faint, but there's some blebs of elevated calcium here, which is the scheelite as well. We do see calcite in the veins as well, so that's why the calcium's very high. And then just picking up the sulfides, and particularly the chalcopyrite. We had limited exposure to this technology. All explores a 3D tomography drill core scanner. In your mind, you've got to flip this upside down because I forgot to rotate it. But you can see that this is the mineralized vein that correlates to the scheelite in this particular vein. And up here is the barren vein, which is actually this vein. So basically, just switch it around. This could be a very interesting tool to actually help delineate mineralized versus unmineralized veins. However, when you've got such a good response in 2D, there's absolutely no necessity to go to 3D. But we need to understand if this barren vein here doesn't suddenly become mineralized further along strike and look at those controls. So in terms of genetic model, EQ are using models that have really come from China and South Korea. We're looking at the kind of extended granite-related models, so we can see that as we get closer to the granite intrusion, we may see deposits more like Wolfram Camp, but Mount Carbine is certainly sitting up here in that kind of distal position away from the main intrusion. I think the thing that we really wanted to try and understand, and I'll hopefully get a chance to talk to Courtney about, is that vertical zonation mineralogy. Whether or not that actually can be picked up, particularly with the high logging that's been done there. And I know that Daniel, you talked about this as well, and I think it'd be nice to understand if that's something that could be used for exploration further along the way. So just to highlight again the Geoscience Analyst package, it's available online. Please do, if you wanted to play with it. Again, as Paul said, the EQ and Chronomet are really generous when they donated this for us to look at. They've obviously done some new work as well, but that's not included currently in that package. Okay, how are we for time? Are we all good? Okay, so I've just got a few projects that we've done with EQ and Chronomet. The first one is a little bit unusual, so it doesn't really fit with the deposit model, but it kind of lends to the next part of the story. So I think I might just talk about it very, very briefly anyway. One of the things we were tasked with was the first task for the ore sorter they brought on site, which is an XRT ore sorter, was to process the low-grade stockpile. I don't think I really made a big deal about it, but on the site map, there's about a 12 million ton low-grade stockpile. This was kind of either the very low-grade material that was poured out of the pit just before closure, but it's also been accumulating for a certain amount of time during the production. EQ Resources were really interested to understand the grade distribution across that low-grade stockpile. Is it consistent, and do you see a variation within the particle size? A lot of this material is used for a quarry operation. So if they could understand a little bit more about that grade distribution, then they could potentially allocate whether they're going to send material to the quarry or whether they're going to keep it for the process plant. So these are some of the sample. This is one of the pits that was dredged from the stockpile. It was put through a field-based screen, and about 6 or 7 tons of material was sent to UQ for us to process. Unfortunately, we had to do it by hand, coming out of these bulkers over Gilson screens. And this is kind of an example of what we're trying to see here. Really well mineralized particles in a very coarse particle size. For them to extract this, this also has to be crushed and go through the either through the sorter or directly to the process plant. So this is the lobe of the low-grade stockpile. You can see the grade distribution on the plot on the right-hand side. It is actually fairly consistent. There's not too much variability. There's just a few areas that are decreasing very highly in grade and actually almost become very uneconomic. It's a very low-grade stockpile anyway. I promise I won't dwell on this too much, but essentially what I wanted to highlight is when you screen this material, the coarse material here is about 100 mils, so up to about 10 centimeters, going down to the fine grain material. From the first pit, we saw a really nice increase in grade into the fines, which seemed really good. The mass distribution wasn't that great for the fines, but essentially this is the material that goes straight to the gravity plant anyway, and this goes to the ore sorter, so all seems quite good. When you look at the distribution of the tungsten, again, it holds up quite well. Most of that material is either going to the sorter or to the process plant anyway, so that's really good. But sampling is always really key. So when we looked at some of the other sample sites, you can see that actually we get the highest grade in the very coarsest material, and that tails off into the fines. However, maybe the highest grade, but in terms of the overall tungsten distribution based on mass, this doesn't seem to be particularly significant, and we still see a general increase into the fines. One of the things that we're still working on is actually unraveling why that might happen. Is it something that happens in the pit during blasting, and how does that tie back to the original geology in the pit, and how can they potentially utilize this in the future? So as a kind of a very broad summary, the -8 goes straight to the gravity plant through jigs. The +8 to -26.5 goes to the XRT ore sorter. And then you would then reject pretty much above 26.5. So in this scenario, we could reject just 12% of the mass and would only lose 1.4% of tungsten. However, in the second scenario, it flips around and actually we're going to lose, for 37% of the mass, we actually lose 30% of the grade. So it's not quite as clear cut as just taking one slice, one cut. So understanding why this might happen is going to be really important for them when they actually do start their screening. So in light of that, I kind of want to move on to another project that's only just started. I've called this Advanced Manufacturing Commercialisation Fund. It's a commercialisation fund through the AMGC, which is the Advanced Manufacturing Growth Centre. So that's my second typo of the day. Essentially, the reason I wanted to kind of show you this is because characterising these large oversized materials, often these will be sent away to places like Sydney as coastal defences. But you can see this large block here. It's probably about the size of one of these tables. It's really highly mineralized, and understanding a little bit more about how you can pick these mineralized materials and their geological context or their alteration footprint is really quite key. So the next thing is to understand if we can do it on small size particles or relatively small size particles, can we then move back into the pit and start characterizing it? So with PlotLogic, who are a Brisbane-based startup, a hyperspectral company, EQ Resources and UQ are working together to try and understand how we can better do this. So PlotLogic have developed a whole range of sensing equipment. They've almost at the request of EQ Resources, they've built a dedicated hyperspectral core scanner. So it's their first kind of foray into core scanning. This is a high specs near infrared to short wave infrared imaging camera. And essentially it works in the same way as most core scanners do. The core just passes through underneath. There's an imaging spectrometer and the data is processed pretty much in real time on the side. The thing that we want to try and understand here is how can we use this for grade control? Does it give EQ something they can use in a range of different settings? Can they use it in the pit? Can they potentially also use it in either over conveyor scanning or also in shovels as well? So this is the kind of the overall aim. Ultimately, this all links back to the mineralization and what can you detect with hyperspectral mineralogy. UQ's kind of contribution here is that we're going to be working on the validation test work using micro-XRF and other mineralogical tools, and it kind of links back to some of the things that Courtney and Carell were talking about earlier in the day. So PlotLogic said to go ahead and show these. These are quite preliminary interpretations. So Tony Bainbridge from EQ gave PlotLogic a series of example rocks and said, if you can tell us what these are, we're kind of happy and you know, we're going in the right direction. So you can see some Hodgkinson Formation, typical standard kind of wall rock. The black here is wolframite. and obviously quartz, and then a few other shrapnel bits around the side. In full disclosure, there's proprietary algorithms that PlotLogic are using. And when they showed us these, they said, oh, this is something that's picking up mafic minerals. But then when we kind of discussed with them and flipped backwards and forwards between the wolframite, we said, well, we don't know what you're doing, but you're picking up the wolframite. And it's something that hasn't really been discussed or shown. I think, Daniel, you did mention that if you, in the high log data set, if you go over across a really coarse piece of wolframite, occasionally you may get a spectral response. So there must be something that's happening with the wolframite for it to become spectrally active, but this kind of changes the way that potentially the technology can be used at different points in the mining operation. So other things that are picking up very clearly, things you shouldn't really be able to pick up with a visible shortwave infrared system is quartz. So again, we see very high concentrate or higher heat map for what's been interpreted as quartz, and most people probably would already guess this isn't really picking up the quartz, but it's quite likely to be picking up fluid inclusions inside the quartz. So again, this is a really nice tool to identify mineralized veins and potentially also where the quartz has a lower intensity, the smaller inclusions, which could be the earlier vein generation. And then other minerals that we've talked about as well, tourmaline and different chlorite types as well. So there's certain things that are in this preliminary stage that are being picked up. And the key now is to link them back to parogenesis and see how we can actually use this to identify mineralized or barren veins, both in the stockpile and in the pit. So in terms of implications for Mount Carbine, this is quite important. We think that potentially the hyperspectral identification of wolframite may be due to the manganese substitution. But for you guys that are working on the spectrum, we're really happy for you to contribute on and suggest what it could be. There is a whole range of data available from an honours thesis that was put out of the University of Adelaide a little while ago, and they did an abnormal amount of microprobe analysis, but you can see this very clear transition from ferberite, the iron-rich end member of wolframite, down to the manganese end member. So certainly we think that if we are seeing it, it's related to a substitution into the wolframite. But one of the things that would be really important to understand is, does that spectral response change at different compositions as well? Yep, so I did have some other slides. Essentially, they are it's a slightly different rock. There's a little bit of an offset between their sampling and our sampling. So we've got some rocks that they haven't yet scanned, and we've got some rocks that we've scanned and they haven't yet scanned. But this is another example just of the use of micro-XRF. So Pirelli showed a really nice example from Wolfram Camp. It's becoming to be really quite an important tool in unraveling some of these complex relationships. So you might just be able to see it. There's a green box here that's just picking out this straw-coloured scheelite and the bladed wolframite. And one thing that we want to try and understand is when you look at the UV, why do we see the wolframite that in RGB images looks very black, has this kind of dusting of scheelite all the way through it. And that is obviously related to the kind of the hydrothermal overprint, but unraveling that is always going to be one of the things that we aim to do. So I'm just going to shoot through these really quickly, not really to dwell on them. The tungsten, obviously, it correlates really well with the scheelite, but actually when you move into those wolframite grains, there's actually dark areas which indicate that the tungsten's been removed. So potentially all the black doesn't necessarily correlate to a grade. So in the previous, I don't want to say the olden days, but in the 80s, one method for estimating the grade was to almost wrap the core in an acetate sheet and draw around the wolframite and then unravel it and estimate the grade. But it seems that potentially that may not have been wholly correct, but as good as you're going to get. But certainly there seems to be a lot more complications going on. You can't see that that is this with calcium. So again, trying to highlight those scheelite areas, and you can see that the scheelite is progressing all the way through those wolframite grains. And manganese, which potentially could be causing that hyperspectral signal. So one of the things that we really want to do is to then look at these in more detail, understand the manganese distribution and concentration, and then potentially relate that back to the vibrational spectroscopic response. Okay, and I think the last one, just sulfur, just because we do see sulfides through this. And one of the aims of the AMGC project is to actually also understand the geoenvironmental characteristics of these materials as well, which is where Anita's going to be partnering in and bringing her expertise to that. Okay, I guess this was the last thing I wanted to show was just silica. Yep, it's not that great, but for those of you in the room that perhaps have looked at these as well, there does seem to be a slight tin shadow around the quartz as well. So I was curious if anybody has seen something else in some of their XRF images. Is the tin real? Should we discard it? Does that relate to the fluid inclusions that we potentially see in there? I think there might be a little bit more of a story there. So yeah, okay, essentially in the next part of this particular project and how it kind of links back is we're going to validate that hyperspectral imagery with the micro XRF, microprobe and potentially laser ablation. There's a reference sample suite from across Mount Carbine with petrology that they want scanned and characterized. And then in the next few months, PlotLogic are going to move into the pit with a robot, essentially with a hyperspectral camera attached that's to map those benches. And then we're going to see if we can pull out some of these geological relationships from there and then move towards more of a geology and grade model for Mount Carbine benches ahead of potentially re-mining. And this is a picture of the pit that must have taken about a month or so ago, and the pit level, the water level is draining quite significantly. So they're working hard to get the water out and then hopefully get back in there. So I think I might just summarize. Well, most of this comes from the Atlas. So essentially, the key points, it's a quartz vein hosted tungsten deposit. Potentially, there are many more of them in that region. So exploration around there is going to be really quite important. I think one thing that we can show from here is that the mineralogy and the texture of the mineralization means it's very amenable to ore sorting, which is a really important step to upgrading very low grade deposits. From a bulk mining perspective, this potentially wouldn't be economic if it was just a pure crush and grind operation. So yes, certainly further resource potential at Mount Carbine and regional discovery opportunities will hope. Okay, any questions?
Thank you. Thank you so much, Nathan. All right, questions about Mount Carbine? I'm looking. Oh,
thank you for that. Excuse me. Do you know how Mount Carbine watershed and Wolfram Camp, in terms of resources, grade and tonnage, shape up against most of the operating or the economic tungsten deposits that are being operated elsewhere in the world?
Can I defer to Paul, who has just done a tungsten compilation for the New Economy Minerals? I think my knowledge would be kind of not. Is that okay? Do you,
I was reading something the other day.
Sorry, thank you.
Sorry, I was reading about not on a global scale, but on the Australian national scale. I was reading something the other day, and my recollection was that the northeast Queensland deposits host about 20% of the Australia's tungsten resources. So that's my estimate off the top of my head, and I think the majority of those others are down in Tasmania. Okay. But please don't quote me on that number.
Thank you.
Any questions about the hyperspectral stuff from our hyperspectral team? I'm looking at Dan, and he's looking like a like he doesn't want me to
grill me afterwards, not on the stage.
Dom has a question.
Did you say a hyperspectral robot?
Yeah. It's not artificial intelligence yet, but it's I think that happens in Brisbane. Yes, but I think there are issues in that pit's just been drained. There's a lot of boulders and debris. So before that robot goes in, I think it needs to be optimized for that condition. But yeah, certainly they want to try and have an automated way of bench scanning in certain levels, and potentially those benches are quite tall. So you can't just point it upwards. I think it needs to either elevate or be raised. And I know that Steve's going to say put it on a drone. Yeah, so I just save you from asking it, but yeah, potentially that's something they could do, but I don't yet know if they've got that capability or if that's what they're planning. Sure.
Oh, cool.
Any more questions? Oh, Paul has another question.
And just before I ask my question, I should qualify that I have seen that robot and it is nothing at all like those beautiful humanoid things we saw on the slides yesterday. It's a clunky couple of boxes with some tracks on the bottom, but it's highly effective apparently. I guess my quick question was, Nathan, that those plots you showed about the size distribution and the grade.
Oh yeah.
Is there anything from sort of visual inspection that gives any clues as to why that might be? It looked like pit 3 was different to the others.
It was quite different. The thing that we wanted to do was to go back to some of those size fractions and physically lay out all of the particles and identify them. But as time and deadlines came through, there's only really one way that you can assay a particle, and that's to crush it. So most of that material went through the crusher, but we've got all those materials analyzed using the TEMA, but we're just a little bit backlogged in terms of processing that. So the physical intact attributes are going to be a little bit hard to pull together. We do have some photos, but the mineralogical attributes we will be able to pull back together. So that's kind of on the next list. Yeah.
Any more? Oh, another question for you, Nathan.
Could you expand on the techniques that you use to distinguish between the mineralized and the barren pipe, and what's the process behind it?
It wasn't rocket science in our kind of the small window that we looked at there. Essentially, we kind of guided by the presence or absence of the wolframite or the scheelite, but there is question about whether or not along strike you actually see in those veins that appear barren, whether they actually do contain mineralization. So this probably does involve actually getting that data from the pit and being able to physically see the mineralization along strike, because I think previously it's been quite hard to be able to pull that together, particularly from drill holes that may just pierce a vein kind of almost perpendicular to the strike of the vein. You don't necessarily always capture the mineralization. So we haven't done it yet, and it kind of almost moves outside of the scope of what we're trying to do, but we're trying to give them the I guess, EQ, the ability to then take this data and have confidence that they can actually do that from the core scanning that's going on. So, so PlotLogic have been on site for probably a month or two, scanning the entire core library that's there. But there's going to be a lot of post-processing and interpretation, which EQ are going to do themselves. So hopefully that's kind of part of the story that they'll gradually be able to unravel and hopefully put that back into context in the pit and actually look at how those veins appear in the actual pit. So I don't think I answered your question particularly well. I don't yet know, but hopefully this is one of the tools. If anything's going to do it, hopefully it's this that can do it.
Any more questions? All right. Are there any online? No? Okay. Right.
I'll let you do that.
Now we're going to swap back to Paul. Bring us home.
Yes. It's getting close to 5 o'clock.
It's getting close.
No,
to
you
5
won't.
o'clock.
You won't have to wait 42 minutes. No, that was great. Thanks.
All right. Thank you. Thanks, Nathan. That's so much interesting stuff happening up there at Mount Carbine. What I wanted to do was just have a quick run through what we see, what we've put, I guess, in the Belgammon geoscience analyst model. I was going to sort of run through a lot of the different data items that are in there, etc. But I think instead I'll just have a quick look. I was looking at the model last night, and then I guess it was brought more into relief today, all the discussion, particularly from Avish about indium and copper and how the whole story fits together. And it's actually quite interesting when you go and have a look at the Belgammon model, which has a hell of a lot of data in it. And it really tells a nice story about the indium. Well, I think it might tell a nice story about the indium and the copper distribution. So just briefly to give you a feel for what's in these in the 3D models. Basically, what we did, we tied the gift area down in Silver Valley, which has a lot of tin deposits in it as well. So, and it's very close to Belgammon, so we put it in the same model. but we'll just look at Belgammon today. What we typically put in these 3D models is the regional data set. And so you'll see that there's the satellite image and the DEM to give you some reference points to the topography, etc. We put the geophysics in there. Okay, so you'll see in this case we've put them in as images rather than actual digital data grids, although the data grids that will be in the source data. So that we've put in the magnetics, the potassium, the thorium, and the uranium, etc. So these are the regional geophysical data sets, and you'll see that's where Belgammon sits right there. We've put in the regional geology, so that oh, there we go. So that's up to the north. Oh, excuse me. I feel like you're on a sideshow, a carnival or something, going up and down those hills. There we go. So that's the regional geology, and we also put in, I guess, as you've seen on a couple of different presentations, the regional geochemistry, particularly the stream sediment database, which is not highly populated in this area, but you'll see certainly some down at the south here. So they're the regional data sets, just to provide some context. And then you'll see from Belgammon is one of the better populated 3D models. And so we have the block model. Let's zoom in on that. Okay, so that we have this a very nice orthomosaic over the deposit, which is incredibly detailed. I think it's something like a 5 centimetre resolution orthomosaic that we put on the topography. We have the block model in there, so you'll see that that's the coloured sections there. I'll turn off the DEM so you can see that block model. Okay. And what's in the block model, if we open it up, is silver, arsenic, copper, and indium and tin are in that, and it provides some really nice, some nice insights as to the distribution of those metals through the deposit, which we'll get onto in a minute. We also have the 3D geology, so that what we've done here is the orange is the Una porphyry, which from hearing Avish talking this morning, I think that's about a 330 million year old porphyry. And then you have this later Slaughter Creek volcanics, sort of dikes that are cross-cutting the system, and you'll see them there in green. And so this is this sort of shallow dip that you have on the Una porphyry, and and the mineralisation appears to be very strongly spatially associated or within that Una porphyry. And then there also in here are some isosurfaces of the grade, so you'll see that in there. I'll turn the block model off. So there's some sort of rough isosurfaces. So that's the 0.4% copper shell there. And then the one other thing is the infrastructure, and there are where possible in most of these deposits in all of the deposits where we could find them, a lot of the old sections with the geology on them, etc., and the drilling in this case. So we've put them in registered, of course. But what look at this last night, and oh, your internet connection's unstable. That shouldn't worry us. So that there's the sections. I'll turn them off. So this orange is the Una porphyry. And the green, as I was suggesting, is the younger slaughter yard house volcanics, and in this case, the red is the copper shells. So if we apply a slicer to that, so that we're essentially putting a section on, and so what we're having a look at here is the Una porphyry in orange, the slaughter yard volcanics in the green. And then in the red here is the copper shell, and then the drilling itself is actually the indium distribution. So there's a very strong correlation between the indium and the copper, which is not surprising given what we heard this afternoon from Avish. But one of the really interesting things in looking at this is that when you look at the high-grade indium is actually distributed here around the younger slaughter yard volcanic units. And that's, I thought it was really interesting hearing about that textural evidence with the recrystallization of the sulfides, etc., earlier this afternoon. So that perhaps when you look, and this is exactly what these deposit atlases are aimed at, is when you look at these spatial distributions, you start to get a lot better insight into perhaps what's happening. And we all know when you look at deposits, you need to look at the microscopic to understand the textures, but you also need to look at the meso to macro scale in the deposit to understand the spatial relationships. So it's sort of really nice that we've got these great data sets that are all put together. And I was talking to someone a bit earlier and saying overwhelmed with data, but it's the sort of thing, it's a bit hard to do here in a workshop situation, but it's to spend a couple of hours and sit down and look at these sorts of things, and all sorts of information and insights pop out. So it's really, really useful. So that's just an example of the Belgammon data set, which is probably one of the better populated data sets. What I wanted to do to wrap up is basically I wanted to run a quick poll here, and there you'll see the code up the top. So if you can grab out your smartphones, I think it's going to be the last thing that'll be asked of you this afternoon, apart from maybe bending your elbow next. Here's a question. I guess we're always looking to see how we can improve, and particularly if we're going to be doing more of these deposit atlases, to make sure that we're catering to what people really want. So I guess the question is, what are the most important data sets in these 3D models, including what you've already seen, if you think it's the most important thing, or what is on your wish list as well? Is there anything else that should be going into these that you think is most important? And there's a bunch of things. For example, not many of the models have isotope data in them, for example. And it's always a little bit harder to go and dig through all the theses and get all that information, but there's a bunch of stuff. Drilling assay data, which is not a surprise, and it's the models that have that are always useful. So thanks for that. The block model, okay, yeah. And petrophysics is something that we don't have a lot of. We do have some in the Northwest Mineral Province Atlas, mostly off the back of the undercover Cloncurry study by CSIRO. Sections, yep, we have a lot of those. Particularly older sections that we're able to get. Isotopes when it arrives. Yep, alteration split up by zones according to mineralogy, which is incredibly important. Sometimes difficult to do without the data, but where we've got them, yep, that's a great. And drill core photos, we do have that in some of them that we saw has been taken into the Digital Earth a bit earlier. Multi-element geochem. Okay, excellent. Well, that's good. So thanks for that. That gives, we try and get as much feedback as we can, and there's no better scenario than when we've got everybody in the room waiting for a beer. So they're obviously going to put answers up here really quickly. So thanks for that. Now, let me see. I'm not sure. Rick, would you have advice as to how to move on to the next? Right arrow? There we go. Okay, thank you. And so the final question I just wanted to ask is, looking at another deposit atlas throughout Queensland, what are the deposits that you would like to see in there? Obviously, we've already done most up in Northwest Queensland, and these that we've seen today in Northeast Queensland. But what are the other deposits that we should be considering to put into another? Okay, Cannington, yep. Yep, Cannington was in the Northwest Queensland, but that's good. Any others? Oh, here we go. They're all coming up now. Kiston, a lot of gold deposits, which is good. We haven't all the atlases to date. We've only really touched on Tick Hill as a gold deposit, so that's great. Charters Towers coming up there as a big number, Ravenswood. Yep. Central Queensland porphyries. If anybody knows any particular, I know, I guess the Kobie Johnson prospect, if there's any other Central Queensland porphyries that people would want to put up there, please go for it and pop any names in there. Bajingo. Krakow. Twin Hills. Ravenswood. Mungana, Gympie, of course, down in the almost the southeast of the state. Free, smash them all in. The more goes in here, the more chance they are to be worked on. So that's good. Okay, and that's Chillago, is it? Okay. All right, excellent, good. Oh, that's good, thanks, because it's great to get some input as to what people think are the important deposits that we maybe should be starting to look at. Okay, month Molly. Oh, Monto Molly. Okay, all right. Yeah, on the smartphone, the fingers this time of the day. All right, okay. Well, thanks everybody for that. That's excellent. That gives us a good start to start thinking about what maybe what should be the next deposits to focus on. All right, I guess you will be happy to hear that that was all that I had planned. So we'll probably finish about 15 minutes earlier than expected. If that's all right with you, Helen, or did you want to?
No, I'll just throw to the crowd and see if there are any follow-up questions from what you've presented most recently or throughout the afternoon. Yes, Stephen Micklethwaite. Always.
It's actually a question kind of for the room, based on what Paul has on the screen there. Does anyone think there'd also be any value in doing a deposit atlas chapter on type deposits from around the world that are relevant to Queensland? So like really important IOCGs, for instance, that would be a compilation of everything we know about that, which maybe can inform our exploration here.
Yes. Sorry, go on, Helen.
I was going to say there's stunned silence if anyone wants to offer an opinion. John's always got something to say, especially if there are robots involved.
Yeah. I see what you're saying, Steve. It's basically in terms of analogies, for what we have here in Queensland. Are there any learnings we can take from elsewhere as to what what we should be looking for? Yeah.
Let's take that on advice, shall we?
Take that on. Well, I know that most people will be around here for another half hour outside. So,
yeah. They
yes.
might be more opinionated with a bit of lubrication. Okay.
Yes.
We've had a couple of questions online which we've been answering just by writing them about some of the previous talks from today and yesterday. So if anybody does have something burning and they didn't get to ask their question or they didn't get to catch the speaker, anything to bring up before we dissolve the proceedings? All right. We are going to make them recordings. They've been recorded, so we'll make them available online. Share the links with all the registrants. I guess we can, Evan's run away, we can do that. Okay. Well, thank you to Paul. Give him another round of applause,
thank you, Helen.
please. And all the speakers from this afternoon.
After you, Evan. Oh, sorry, you're going to hear all of my snuffled conversations in the back of the room.
I'll just speak into this one. That's all right. Okay. Thank you so much, sincerely, everybody who has stuck around to the death of this workshop. I really, really appreciate it. There's actually quite a few people still here, and that one empty table right up the front, which received very little love. But thank you so much for participating. Thank you to all of our speakers. Every single one of you have made this a really, really great event over the last 2 days. We appreciate the efforts that you go into to be here, to put all the material together and to present for everybody. And thanks to all those who have travelled to be here as well. I want to say thank you to Evan Marshall, who has been in GSQ since when did you? January. Okay, so really only like 4 months, 5 months, and has taken on the organising of our workshops, our webinars, and I just think he's doing an amazing job, and so he's really been the one that's pulled all of this together. So just a big round of applause for Evan. All right, now, and thanks to our online audience as well for hanging in with us. The numbers have been dropping slowly over time. If anybody does pop any questions in the online chat in the next 5 minutes before we switch that off, we will get back to you, I promise. And as we said, the session has been recorded, and those recordings will be available at a later date, probably in the next couple of weeks. It does take a little bit of effort to go through and get them ready for consumption online. So right now, let's call it quits and go out to the foyer where we can enjoy one last beverage or two if we so desire. So thank you everybody for being part of this workshop. Really appreciate it.